Vice Rector of Research and Transfer, and in the name of the university, it's a pleasure for me to welcome to this Polytechnic School of University Carlos III de Madrid to celebrate the first international conference on advanced materials and energy storage, which has brought together the most renowned national and international researchers working in this field. One of the strategic objectives pursued by Carlos III University is to work of excellent international and interdisciplinary research. In this sense, building on the excellence of the university and also of Spain, I would like to congratulate and thanks the convener of this conference, Dr. Bidham Pandit, Conex Plus Fellow in our university, who is one of the best examples of the development of international and quality research activity without forgetting the dissemination of the results promoted with conferences as the one we are holding today. Of course, I would also like to thank and to congratulate the research group Material Synthesis and Processing and the Department of Material Science and Engineering and Chemical Engineering for the organization and the success of the event, for the level of the contribution and speakers. I'm sure you will enjoy the scientific program during this day, and I hope you can have a few more days to enjoy also Madrid and its social and cultural environment. So thank you very much and welcome to University Carlos III de Madrid.
Good morning, everyone. So it is with great pleasure that I stand before you today to make a special announcement. We have already have a distinguished guest, Professor Christina, from Deputy Vice Director of Research and Transfer, who has generously accepted our invitation to be a part of our conference. I thank you from our group and from our university. Now, let me give you a brief the conference. Good morning, everyone. Ladies and gentlemen, and esteemed guests, colleagues, and respected professors, welcome to the first international conference on advanced materials and energy storage, ICAMES 2024. I am Bidhan Pandit, the convener of this conference. I stand before you with great excitement and anticipation as we gather here for ICAMES 2024, an event that promises to illuminate the path towards a more sustainable and efficient future. I extend a warm welcome to each one of you who have come from different corners of the globe to be a part of this dynamic exchange of ideas and knowledge. This year's conference holds a special place in our hearts as we navigate the forefront of energy storage solutions and more specifically explore into the fascinating world of batteries. As the demand of clean and efficient energy continues to surge, the role of batteries has become pivotal in shaping the landscape of our technological future. Our program is precisely crafted to cover a range of topics from lithium, sodium, to calcium-ion batteries and everything in between. There's something for everyone here. Throughout the conference, we'll be treated to an array of presentations, workshops, and discussion related to battery technology. Our distinguished lineup of speakers, leading experts, and visionaries in the field will share their insight and expertise. Their contributions will undoubtedly spark new ideas and perspectives that will drive the battery research and industry beyond. In addition to the formal sessions, I encourage each one of you to actively engage in the networking opportunities available. This conference, it's not about passive learning, it's about active participation. Be sure to engage in interactive sessions, ask questions, and contribute to the vibrant discussions. As we start this intellectual journey altogether, the advancement we make in battery technology today hold a key, more sustainable, resilient, and energy efficient tomorrow. Before we jump into the enriching sessions planned for the conference, let's take a moment to express our gratitude. A big thank to our organizing committee, sponsors, speakers, and each one of you for making this event possible. The main partner and sponsor of our conference is CONEX Plus, which is our training and incoming mobility program that aims to accelerate the development of international experienced researchers in UC3M within the framework of Marie Curie Co-Fund Scheme. After successfully completing our ambitious CONEX Plus project related to sodium-ion batteries, we found ourselves with a wealth of knowledge and a desire to share our experiences. This led the idea of organizing a battery conference to disseminate insights, promote collaboration, and drive further innovation. Here's a story outlining the journey. Professor Alejandro and me, as a project lead, realized that the knowledge gained from our research could benefit not only our own organization, but the broader scientific communities and industries. The motivations behind the decision to organize a battery conference were clear. We had overcome challenges, implemented innovative solutions, and achieved outstanding results. We recognized that the insight gained during the project could be a broader implications for energy industry and beyond. We are passionate about advancing the field of battery technology. We believe that organizing a conference would provide a unique opportunity to share knowledge with researchers, engineers, professionals eager to stay at the forefront of energy storage advancements. Having collaborated closely with various experts during the project, we see conference as a chance to expand network and create new collaborations. We plan a platform where industry leaders, researchers, startups can come together and exchange ideas and explore potential partnerships. Recognizing the importance of educating next generation scientists and engineers, we aim to include educational sessions in the conference. We want to inspire students and young professionals to pursue careers in energy storage. And last, we are delighted to share iScience Self-Press Journal, Q1 journal with an impact factor of 5.8 is proud to associate with our conference ICAMES 2024. iScience Journal is currently accepting submissions for a special issue on advanced materials and energy storage. Professor Alejandro and me serve as guest editors in this special issue. Conference participants are invited to submit their original research articles, reviews, and studies. The success of this energy conference not only showcases our achievements of our project team, but also position UC3M as a hub for innovation and collaboration in ever-evolving field of energy storage. I now request Professor Alejandro, also the organizer of the conference, for the welcome speech. Thank you.
Well, I think I'm going to be very brief, just to say thank you for coming. Thank you just for the organizer, all the organizing committee, all the speakers, just for coming. Also the sponsor, mainly the CONES program, that I think is a very good initiative in this university. Also Bidham Pandit, that probably he's the main, the core of this Congress, because he was involved in all the organization. And also thanks to Christina, because I know that you have a very tight agenda, and then thank you very much. So I think it's enough just from my side, and then I pass the word just to Janif Sanchez, that he's going to present the VDCAT program.
I prefer to make some slide, a limited number of slides. Don't be afraid. In order to speak about this VDCAT project, that is a FET Open project. And okay, excuse me. No. Okay. So I will speak about that, and this VDCAT is part of this joint conference between battery material, preset battery material, and post-lithium battery. First, let me introduce me rapidly. I originate from Grenoble in France, where I was professor, until the University of Carlos III offered me a position of European Chair of Excellence during 6 months. And thereafter, I liked the life in Madrid and in this university, and I obtained a position in the Connecting Excellence program of the university. I think I was the first one to get the position. And then the title of my scientific topic was ACABA. Spanish is finished, and was Advanced Calcium Battery. Therefore, during some time, we spent time to develop a laboratory adapted to battery, and this offered me the opportunity to present this project as in the FET Open call, and to obtain the VDCAT, that is no more ACABA, but versatile ionomers for divalent calcium batteries. And so I will. So I have to present rapidly is a roughly a €3 million project that is coordinated by the university UC3M, and that has 6 work package and 8 partners. Indeed 9, because one of the partners moved from Germany to Italy. And so we have 2 groups in Germany, in Ulm. The leader was Stefano Passerini, and in Münster was Elie Paillard. In France, we have two places that were involved in, was ICGM in France. The structure is that you have associated university, people from university, professors from university, and pure researcher in CNRS, something similar to CSIC, but you have not something only CSIC, only CNRS, but mixed with the university. And in Montpellier and in Grenoble, my former laboratory, the LEPMI, and involving the Institut National Polytechnique de Grenoble. And a small company, Eras Labo, that is around Grenoble, in Saint-Nazaire-les-Ems, who was in charge in upscaling the synthesis of organic chemical, salt, for example, and also precursor of polymers. Spain was involved with CDTEC, that a lot of you know, in San Sebastian, led by Alberto Blasquez, and the university in Leganés. And in Italy, we have the group of Vito Di Noto, Professor Vito Di Noto in Padova, Uniped. And after the moving of Eli Paya from KIT to Polymer, Polymer is Politecnico of Milano. Okay? So, excuse me, that is, I'm not fluent with that. We did per chart and the project with the size war package, we pay a lot of attention also to the understanding of the conduction mechanism because it's a terra incognita, and in the case of, in particular of divalent, and in particular in the case of calcium. And also, you do not hear me? Okay, so excuse me.
No, for the online.
Okay, okay. And also war package 5 that was dedicated to cell fabrication and testing, particular push cell. The war package 2 was the core war package because it did with the synthesis of new electrolyte and use both as electrolyte and binder of the composite electrode. So organic chemistry, inorganic chemistry, electrochemistry, and also processing. That is. And the VDCAT addressed the 3 battery components, the negative electrode, the positive electrode, the electrolyte, and also the fuel cell. Okay. So indeed, it was what I call an hypothesis-driven project. I mean that the problem of electrolyte in the field of battery, when you go to, for example, to lithium battery, you have half a day dedicated to all kinds of electrolyte. Indeed, the problem of the scientific community is do not pay attention to the electrolyte, and indeed, the performances of battery strongly dependent on the electrolyte. So in that case, I was to say how to define a polymer electrolyte able to provide a calcium battery. So what we say, we went to have a single cation transport, as in ceramic. So, but also with high mechanical strength, as in ceramic. And in the same time, we went to add in the system polarity in order to perform the ion pair dissociation and to have solvating ability. And so to pay attention at what is more important than the conductivity, that is the conductance of the material, and the cationic conductance. Okay, this was the objective. Okay. So that is what we have to do, was to define calcium ionomers, to cross-link this calcium ionomer in calcium networked ionomer, and then with that to add nanocrystalline cellulose in order to have good mechanical performances, and to go to very thin film in order to play on that to get good conductance by square centimeter. At the same time, to develop, to propose this material to be used as the binders for the positive electrode, for example, sulphur, vanadium, calcium vanadate, and also phenothiazine as redox molecule, and also to have possibly, in alternative to calcium metal, some binders for the negative electrode, and to go to the final object. So I have finished. Thank you for your attention.
So that concludes the inaugural session of the conference. Thank you, Alejandro. Thank you, Christina. Thank you, Janif, for your talk. So now, without further delay, let's move on to the highlight of our opening session, our distinguished keynote speakers. These individuals are pioneers in their respective fields, and their insights are sure to inspire and set the tone of the entire conference. Before we go into the next segment of our conference, I would like to extend invitation Professor Janif to take the role of session chair for the upcoming session. Thank you.
Thank you, Bidan. So the first lecture is a keynote lecture by Dr. Buddha Deka-Roa and from University College London. And the title is Light Accelerated Fast Charging Batteries. You have 30 minutes.
Oh, thank you.
Including question.
Good morning, everyone. And I'm really thankful for the organizing committee for inviting me here. And I'm really glad to be here to present our research activities today. And first of all, actually, I'm not a pioneer, so I'm just the very new and young researcher. So I'm learning the things step by step. So yeah, I'll be talking about some kind of defined kind of energy storage systems today, which might be called light accelerated fast charging battery systems. So I'm an assistant professor at University College London. And yeah, so we have the very diverse research culture at UCL. So we have nearly 50,000 of students in total, and from different countries, over 150 countries, and also nearly 16,000 of staff. So my research group mostly focus on some kind of energy material and storage systems. So we not only deal about the energy materials, but also we used to talk about some kind of, different kind of battery structures. Especially, for example, if we talk about the IoT technologies, so some kind of IoT technologies, whatever batteries at the present we are using, for example, coin cell kind of BAS. So those kind of batteries might not be suitable if we talk about the specific on-chip energy storage system. So that direction is also actually my research group is focusing on that. So if we talk about, so we are focusing 4 different kind of research directions. So one is the light accelerated battery systems. So can we use the solar energy, for example, free energy to accelerate the battery systems in real life applications? And second thing, some kind of planar batteries, can we make some kind of very small, tiny batteries? For example, so if those batteries can be directly integrated with the other smart electronic systems so that we can just make it very small and on-chip, that means off-grid and off-grid devices. So, and also we also work a lot on the metal kind of anode-based metal, specifically focusing on some kind of zinc-ion battery systems. So zinc-ion battery systems, one of the exciting systems. So if we talk about the safety concern, the cost, so I believe the zinc-ion battery is one of the exciting systems. So we might be able to use it for mini-grid and off-grid scale, mini-scale energy storage system. And definitely, so when you talk about the batteries, always, some kind of in situ and ex situ monitoring plays a very important role to understand the such stress mechanisms, right? So I'll be mostly talking about today light accelerated battery systems, so apart from others. So as we already know that, the renewable energy systems, so we can get a free energy. So we just need to think about how we can utilize this kind of free energy to use in our day-to-day life. When you talk about the solar energy, one of the very exciting renewable energy systems in today's world. And when you talk about the solar energy, the concept is, we can just use solar cells and integrate with the batteries so that at the night we can just utilize it. So this kind of systems works very well when you talk about the large scale applications. Definitely, so this kind of high, solar conversion efficiency based solar cell with the smart battery systems is the best, for example, integrated systems to utilize the solar energy effectively. So, but some of the applications we don't care about the, very, large scale harvesting or some kind of very small energy storage systems. For example, if we want to use some kind of street light applications, some kind of, LED applications in the street light or some kind of detections. So in the things we don't need actually very high energy battery systems and also high efficiency based solar cells, right? So when you talk about utilization of solar energy, we can just integrate with the batteries, so based on our effective configurations. So sometimes what happens is if you talk about the area size, so it's sometimes external integrations just increase the packaging size and also some kind of add device complexity. Specifically, for example, so we need to optimize the output of the solar energy to the input of the batteries. So we need some kind of additional electronic components so that we can optimize the transportation, such transportations. And also when you add external integrations, we always talk about some kind of losses, some kind of ohmic transport losses. And sometimes in the solar cells, we have the very limited the OCV. So in general, for example, it's standard one volt, for example. Sometimes that 1 volt is not enough to research the one batteries, right? So specifically talk about the lithium and battery systems. So that is why, so we thought that can we realize some kind of different kind of systems, for example, to store the solar energy for the realization in the such storage process, right? So that was actually, this research is quite new. So when I was in the University of Cambridge as a postdoc, that time, so I thought that, can you think about some kind of different way? For example, some of the materials is semiconducting. Solar energy means we need the semiconducting material. And thereafter, we need to play with the source transfer materials to just, separate and for the realizations, for the transportations of electrical signal. So our idea was that, okay, let's talk about and think about that whether it works or not. Particularly, specifically, if we talk about if you use, let's say, the semiconducting material, battery material, and we expose the light, whether it works or not for the charging storage process. So definitely, first idea is that we can just take the solar harvesting materials, mix with the battery systems and the binder and conducting entity, this use as a hybrid material. But what we observe is that, for example, in the batteries material, we use the highly conducting binder, for example, the binder, and also we use some kind of carbon black. So those carbon blacks just absorb all the light. So the light, whatever you're exposing, that is not reaching to the material. So, and also because of, if you're using the, for example, a solar harvesting material separately, so again, the batteries material and the solar harvesting material interfaces plays a very important role. So the best way is that let's talk about some kind of single electrode materials, so which has the capacity to store the surges as well as optically active. So to make some kind of compact design, and we can see the light weight as well as accelerated mode. Right? So even though we're working on lithium and batteries, they will not like it, the V205 is the not best candidate materials for lithium and batteries, but we thought that, okay, let's start from some kind of material which can be used as a cathode for the lithium and batteries, but that is not an ideal candidate, right? So yeah, the band gap is 2.2 electron volt V205 we talk about, and then yeah, so that means 2.2 is also not ideal material for the most of the harvesting of the solar energy, but we can use some kind of visible light, right? So, and also it can be used as a cathode material for lithium and batteries, again, not ideal. And then, so we thought about that, okay, and the photo batteries, we always need to think about when we expose the light, we need to separate internally surges. Otherwise, it will just again recombine. It doesn't make any sense if you just shine the light and if you generate electron and holes, then if you are not providing any kind of source transport layer, it will just recombine it. So we will not get any kind of output from that system. So that is why we just try to use some kind of material, for example, reduce graphene oxide P3S3 with the V205 to realize it whether we can use solar energy for the realizations of the surging systems. Okay, so before applying for the direct batteries testing, so it's always important to do the that means electrical characterizations, we can say. So the best approach is very simple. So we can just use, to confirm whether this material is sensitive to light or not, we can just use, let's say, some kind of photodetector, we interdigit electrodes, and then broadcast the materials. This is the metal semiconductor metal-based photodetector, and expose the light. So that means when you add 1 volt. So we can expose the light, and we can see the increase in the current. That means this material has the sensitive to the light. Again, next step is that it needs to be internally separated electron and holes. So that is why, because we are going to use some kind of RGO, P3, S3, and V205. So that is why we make also some kind of layer-by-layer design to see whether it has the capability to separate the photons and holes and the electrons. So that is why, for example, so we make it these kind of devices, for example, layer-by-layer, and we measure that means IT responses. This is the time and the current responses. This is response time. So, and without any voltage, so no voltage across the device. And then we observed some kind of, enhancement in the current under the light. In the dark, there is no current. So that means that, okay, this combination has the potential to separate up to certain extent for the electron and holes. So then we applied for the lithium-ion batteries. This is the half cell, we can say. So against the lithium. So we observe significant enhancement in the CV area, for example, so without changing the positions specifically. And also, for example, if we talk about the CV area, if we talk about the peak current, so we can correlate the diffusion constant, right? Lithium and diffusion constant. So because this parameters is, for example, if you're using same kind of electrode materials, this is almost the constant value, right? Only the scan rate and the diffusion constant is the variable parameters. So from here, we can understand the diffusion coefficient of the lithium ion. So for example, here, if you talk about, so when you expose the light, the diffusion coefficient of lithium ion increases. So from here is also we can see that such transfer resistance drastically decreases, right? So that means that the photogenerated electron and holes plays an important role in the such transportation process in terms of the lithium ion. And also similar way we did some kind of CP that means galvanized discharge measurement. So CVD enhancement in the capacities we observed it, for example, under the light illumination that accelerate the charging process as well, because the same current, for example, same current density. So we can see the enhancement in the current. So here we didn't consider about the C rate because the metal is the loading of the metal is quite low. So it's not fair to consider the C rate, right? So C rate is considered we need some kind of sustained amount of the material. So that is why we always talk about the that is current density in terms of milliampere per gram. So here is also we observe significant enhancement in the capacities of the system. So we assume that the photogenerated holes help the driving the charging process by changing the oxygen state of the vanadium. So that means the intercalations of lithium ion. So that I will discuss actually further on. At the same time, some of the electrons, photoresident electrons, is transferred through the external circuit, and then the plating of lithium ion takes place on the anode side. So that is our assumptions. So similarly, and one more thing is that it's very important to understand whether if you're intercalating the lithium ion or deintercalating the lithium ion, submaterials properties should not change drastically, right? So that is why this is a different set of charge and discharge. So we did some kind of optical measurement as well, UVPs measurement to understand the band gap of the materials. So because of BM effect, so when you intercalate lithium ion into V2O5, so slight expansion in the band gap takes place. For example, this is not a very huge, still it's sensitive to the visible light. So because of the splitting, that means move of the Fermi level and a splitting of the band. So and then so we thought that shall we try to just discharge the battery to 2 volt and shine the light. So we observe increase in the OCV. Okay, so it's a huge debate actually in this measurement, right? So we thought that in the OCV there should not be transfer any electrons through the external circuit, right? In the OCV mode in the batteries. It's okay, as the definitions. But so otherwise, for example, how we'll able to measure, whether battery is charging or discharging, because we don't need to apply any kind of external current or external potentials, right? So that is why we just measure in the OCV mode. So we observe when you expose the light, increase in the OCV, and then discharge it, we can get a very good number of capacity. But in the dark case, if you just rest the cells, we don't get this kind of capacities. Okay. So similarly, for this is the light, and discharge it at the applications of some kind of current, and then we got the capacity. And when you're discharging it, if you expose the light, it's some kind of stable potential we observe. So this is nothing but a simultaneous photo charging process. Okay. So and then when we switch off the light again, normal discharge process takes place. So to understand whether any kind of electron transportation takes place or not at OCV, so what we did is that we measure, this is called conoamperometry measurements. So we can just put the OCV, for example, you can apply the OCV and then shine on light to the batteries, and we can see this some kind of generation of the current. So this current we always talk about measuring the external circuit. So That is why there is a possibility for the transportations of electrons through the external circuit. And that electrons, we are not talking about in the terms of the milliampere current, we are talking about in the terms of the microampere current, or maybe in the nanoampere range of current. Because in the photodetector or this kind of devices, we cannot expect the current in the order of the milliampere current. So there's a possibility, through the transportation of electrons through the external circuit. That is why we are observing the current, otherwise we should not observe it. So then, this is one of the collaborative work with the Cambridge University. So what we thought that, can we think about whether, light illuminations, that means the interactions of lithium ions or not. So this is one of the PhD students. He did a very exciting work. So this is, for example, this is nothing but operando optical microscopy in the reflections mode. So for example, this is the one single particle, single V2O5 particles, but we have the layer by layer of the RGO and P3S3. So when you intercalate the lithium ions, so the sticky, color changes. For example, this is the inserting the lithium ions, lithiation and the deletion process. When you deletion process, again, it comes back to similar kind of contrast. So from that, for example, this is the relative normalized intensity change. So for example, if you are, discharging, decreasing the change in intensity surging, so similar kind of, variations takes place. So this we can correlate with the surging process. For example, so here we observe is that, so in the dark mode, in the OCV, this is the OCV, for example, first, when you expose the light, so when you're discharging process in the V2O5, so we are integrating the lithium ion into the V2O5. So that is the phase of, LiX V2O5, right? So when you're charging means you're exposing the light, so we are expecting that lithium ions, deintegration process takes place. So that is why, for example, if you think about it, this is the contrast at the open circuit, no additional light. So we just measure it, something like that. We didn't observe any change in the OCB, okay? But when you expose the light at different time, for example, contrast changes takes place at the edges. So that means, for example, when you're exposing the light, so the surface, diffusions of the lithium takes place. So that means that is the possibility. So that means that lithium ion deintegration takes place from the surfaces. Okay. So that is actually we have concluded here, but still, it's very difficult to understand how the holes participate in the surging process. So at the moment, we are trying to understand actually, can we get some kind of techniques that we can detect how holes participate in the surface storage process. So that way also we are trying. And also sometimes we are, tuning the material, for example, through the hydrogenation process. For example, if we just annealing the samples in the hydrogen atmosphere, you can observe significant improvement in the, for example, in the optical activity as well as, electrochemical activity of the V2O5. So this is nothing but is just induce some kind of oxygen-related defects or some kind of oxygens containing hydrogen groups. So that really, that means create some kind of, what is called defect states in between the forbidden gap, and that just increases the conductivity of the materials and as well as the electrochemical activities. So similarly, we did some kind of hydrogenation process. So we observe, significant enhancement in the improvement in the surface stress capacity of the materials, as well as, and interestingly, because of improved the light activity. So when you expose the light, for example, if you compare this, both the light, for example, V2O5 and the hydrogen V2O5, so we can see the better, surface capacity. That is nothing but, more, that means optical activity of hydrogen and V2O5 as compared to piston V2O5. So yeah, something like that we expect that. So we can see the improvement in the capacities in terms of that. And also one of my colleagues, so he's from Imperial, so he tried to understand actually how does hydrogen process takes place and understand through simulation, DFT simulations. So for example, so in the V2O5 is the less texture, so the diffusions A part is very prominent, so that really suppress the diffusions of the other parts, C part or the B part. So he tried to simulate, for example, oxygen's O1 vacancies are from originally decrease the energy barrier. So if any kind of oxygen vacancies takes place, so that diffuse the energy barrier. And similarly, interestingly, OH one side, this is nothing but the OH one side. So here you can see the OH one side. So if you're increasing some kind of OH group, so that significantly reduces the diffusions of lithium ions. So that is why as a result, when you do the hydrogenation process, you can just improve the surface storage capacities. Okay. So also actually, I'm really a friend of these zinc and batteries. I really like to work on zinc and batteries. So yeah, because B2O5 is one of the very good material for the zinc and batteries. So we also trying to understand and apply the zinc B2O5 or VO2 different phase materials for the zinc and batteries. So interestingly, so this is the zinc and batteries we can use aqueous electrolytes. So we don't need the sophisticated, glove box systems. No need to worry about that. So you can just assemble anywhere, wherever you want. Okay. So yeah, so reserve is also the 300 times greater than that of the lithium. So that is one of the very important so in our society. And also zinc metal can be used as an anode metal, but there is also definitely when you talk about the metal, there is always some kind of dendrite formations takes place, right? So that we also are trying to suppress the dendrite. And if you talk about the cost-wise, zinc is stay here. So if you talk about the lithium and also capacity, that means galvanic capacity is quite high, 5,854, right? So there is no any doubt. So this is until 2020. So just jumping the publications these days about the zinc and batteries. So if you see any kind of publications, everywhere you can see zinc and batteries and suppression of the dendrite growth based on the zinc and batteries. So yeah, so here you can see some of the exciting news. They're trying to directly commercialize some kind of zinc and batteries for the mini grid scale energy storage systems, specifically when you talk about the very safety as well as the cost effectiveness systems. So yeah, so VO2 is one of the really good candidate because I work on VO2 during my postdocs. I really like this candidate because it's a very highly stable capacity we can get it based on that. And interestingly, this is tunnel like FEMOX structure. It's a very big FEMOX structures and it's just diffuse the zinc ions through that. So when you talk about the aqueous battery systems, for example, hydrated of zinc ion takes place. So 6 water molecules surrounded by 1 zinc ions. 1 zinc ion surrounded by 6 water molecules. So that is the very large. So we need some kind of energy to remove it, or that means that means what is called remove the water molecule from the zinc ion. So that is where some kind of, if we have the very big tunnel-like structure, so the zinc ions can directly integrate with the water molecule, okay, without losing the capacity. So it has a very good theoretical capacity, around 46 milliamps hour per gram, and also the band gap is 2.3 electron volt. So then we try, why we cannot see this kind of as a photo accelerated zinc and batteries. So again, based on the Fermi level, so we don't need to use the P.PS or something like that, so we can just consider the RGO. So this kind of 3D porous electrodes, and also this kind of batteries. Again, so we did the electrical measurement. We can see the current increase and the decrease, and layer by layer to see whether we can observe any kind of generation of the current across this material and has the capability to separate it. So again, I expect that based on the optical properties, we have seen the improvement in the capacities. But here we observe 2 different things. One is we observe at the low current density, the slow rate, so we observe less capacity improvement. But when you talk about the high current, 5,000 milliamps hour per gram, which is a very high current, still we observe the capacity 200 milliamps hour per gram. So yeah, so here you can see that. So and also you can see the improvement in source transfer resistance. So to understand why we are observing this kind of 2 different kind of characteristics, that means why at the high rate we are observing more improvement in the capacities under the light illuminations as compared to the low specific current. So yeah, so for example, based on the peak current, so we can consider peak current. If you talk about the aqueous-based system, there's 2 things takes place in the source storage process. There's either one is completely battery kind of behavior, one is some kind of capacitive kind of behavior. It might be the electrical double layer capacitance, or it might be the pseudo capacitance. When you talk about the nanomaterials, it's a really important factor, nanomaterials. So that is why when you talk about this peak current, you can just correlate with I capacitive contribution, diffusion consumption. So this is nothing but the FV to the power. B is the standard, is the B. So B is the important parameters that define whether it is capacitive contribution or diffusion contribution, for examples. So if B approaches to 1, this is nothing but completely capacitive contribution. That means it's a very fast charging process. So you can charge the batteries at a very high rate. So when you talk about a B equal to 0.5, that is nothing but completely battery kind of behavior, diffusion, slow diffusion process behavior. There is some kind of bulk kind of phenomena. So for example, here you see that, so this material, if you go back, so it's still at a very high current So that means, let's say, 10 ampere per gram. So you're still observing nearly 60 milliamps per gram capacity. So this metal has the high rate capability. Okay. So that is why in the peak current B, peak 1 for example, it is a peak 1, peak 2, peak 3, peak 4. So this is a process to B. This is nothing but this metal has the high capability. That means high rate capability because dominated by capacitive contribution process. And similarly, this is more than 0.5. So this is the 0.5. And then when you expose the light, we drastically observe further increase in the capacitive contribution, for example, Ca. So that is why at the high rate, we are observing much better, such storage process. So similarly, again, we can just correlate the diffusion constant. For example, two different ranges, you can consider it, for example. So this is the low scan rate. Low scan rate, the diffusion constant enhancement is slightly lower. Okay. So, but when you talk about the high scan rate means you are charging, discharging the batteries at a very high rate. So that is why diffusion constant is the very high. So that is why, as a result, we are observing more, improvement in the capacities when you expose the light at a high specific current. Okay. To further understand, so that is, this phenomena is completely one position. For example, we are just talking about only the peak positions. If you see this CV graph, this is broadening CV graph. This is not completely the battery kind of very sharp, surging this, that means peak. Here is actually there's some kind of, capacitive contribution kind of behavior. So that is why, when you conclude it, we need to consider the current each of the voltage responses. We need to consider whether capacitive contribution dominant or the diffusion contribution dominant overall in the capacities. So that is why, so these equations, for example, we can apply every, that means current of the CV, for example, at different, scan rate, that means in the CV. So that is why in the whole CV, we can just consider capacitive contribution, diffusion constant. That is nothing but we already know. One is the capacitive, one is the diffusion constant. So this is the K1, V is the capacitive, this is the diffusion control because VB to the power B, right, is the half. So from these equations, we can actually consider how much percentage of the capacitive contribution dominates overall charge storage process. This is the overall process. So then we can just, because this is the two dependent variables, so we need to make some kind of independent variable. This is that line equations. So you can just divide these equations, that means V to the power half, so we can rearrange these equations. So this is nothing but state line equations. Y equal to mx plus c, for example, right? So this is the constant, and this is the. So if we plotted this graph against, if we can get a K1 value, we can directly correlate the capacitive contribution process. So that way, we calculated both is, for example, in the dark CV, this is the 1 millivolt per second. We observe 89% capacitive contribution even in the dark process.
3 minutes.
Oh, sorry, yeah. So, but when we expose the light, so we have observed 99% the capacitive contribution process. Okay. So again, so this is the highly stability. For example, if you can see that, so 90% capacity retentions over the 1,000 cycles. Even though this is not the ideal electrode metal, no such kind of binder, no such kind of conducting additive, super P. Okay. So, and as expected, there is no such kind of change in the optical band gap. So further, so when you mix about some kind of these kind of things in the solar cell or solar, what happens is that a lot of electrons just trap at the interfaces. Can we realize some kind of well-designed structure? So as a result, we just discuss some kind of, because MOS2 is also one of the layer structure materials. So we just grew MOS2 on the top of the, so first we coated the zinc oxide. Zinc oxide is very good, some materials. And then we have coated the MOS2. So similar way also we have performed, we have observed the charging behavior of this kind of photo batteries. So some of our, that means contributions find the media attentions. So yeah, so I would like to acknowledge my exciting research group and also my exciting collaborators from different university and the funding agency. Thank you so much. So I apologize if I take more time. And now I'm happy to take the question.
Time only for 1 or 2 questions.
So thank you very much for your
I think I can take this microphone.
Okay, so thank you very much for your nice talk. I was wondering about the contributions, the capacitive and the Faraday contributions in your zinc aqueous ion batteries. Have you been able to separate what is the pseudo-capacitive and capacitive contribution? Is it purely capacitive or pseudo-capacitive?
Oh, it's difficult. So there is no such kind of procedure to separate the whether pseudo-capacitive or electric level capacitance. So the capacitive contribution both contain, it might be the electric level capacitance or the pseudo-capacitance. So because both are B values behave like 1, so there is no such kind of way to separate them. Yeah.
Okay. Thank you.
Thank you so much.
Okay. So it's a nice presentation. Just I have one question. That you are working on zinc ion batteries. I know you, and aqueous zinc ion batteries as well.
Yeah.
So is there any probability that it will gonna replace the commercial lithium and sodiums in near future? Because it is an alternative battery, aqueous zinc ion, I know, but just a curiosity.
Okay. So in our scientific community, to just highlight with some of the things sometimes we just blindly used to say. For example, lithium will be replaced by sodium ion or some other system. So lithium will be always there in the lithium because it has the own potential. Sodium has own potential and zinc has own potential. It depends on what kind of application you're talking about. Definitely, if you talk about the energy density in terms of the aerial energy density or polymeric energy density, lithium will be the best candidate in the world. So if you talk about the safety concern and safety concern plus cost effectiveness, so I believe that in the mini grid scale energy storage system, specifically, for example, if you want to store the solar energy at home, we don't care about if the battery size is slightly bigger, but we care about the safety concern, right, and the cost effectiveness. So for those applications, definitely zinc will be the best candidate, I believe. And also, if you see some kind of other countries, for Canada and US, they're playing the really important roles in the zinc and batteries to commercialize, specifically for the mini grid scale and off-grid scale energy storage system applications. Yeah.
Is there any industries available on zinc ion still now?
Yeah. So this is one of the salient energies. So they are really playing an important role in the that means the Canada surging in the future challenging in the zinc. So this company is playing a very important role in the zinc and battery system.
Thank you so much. Yeah.
Thank you.
Hello.
Hello.
Thank you for presentation. I have just one question. In a potential scale-up of this technology, how we can get the light?
Okay, so this is just proof of concept we are trying, and this research started from mostly 2018. So there's a lot of challenges still remains. First of all, the materials, the loading of the active metal is very limited at the moment, and we need some kind of, if you really want to, utilize or effective transportation separation of photosurges, we really need to think about the solar cell technology, for example, layer by layer coating of the materials. Yeah. So that way, I think if you think about that, definitely it might find some applications, but it's not at large scale applications. This will be some kind of small scale applications. For example, in the street light, for example, if you want to daytime store the energy and the light, and the night time it will just that means provided the power. Yeah.
Okay.
So thank you again.
Thank you very much, and I really apologize if I crossed the time.
Next presentation will be done by Dr. Marta Arro Raymond from the Universidad de Zaragoza. And we'll deal with lithium-ion-based solar electrochemical energy storage, a sustainable power solution.
It's okay. Okay, thank you. Okay, thank you for the invitation. My name is Marta Aro. I'm Ramón y Cajal researcher in the Instituto de Nanociencia y Materiales de Aragón, and my talk
is very close to the previous one, Professor Buda, is lithium-ion-based solar electrochemical energy storage, a sustainable power solution. Okay, according to the energy technology perspective, published in 2023, to reach the net zero emissions by 2050, the scenario by 2030 is going to be that the electrical vehicles are going to increase in 6 times, the energy demand is going to increase in 25%, and from this energy, over 60% should come from renewables energy sources. Particularly are increasing a lot the wind energy and the solar energy. And the forecast, when it was provided in 2006 and in 2021, this forecast of wind energy increases by 4 times. But if we look the solar energy, this increases 30 times. Okay, I think it's good news that we are going to have a lot of wind and solar energy. But it can happen one thing, that is the cannibalism effect. What is this cannibalism effect? If we have a solar farm with plenty of solar cells, it can happen that the energy is intermittent, that in one moment we have so much energy that the price of this energy is so low that it's not economically sustainable. We need to store this energy. How we can store electrochemically? We can store in batteries, and here we have the solar cell, and we charge the battery, and when we are in dark, we can have the energy back. And we can synthesize solar fuels. We can have also a solar cell and 2 electrolyzers, and split the water to have hydrogen as energy vector. But since the 70s, is also already fabricated the technology of photoelectrochemical cells, in which we have our light harvester, we separated the chargers, and we can synthesize directly the solar fuel, as the hydrogen in this example. As my background is in the production of solar cells, in hydrogen solar fuel, and also I was working in batteries, I was wondering, as my previous the Professor Buda, is it possible to fabricate something similar, like the photoelectrochemical cell, not for producing hydrogen, but for charging directly the battery? And I was working in 2 projects that I think that provides clue the types that is it possible. This works. In the first one, I was working as postdoc in the University Jaume I with Juan Bisquert, and we wanted to do a photoelectrochemical cell for producing hydrogen using organic semiconductor. The typical organic solar cell of bulk heterojunction, and when we have the photovoltaic cell, we obtain milliamps, okay? But when we went to a photoelectrochemical cell, with water, only microamps. And where are our photocurrent? Where is? Because the semiconductor produces the photochargers. If we are not able to obtain photocurrent, it's because we are not able to extract quantitatively these photochargers. Then we need to look at the selective layers. I think that is the clue of everything. Then here we look again the photovoltaic cell and our bulk heterojunction. We have zinc oxide electron selective layer and trioxide molybdenum as hole selective layer. Then the photochargers can be separated and used. Okay, then we did the same in the photoelectrochemical cell. We maintain the electron selective layer, the zinc oxide, and we remove the molybdenum oxide, and we put the electrolyte, in this case it was acetonitril, with a hole scavenger, that it was the redox pair ferrozine. Then when we did the typical current voltage diagram, we obtained with the photovoltaic cell this red line, and when we did in our photoelectrochemical cell, we obtained this blue line. Okay, the photovoltage is the same, but the photocurrent decreased in half. Then Antonio Guerrero, that it was the one that was doing the solar cells, realized that here we have the electrode is a silver mirror and reflects the light. We don't have that in our photoelectrochemical cell. Then we did a semi-transparent electrode of silver, and we obtained the dashed red line that, okay, we reproduce our photoelectrochemical cell. But not only this. In a step further, if we play with the selective layer and the redox pair, we can send holes to the electrolyte like this, that it was with the zinc oxide and the ferrocene. But if we do the opposite, we have a whole selective layer like P.PSS, and we put a redox pair that's capable to extract the electrons, like benzoquinone. We can inject to the solution electrons. Okay, but the objective in our project, it was to do water splitting. Then we adapt this whole selective layer, the P.PSS, with a cross-linking layer, and we did an electron selective layer that it was titanium doped, and we put as catalyst platinum, and in this case, the layer, it was thick enough to protect the bulk heterojunction, the organic, because it's sensitive to water. We lose some photocurrent, but we are close to 1 milliamps, but it was stable at least for 3 hours. When we measure the hydrogen, here is our photocurrent, and the dots are the hydrogen measured. We estimated that we have 100% of Faraday efficiency of hydrogen production. In the second work, that it was led by Sixto Jiménez, also in the University Jaume I, we have another photoanode. In this case, it was vanadate of bismuth, and we put nanoparticles of lead sulfide. And when we did the cyclic voltagrams under light illumination, we observed that in first we have this flat voltagram that is normal, and then when we were cycling, every time it was more capacitive. That is more hysteresis, is more capacitive. Then by XPS, we observed that what happens is the sulfide, it was disappearing, and it was appearing more oxide. Then the lead sulfide, it was changing to lead oxide. Then we proposed this system that it was like we call photocapacitor, and the vanadate bismuth acts as light harvester, and when we are under light illumination, we have the photoholes stored in these lead oxide particles, and the cyclic voltagram, when it's dark, is flat, and when it's illuminated, is capacitive, that is almost a square. And also the border representation, we observe that when it's dark, we only have one plateau that is related with the electrochemical double layer capacitance, but when it's illuminated, we have a second increase that is related with a chemical capacitance. Also, when we stop the light, it was in dark, we close the system, and we are able to obtain the energy back, estimated in 0.35 microwatts hour centimeter square. That is not too much, but enough for a sensor to send a signal. Okay, with these results, and looking the previous cell that we have a light harvester and a capacitive layer, we propose this system, that our light harvester is cuprous oxide, and the storage material, it was the titanium oxide, for storing the lithium ions. Then the cuprous oxide, it was obtained by electrodeposition. We obtain prismatic crystals, and we corroborate by XPS that the state of oxidation of the cuprous, it was 1. That is the one that we are interested for these electrical properties that were estimated by ultraviolet beam spectroscopy, the band gap, and the ultraviolet photoelectron spectroscopy, the valence band, and the Fermi level. Then we can calculate our energy levels. On the other hand, we wanted to have the storage material, that it was the titanium oxide, that it was obtained by hydrolysis of the isopropoxide of the titanium. We did a thermal treatment at 400 degrees, and by XRD, we corroborated that we have an ATASA with very small size, 11 nanometers. Here in this plot, I represent the LED emission, the spectrum emission of our white LED, and here the absorption of our two materials. The cuprous oxide absorbs in the visible region, and then most of our ultraviolet, of our light, of our LED, and the titanium oxide in the ultraviolet that then doesn't absorb. Then only the light harvester is the cuprous oxide. On the other hand, we wanted that only the titanium oxide was capable to intercalate the intercalated lithiums. Then we study the cyclovoltagram in the electrochemical window that we were interested in, between 1.6 and 2.6 volts against lithium, and copper doesn't do anything, it's flat, and the lithium shows the two typical peaks of intercalation at 1.7 volts and the intercalation at 2 volts. We did the half cell battery and estimated the capacity, and we observed that we can have very fast response, up to 10 C. That is normal because we have very small nanoparticles. We have only 11 nanometers. Then once that we have our photoelectrode, we adapt our coin cell, the typical SCR2032. We hold the spacer and the upper case and join together with indium ring. When we clamp the battery, this indium melts and seals the battery, and the lithium is protected. As I came from water splitting, the first study that I did, it was in dark and light, the linear sweep voltammetry. When we have light, it was in yellow, fringes is illuminated. This is from open circuit up to 1.6. In dark is in dark, without light, and in gray is in dark, and in yellow is under light illumination. We observed that we have important photocurrent, and also as I came from water splitting, I proposed this scheme that, okay, I have my semiconductor, and I see the host as a redox pair. And the system is working because I illuminate, the photoelectrons go from the valence bands to the conduction band and can produce the lithiation process, and the host the dilithiation process. But when we did the cyclivoltagrams at different energy powers, the behavior of the anodic peak is what it was expected. We have from dark up to 1 sun, that is 100 milliwatts centimeter square, the voltage shift and the intensity increase, but in the cathodic peak, we don't have any response until we don't go up to above 50 milliwatts centimeter square. And then this model is not good. And I was reading a lot of literature, and I like a lot this work because it was electrochemistry of semiconductors. And okay, we don't have a redox pair as I have in the first example. I have a semiconductor. Then the semiconductor has its own conduction band, Fermi level and valence bands, and doesn't match with the electrochemical redox potential because the lithium goes to determined planes inside the semiconductor, and also we have kinetic limitations related to the Nernst equation. Then we propose this, that we have to consider the properties of the titanium oxide that is in contact with the light harvester, with its own conduction band and Fermi level, and also the redox process that is in contact with the electrolyte. Then, okay, the photoholes can produce the dilithiation, but the electrons, we need a threshold at least, because most of the electrons go to the conduction band of this titanium oxide, and these electrons have not energy enough to produce the lithiation process. Once that we understand the system, we prepare our battery, that it was a half cell configuration, and in that we have stabilized the open circuit voltage. Then we illuminate it. We observe that the open circuit voltage increases up to 2.6 volts. Then we switch off the light and close. and we discharge the battery. We corroborate that it was not degradation of the cuprous oxide in that moment, because it's quite tricky if you work in chemistry, and we estimated the discharge capacity, that it was the best, it was a third cycle with almost 180 milliamps hour centimeter per gram in C.1C rate. And the efficiency, it was up to 0.29. Okay, with this I can go to the conclusion. I hope that after these two talks, we're convinced that photorechargeable batteries is an incipient technology, and we propose a working mechanism model to fuse the solar cell and the battery, but there is plenty of room of improvement. Okay, here we have only half cell battery. We need to move to a full cell battery to do properly the charge, reduce the kinetic limitations to get closer the conduction band and the redox electrochemical potential. And okay, this was done with organic electrolyte that is not the best to be illuminated. And we need to move to hybrid or solid electrolyte. I have many people to acknowledge, but here in this work, I want to acknowledge Emilio Juarez Perez, that is my colleague that works in solar cells, and our PhD student Isabel Ciria, and all the economic support. Okay, thank you.
So,
Thank you very much. It was a very nice talk. So when you expose the different kind of intensity of solar light, right? We have observed shift in the peak positions. Is that because of the heat generations into the cell, or some other things?
The peak shift?
Yeah.
With the power?
Yeah. Is it heat generations? What kind of solar sources you have used it?
It was a white LED. The spectrum that I showed, it was the emission.
Okay.
It was above 400. Then it was the power. We think that the shift is because we are generating more photoholes. And then it was
okay, yeah.
moving.
So at the moment, actually, we are mostly using LED-based solar simulators. So that actually doesn't generate any kind of heat. So as compared to the broadening, those things. Yeah.
Okay, no. It was a white LED.
Yeah. So, and second question is that, so thermodynamically, for example, if you talk about lithium-ion batteries, right? So when you expose the light in the lithium-ion cell, so it should not get the voltage OCV more than, let's say, the photogenered voltage less than more than 2 volt in general, right? So we are also really struggling to understand actually why we are observing the voltage more than thermodynamic limitations. If you see the band gap is splitting, those kind of things. Do you have any comment on that?
Sorry, I lost the question.
Okay.
Sorry.
So in the lithium-ion battery systems, so for example, in the solar cell, let's say solar cell, so we observe OCV around 1 volt or maximum 1.5 volt. So when you talk about lithium-ion batteries, so even to that, whatever photon we are exposing, that doesn't have much energy to, leave the voltage more than 2.5 volt in the lithium-ion batteries. Actually, we are also really struggling to understand. So do you have any comment on that?
Yes, I think that is the point of the reference, because if you have the cell, it's just where you have the semiconductor conduction band and the valence band. It's because I came from the water splitting, then it's related with that, with the reference that we are using. I know that the solar cell is not more than 1 volt, but in this case it's because we are against the lithium. Yeah. Then the titanium is that. If not, we are not able.
Thank you. So next talk will be done by Dr. Sergio Carrasco from EMDA Energy. and deal with metal organic frameworks for energy application.
So, okay, first of all, thank you very much for the invitation. I'm glad to be here talking about a little bit about these materials that are very special, metal organic frameworks. I have decided to choose these particular two applications that are related to hydrogen technology, that are the proton exchange membrane fuel cells, and also the generation of green hydrogen through the photocatalytic overall water splitting. So we come from India Energy Institute. We belong to the Advanced Porous Material Unit, and we are interested in such kind of materials. These are very interesting synthetic hybrid polymers that are composed of metal ions and clusters that are linked together to form such kind of final materials that are called metal organic frameworks. We can obtain them in different morphologies, different sizes, and the most relevant features of such materials, the first of all, as UPAC definition, they are potentially porous materials. But also, they possess a tunable surface area and pore volume. They are typically crystalline, so we can characterize them according to the typical techniques of crystal characterization. They are low cost. This is going to depend, of course, on the metal source that we are using for them. And they are quite versatile. Versatile not only in terms of different combinations between metals and organic linkers, but also according to different modifications that we can perform over the final structure. So these materials have been classically used in different areas. Today I'm going to focus in energy, but this is quite diffuse between energy, catalysis, so we still don't know where we are. But just to give you an overview about the use of more materials in energy applications, they have been used during the last 20 years, and there have been a lot of quite milestones, including something related to gas storage, including methane, CO2, hydrogen. They have been also used in storage devices such as lithium batteries, lithium sulphur batteries, also used as capacitors. And we are glad that we have also contributed to this timeline with this last work here that is a material that has been used for the production of hydrogen in a record manner never described before. So in general, we can distribute in storage and conversion. However, the problem with these materials is that sometimes they show limited accessibility to binding sites that are the metals. Sometimes the reagents found difficult ways to diffuse to these active centers. And sometimes the structural stability is compromised under certain working conditions. For these things, we typically use different strategies consisting on defect engineering to modify these materials and to make these MOFs apt for different energy applications. Such strategies are very similar to those that we can find for pure inorganic crystals, and they are oriented, as I told you before, to improve the accessibility, the diffusion of reagents, and also to improve the stability. In summary, it's just a matter of improved activity and stability. With that, I would like to start just with the first application, that is the use of MOFs for proton exchange membrane fuel cells. As we all know, we are heading towards the hydrogen economy. And this hydrogen economy is based on three different bases that consist of hydrogen generation, hydrogen storage, and hydrogen utilization in the form of electric currents, heat in different areas, such as transportation, foods, industry. The problem, unfortunately, is that we are still a carbon-based society. So some of this hydrogen still comes from other sources rather than renewables. But in the context, the good point is that we can develop different devices such as these proton exchange membrane fuel cells that are very interesting in the sense that they are very suitable for portable applications. And compared to other conventional batteries, they are lighter because the proton exchange membrane in the center, typically it's a polymer, quite light. In general, they take lower times to be loaded, and they are less toxic than other devices. So we will focus on the characteristics that should be accomplished for this proton exchange membrane. The typical material commercially available is Nafion. Take into consideration this conductivity number, 10 to the minus 2, because it's our reference. From this, we have to find a material that accomplishes several rules, such as, for example, thermal and mechanical stability. However, the problem of Nafion is that sometimes under different humidity or water conditions, we show degradation. So the requirements to substitute this Nafion by other kind of materials, particularly based on MOFs, is that this MOF should be ionic conductor, but electronic insulator to avoid passing through the electrons there. Should be stable at different temperatures and a wide range of relative humidities, and should show labile protons within the structure. For this, we have oriented the strategies of the synthesis of this material using this kind of organic linkers that are based on phosphonate or phosphonic acid, because they present this kind of labile protons that can remain in the structure. And also we are using typically metal 3 or metal 4 cations, because they typically lead to strong coordination bonds, so the material is typically higher, so a higher stability in these cases. So this is the first example that I want to talk about. It's a bismuth pyrene phosphonate. We obtained this material the last year, and it's quite interesting because we have very strong coordination. It has these labile protons, 2 labile protons per each unit cell. And the interesting part of this material is that quite chemically stable under different conditions, different organic solvents, and with a pH up to 10. So we can work in different conditions. And also, it's quite thermally stable up to 400 degrees. The conductivity measurements were conducted here at University Carlos III with the help of Alejandro and Teresa. And we obtained different pellets. We pelletized our MOFs in a simple infrared press that we typically use to fabricate our pills. And we covered with gold to make all these measurements. They have observed that the conductivity was of the same order of magnitude as that of Nafion, and quite recyclable in the end. We observed also that the material was chemically and structurally stable after all these cycles, and in the end, we imbibed this MOF in a typically conductive polymer, this sulfonated polysulfone, and observed that in the end, the conductivity remains constant. So this is one of the materials that we are still using for the fabrication of such devices. In that sense, we have been also working with such as triazine phosphonic organic linkers, and we were expecting that the conductivity levels were quite similar to those observed for the previous MOF. However, surprise came when we observed a very low proton conductivity, and also after only one cycle, the proton conductivity decreased for 1 order of magnitude. So this is bad, and here is where it comes the defect technology. So starting with the raw material, we proposed different strategies. One of these was inserting within the structure a proton carrier that could help to improve this proton conductivity, and also performing different exchanges, changing these labile protons by other cations. So starting with the first approach, what we did with the previous structure is to include, by a simple wet impregnation, lysine. Lysine is a natural amino acid that provides some proton species to the structure, and what we observe here is that it is true that at the very beginning we decrease 1 order of magnitude the reference, but here the proton conductivity practically remains constant when we include this lysine. This lysine was protecting the structure from the activity or the whole environment, and also we demonstrated its chemical stability after such a cycle. However, it is true that these values are not the best for the proton conductivity, so we move for the other strategy. We tried this ionic exchange using alkaline cations. The good point here is that the material was quite stable using alkaline hydroxide, that is a very harsh condition media because pH can reach up to 14, and the material remains stable. Here, after checking by different techniques, particularly based on ICP, what we observed is that out of the 8 labile protons, we substitute them with 5 of these cations. We observed that the highest values were achieved for potassium, and potassium now reaches values similar to Nafion. And as we can see, if we decrease, so go for sodium and lithium, these conductivity values were lower. We observed also that the material was partially recyclable for 3 cycles, and after all, we embedded again this MOF with sulfonated polysulfone to develop our devices that work more or less well and keeping practically the same values for proton conductivity. Now I move for the second part to, if we have been talking about storage, now we're going to talk about hydrogen generation. And this green hydrogen generation, it's quite interesting because we know that hydrogen is a very interesting energetic vector. So it's partially clean. We can obtain them in a different variety of sources because it comes from water, actually. And it has a very, very nice energetic yield per mass. 1 kilogram of hydrogen is able to produce 3 times the energy that is able to produce 1 kilogram of gasoline when burning. However, there are still some limitations related to the use of hydrogen. Of course, it's because hydrogen is a gas, and the gas should be stored somehow. So, still today, this is a little bit old-fashioned, but it can be extended to the days of today. More than 94–95% of the hydrogen today is the so-called gray, brown hydrogen. There is a problem because if we want green hydrogen, only 4% is, we can call it green. And green, for this 4%, 99% comes from electrolysis of water. Only 1–2% of the works published in the literature correspond to photocatalytic water splitting. That emphasizes on the fact that we don't have very nice materials to perform such investigation, and this is where we are dealing with. We are preparing different MOFs as photocatalysts for this reaction that should accomplish different requirements. It should mimic the photocatalytic systems, the photocatalysis, absorbing efficiently the solar radiation. They should be stable in all these senses, and they have to be built of different active species, both metal cation and organic linker. This is the work that we reported a few years ago that is called IEF11. This stands for India Energy Frameworks. And this is quite very interesting. I'm not going to enter in details about the structure, but keep in mind that here it was found a coordination of titanium that was not very typical in such kind of materials. And this is kind of a trigonal bipyramid. This trigonal bipyramid in MOFs implies the stabilization of different species rather than titanium-4. It stabilizes titanium-3 that is essential for the photocatalytic process. We evaluated the porosity of the polymer. It was quite good. Also, the thermal stability up to 300 degrees. And also, it was stable in different organic media at different pH values. Actually, it was also stable even if we put at pH 12. So, but the most interesting part of this polymer is the photoelectrochemical properties, of course. And we have observed by using some spectroscopical techniques, such as diffuse reflectance UV spectroscopy combined with XPS, that the band gap value of such material totally matched the maximum of irradiance of solar light. That was one of the advantages, so we thought at that point, okay, let's start to use this for the generation of green hydrogen, and we obtained a very recyclable materials. It was stable up to 10 cycles, not only in terms of catalytic activity, but also in terms of stability. So here you have different values to compare with. In the overall water splitting, this was the material providing the highest and the largest hydrogen value production, compared even though to other MOFs with incorporating different co-catalysts. And interestingly, we compared these values with those provided by titanium oxide, that the reference material for such kind of applications. We observe that we are obtaining similar values, and also not only in overall water splitting, also for hydrogen evolution reaction, when we add intermediate sacrificial agent, we are surpassing somehow the hydrogen production yield by titanium oxide. Of course, we are not competitive when we include other co-catalysts in the media. For example, we obtain such values, including platinum nanoparticles. However, with titanium oxide, we reach very much higher values. But consider here that titanium oxide is a very mature technology, old technology, And here we are dealing with materials that have been recently synthesized. So this is the motivation for our current project that is still ongoing now. Here, our collaborators have observed that depending on the changes that we can modify on this IF11, just by doping this material with different cations different than titanium or other organic linkers, we can improve the photocatalytic activity of such material. Briefly, this overall water splitting occurs because sun is irradiating our materials. We create holes in the valence band, and with this simulated density of state, we observe that this valence band corresponds to oxygens, the conduction band here. The contribution comes from titanium, and that means that we can deal with two different elements here in order to improve the material. Our collaborators have observed that just by replacing the ligand, this squaric acid, by this squaratetiol, just by including different sulfur atoms in the structure, we observe two effects. We increase the number of density of states, so we increase the chances of absorption and then transition, and also the band gap values were slightly decreased. So they shift a little bit to the red, but they broke the band of absorption. So we are improving the photocatalytic relevance of such material. It also happened with this squaramide. So this is what we are doing right now. We are doping our structure in a different manners. Our PhD student is modifying the material. We are able to obtain pure materials just by using hafnium, zirconium, vanadium. Unfortunately, those based on hafnium and zirconium, the band gap values are in the ultraviolet, so they are not very useful for our purpose. But it is interesting, this structure based on vanadium that is similar to titanium. However, unfortunately, the vanadium form of this MOF is not stable in water. It destroys easily. So what we are doing right now is a progressive doping of the structure, and we observe that we can modify, including different percentages of vanadium within the structure. So we have seen that only including 10% of vanadium in the original titanium structure, we are able to obtain the similar band gap value as that described for vanadium. And now the material is stable and we can use it. We are now also working on the other part, the part of the organic ligand, and we have observed that this material allows a modification of up to 30% without structural damage. After these values, all material is totally destroyed, and we are obtaining different compact phases. I'd like to conclude. I hope that things are more or less clear, and I have transmitted you the interest of such metal-organic frameworks. In the case of the hydrogen supply, we can provide new different materials based on titanium that are based in both optical electroactive linkers and metal cations with outstanding thermal and chemical stabilities, excellent optical properties in the visible range. And we have achieved record values in overall water splitting for hydrogen generation. In the case of the hydrogen demand, this proton exchange membrane fuel cells, we have obtained a very interesting material based on bismuth, a pyrene phosphonate, with strong coordination with the phosphonic acid moieties, with high electronic density because the cores are based on pyrene or triazine, and they show liable protons responsible for this outstanding proton conduction. But also we have applied some kind of defect engineering strategies. In the case of hydrogen generation, we can modify the raw structure by a simple doping with different metal cations or different organic ligands. And in the case of the hydrogen demand, in the case of the proton exchange fuel cells, we can go for different strategies consisting on including species that provide more protons to the structure or shifting protons by other alkali cations. With that, I conclude. I would like to acknowledge all the people involved in both projects, and of course all the people involved in our unit, or students, postdocs. And here is our leader of the unit, Patricia Orcajada, that couldn't attend today, but she is the leader of this team and the responsible for the success of all of this project. And of course, thank you very much for your kind attention.
Chairman privilege, I will ask
of
you
course.
just a question. Regarding your morphs that you use together with Nathan, I think is a composite membrane. Is that?
Yeah, it is. It is.
And of course, if you put a phosphonate group on the aryl groups, this is better for the for the chemical stability. But as compared to sulfonic aryl sulfonic groups, the dissociation is lower, and conductivity contribution perhaps also.
Yeah, it is true that depending on the MOF material that we are using, sometimes we observe a decrease in the overall proton conductivity. Actually, in the end, the mechanism behind all of this is a contribution of different things, not only probably in the surface regarding the sulfonate group, but also because some of these materials have different amount of water molecules within the structure. So depending on that, and we think, and Alejandro saw that it was the most relevant contribution to this conductivity, it's a kind of vehicular mechanism. But it is true that it's, in the end, it's a combination of Grotus mechanism and surface vehicle. It's, yeah.
Do you think that there is also water trapping by the MOFs that increase the local?
Indeed, because in the example of the proton exchange, when we shifted some protons by potassium, we decreased the amount of labile protons. However, in the case of potassium, what we observe is that because of the polarizability degree, and it's lower, that's, for example, in the case of sodium, water molecules were slightly more free. And this is the reason that we found our hypothesis that the water molecules are able to move faster through the structure, carrying the proton species.
Thank you. Sorry.
Thank you, Sergio. Very, very interesting. Okay, now that there is an expert in MOFs, I would like to ask you: do you have, or can you give us like a general vision about the water stability and MOFs? If you have, are there any relation between this, for example, the energy density of the linkers, the balance state of the metal? Now that you are working in this project that are where you have the water in the media, can you tell us more about your perspective? Feel free.
I'm free to tell you about all the things that have been published about MOFs. It is true that MOFs are not very water friendly in general, but it is because in general also relies on the fact that using different organic linkers that are not quite water friendly. And that includes something like porphyrins, such as pyrines, such as triathins. The point is that sometimes water is not penetrating within the structure, does not go through all the pores within. But in general, we are working with different strategies trying to improve such stability. Take into consideration that in general, MOFs are not stable for pHs lower than 1 or higher than 10. And in the worst case scenario, sometimes you can put the material in pure liquid water and it destroys. And it is, of course, related not only to the hydrophobicity, hydrophilicity of the linker, but also to the strength of the bonding, coordination bond that is established. So this is why, in general, these MOFs based on metal 3, metal 4 cations are more stable in water than those based on metal 2. Actually, metal 2 cations that are the most common in the MOF technology are the less stable in water. So it depends in the end about the structure, conjugation, and the coordination bond. Thanks to you.
Last question.
Thank you. Thank you very much for this interesting talk. I have a question about photocatalytic materials. If you may, could you please make some comments on the oxidation state of titanium and vanadium, because I have some doubts.
Okay. It is complicated in the case of vanadium. We still don't know. We are investigating that. We are trying to perform some paramagnetic resonance because we are not sure about the oxidation state, and we are thinking that we are working in a combination of different oxidation states. And this is one of the reasons that the stability of the material is not quite good when all the titanium is replaced by vanadium. But it is true that in the case of titanium, we performed several experiments in order to determine if this titanium 4 is really a titanium 3 that is required for such kind of reaction. We add some indicators, methyl violin, as far as I remember, in order to establish that if this is true. And yeah, we confirm the presence of titanium 3, at least. But
then you should repeat the DFT calculation because there is no titanium 3 plus in the density of states.
In which one? In the density of states?
Yeah, there is no titanium 3 plus. This is why I was wondering, does it match with the experimental?
Yeah, I agree with you. This is an experiment that are initial experiment for the next project that we are currently. It's more complex than that, yes, it is true. But yeah, this is one of the discussions that we maintain about the things that are going there, because simulations started with pure titanium or titanium 4, but not including titanium 3, never.
Well, I think we can discuss that.
Yes,
Okay,
sure.
You could discuss after that. So now we have to stop, and thank you again for your
Thanks.
presentation. The last speaker of this session is Professor Alois Kuhn. I'm from Universidad San Pablo, CEU, Spain, and deal with the influence of crystal structure on the electrochemical properties of H2V3O5 cathode.
Okay, thank you. Where do I have to put the stick here? This machine?
That
Mouse.
Make it full screen.
Good. Now it's ready. So.
Can you check?
Okay. Yep.
Working well?
That's fine. Okay. So thank you so much for your kind introduction, and I also would like first to thank the organizing committee for giving me the opportunity to give a talk here. So it's really a pleasure to be here with you. Thank you. So, vanadium oxides have gained some importance due to some very interesting cathode materials for lithium-ion batteries and post-lithium-ion batteries, and so on. And so there was the talk of Dr. Bois this morning about vanadium oxides as photoelectrodes for the cathode materials. And so even their recent reviews, they show that, or they debated that if vanadium oxides may be the future choice for metal-ion batteries. And so before centering my talk about what is this material, so hydrogen trivanadate, let's look back a moment about the characteristics, main characteristics and advantages of vanadium. So vanadium is relatively abundant in Earth's crust, so it's ranking 5th place in the among the transition metals in upper Earth crust. And it's commonly used industrial chemical, mainly related to the steel industry and also non-ferrous alloys. That makes more than 90% of the applications, and the rest comes mainly as a catalyst devoted to what is synthesis of sulfuric acid and malic acid synthesis. So another advantage is that vanadium allows for 2 electron transfer. So typically between the highest oxidation state 5+ and typically down to vanadium 3+. So you can achieve that upon deintercalation or intercalation of materials. On the other hand, and this is unique among the transition metal oxides, it has the high or very variety of coordination polyhedra, which ranges from tetrahedron VO4, here in blue, to green square pyramidal environment, and also octahedral one. And this is intimately related also to the different oxidation states of vanadium. So higher oxidation states, they tend to have a lower coordination, high covalence increase, and so on. And the lower oxidation states typically show the higher coordination spheres. So I took this example. This is a metastable phase with chemical compositions vanadium-4 oxygen 9, which is able to intercalate easily lithium, for example. So among these materials with 2 electron transfer, I would highlight here these 3 materials. So there's a vanadium dioxide fluoride, which is able to intercalate up to 2 lithium per formula unit, leading a very high capacity of 525 milliampere hours per gram. Another one, which is a dilithium vanadium dioxide fluoride with a capacity around 460 milliampere hours per gram. And interestingly, upon discharge of vanadium dioxide fluoride, which shows a rhenium trioxide structure, it converts into the structure shown here for the dilithium vanadium dioxide fluoride, which is a cubic structure related to sodium chloride 1. And what is the main part of my talk today is the dihydrogen vanadium oxide, HVO. This is able to intercalate up to 4 lithium per formula unit, leading a capacity of up to 380 milliamperes hour per gram, which is really impressively high. So the synthesis can be done easily by a fast approach using hydrothermal microwave-assisted synthesis. So in a couple of hours, you obtain pure HVO, which shows a nanowire morphology, so 50 to 100 nanometers in width and several microns long. Then also the good performance, cycling performance were demonstrated some time ago, together with a good power rate behavior. And we showed, for example, here, based on the electrochemical shapes, you can distinguish here single solid, single phase regions, highlighted here in purple, which extends up to 1 lithium. And then between 2 and 3 lithiums is another solid solution range, and the narrow solid solution regions up for the highest lithium amount in this structure. And these solid solution of single phase regions are sandwiched by the corresponding biphasic regions as expected. So we could recently confirm that by doing operando synchrotron diffraction experiments performed at Alban beamline. And so you can clearly here observe the biphasic regions here, the splitting of, for example, the characteristic peaks here, which is a 0, 1, 1, belonging to first biphasic region, or here this one, again, splitting of the peaks. And impressively, this happens completely reversibly. So upon charging again, which is here, this is instead of my discharge, you charge it again to initial state, it's completely reversible. So this is somehow surprising because it contains some hydrogen atoms. So let's talk about now about the nature of these hydrogens. They like hydroxyl groups or water groups and so on. So it's surprising a bit the stability of the hydrogen or these water-like molecules in the structure. So for structural refinement, the first dilemma comes from the fact that, as you know, so the light elements are almost invisible by X-ray diffraction, so especially hydrogen, not visible by powder, at least powder X-ray diffraction, lithium only scarcely, while the heavy atoms are well located by X-ray diffraction methods. On the other hand, neutron diffraction, if you want to use neutron diffraction, you can easily detect hydrogen and lithium, which even show a negative scattering length. This is also plausible for oxygen, but vanadium, it has a almost negligible scattering length. When we say normally it's transparent to neutrons, and indeed, maybe you know, some of you are using also neutron diffraction for sure. So the sample holders are made of vanadium, so these are normally vanadium cans. Okay, so this is without the intention of going into the deep or detailed procedures for structural refinement. What we did here is we used the synchrotron diffraction for structural refinement, in which the light atom hydrogen was not included. So this gives the information about the skeleton structures of the vanadium oxygen framework. Next, these refined parameters were used for the neutron diffraction data, in which the hydrogens were omitted. And so by means of different Fourier maps, we were able to locate hydrogen atoms. A single hydrogen position was found, and that was then completed the full structure, and we got really excellent agreement factors for the neutron diffraction patterns and also synchrotron diffraction patterns. We further checked the structural, the robustness of our structural models, which was refined in space group P and MA by doing DFT calculations in the lower symmetry non-symmetric space group P21 to 1 to 1. Okay, and this is the structural model, so the refined structure. So the structure consists of double blocks of octahedra, which are shown here in yellow V1 and green V2, sharing common edges, and they go down in that direction, which is the B directions infinitely. And there are other blue blocks, which are my square pyramids, which are also sharing edges. And the blue blocks are sharing common corners with my octahedral blocks, and they extend infinitely along the C direction. Now, interestingly, what about my water, my hydrogen atoms? So they're strictly bonded to the O6 atom here, forming water molecules, and they form a hydrogen bonds to O5 in the adjacent layer, in the next layer, and so on. And this was further confirmed also by DFT calculations. So due to the reduction of symmetry, so they have like more degrees of freedom. And so apart from this structure here shown there, in which we have a strict arrangement between O6 or 5, we also found here another configuration which was slightly lower in energy, only 0.07 electron volts lower for bromide, in which the hydrogen also, one of it is bonded to the O8 atom here. The proton mass in our spectrum is in agreement with a water molecule surrounded or subjected to a strong paramagnetic environment. Remember, we have vanadium 4+ and 2 vanadium 5+, so which are located in my octahedra, while the vanadium 5+ is purely located in vanadium 3, which are my square pyramids, as shown by bond valence calculations, bond strength calculations. So what about the schematic? So we used for solving the structures of the lithium counterparts was very similar, with the difference that, okay, here we have to find and locate two light atoms, which is lithium on one hand and hydrogen. And already my DFT calculations show that the hydrogen may be also bonded to some other oxygen elements, not strictly to O5, also to O8. And so, but regardless of that, we started the refinements again with a structural model without locating my light atoms, using synchrotron diffraction data. Then we used neutron diffraction, and by means of a successive difference Fourier maps, we located first the hydrogen atom, and the next one we located the additional lithium atom. Interestingly, the hydrogen atom here is different from the hydrogen atom observed in the pristine, in the non-lithiated material. On the other hand, and also highlighted here in red, there's an obvious and apparent shrinkage of the A direction. The A direction is exactly the packing of my layers. So this determines the interlayer space, which is in the principle surprising, because in most layered structures, normally you observe an increase of the interlayer space due to the collation of your ion species into the interlayer space. So that must be, you will see that afterwards, this is related exactly to the different location of my hydrogen atom in the structure. So this is now the structure of my lithiated material with one intercalated lithium. So what concerns the heavy atom structure is more or less the same, but there's a small but important difference, because now the hydrogens, before they were oriented towards the oxygen 5 in adjacent layers, now it's switched towards oxygen 8, which was already intuited in the previous calculations, where one of the hydrogens looked or was directed toward oxygen 8. And this structural robustness was also confirmed by DFT calculations. The difference is now due again to this gained freedom. The lithium here, for example, which is in an octahedral surrounding here, it leaves, let's say, the center of my octahedra and forms a more square pyramidal configuration with my oxygen atoms. So this is interesting. So hydrogen, let's say, and lithium, they see each other. That means the hydrogen must move away from the oxygen 5 position, allowing the space needed for coordinating my lithium in an octahedral, which is a typical combination for my lithium. Also, proton MR spectroscopy is in full agreement with my hydrogen switching, let's say, and subjected to paramagnetic surrounding. Remember now, the lithium intercalation is also goes together with a stronger reduction of my material. So there are now formally 4 vanadium 4+, together with 1 vanadium 5+. Concerning the lithium environment, so we performed bond valence some different maps, and that yielded in principle 2 possible positions. One of it was confirmed by the neutron diffraction data, which is position lithium 1. And in this, we got exactly this octahedral surrounding of the lithium, as I mentioned you before. A second lithium position deduced by bond valence, some different maps, is apparently empty according to my neutron diffraction experiments. And the NMR spectroscopy, again here, lithium NMR came to a rescue, let's say, because we performed now NMR spectroscopy, lithium NMR, and we found up to 5 signals, which were in full agreement only with the structure shown here on the left side. So the lithium subjected to strong paramagnetic environment. And interestingly, when measuring the spectrum against increasing temperatures, maybe you see that here there's an abrupt departure of the more strongly paramagnetic signals, which are the ones at -30 and -40 ppms. And this is an indication of local motion of my lithium ions. This is interesting because they are more paramagnetically shifted. So this is exactly along the edges of my vanadium 2+, which are vanadium 4+. So lithium seems to migrate or move along that direction, which is exactly along the B direction. So for that reason, motivated by this finding, we built and calculated bond valence some different maps. And indeed, we find this is exactly along the B direction here, in which my lithium-1 octahedra are sharing edges. So this seems to be the preferred motion path or diffusion path for my lithium ions. On the other hand, also the empty, at least, lithium-2 positions, they share common corners here in the same direction. But my calculations also, the calculations show there seems to exist another diffusion path, which is along the A direction, so across my interlayer spaces. So what about the vanadium oxidation state? So initially, vanadium has a mean oxidation state close to 4.7. So we performed now LNS spectra of the different discharged materials. So they were potentiostatically controlled. And so here the vanadium L2 and 3 are especially sensitive to the change in oxidation state of vanadium. And maybe you can already observe that. Here, this is my starting material, which is closer to vanadium 205, so which was one of my reference substances, which vanadium is +5. And upon increasing lithiation, that means the charge of my electrochemical cell, we have a shift of the vanadium L2 signals or my edges towards lower energies, which is in full agreement with my ongoing reduction of vanadium. And reaching a composition of lithium 5, we are very close to a pure vanadium 3+ state. In addition, now we are working on operando XPS experiments, also done on alpha beamline, Circe beamline in this case. And this is in full agreement with the findings from LNES. So interesting maybe is the fact that we find also at least at the surface level, remember this is a surface, so covering maybe 5 to 10 nanometers, not more, we find also significant amounts of vanadium 3+ on the surface, but in general, the trend is exactly the same. Increasing lithiation reduction makes the vanadium 5+ decrease, and on the other hand, the other one, the more reduced states increase as expected. Okay, now what about other ions which may be intercalated in HVO? There is a report about zinc ion batteries, and again, I refer here to the talk this morning. Zinc aqueous batteries. So this material is also able to intercalate zinc ions reversibly. And interestingly, so in this paper, they used high-angle annular dark field STEM images, and the dark regions or areas in this picture shown here correspond to the zinc atoms, and the light or the bright ones are my vanadium atoms forming like a hexagonal structure. And this is now interesting because the zinc atoms are exactly located or seem to be located in the same direction and in the same region like the lithium we detected in our work using neutron diffraction. And so this material, for example, is able to yield a capacity of up to 400 milliampere hours per gram. So this is really impressive. So we are now working also on magnesium intercalation in HVO. And for now, we get a capacity which is still moderate, around 100 milliampere hours per gram. And interestingly, also when you perform now bond valence different maps, which are shown here, these seems to indicate my diffusion pathways seems to be different from the one found, for example, for lithium. And there's a paper, previous paper, Rasper's group, So they located magnesium by means of XC to X-ray diffraction, and the position is not exactly the one corresponding to our calculations with BVS. So we are here also working on a re-examination of the structure of the magnesiated materials using advanced method, for example, synchrotron diffraction and neutron diffraction studies. So this is a full picture. So we performed now Bandwidth some different maps calculations for group 1 elements, group 2, and group 12. And as I showed you before, so for lithium at least, the intercalation seems to be favored. And we can intercalate indeed up to 4 lithium in this structure, while for sodium and potassium, at least based on our structure, the parent structure, seem to be hindered. And interestingly, both magnesium and zinc are favorable from this point of view from point Bailey in some different maps. So these are my conclusions. So I tried to show that we could give an accurate description of the crystal structure of HVO, also the lithiated materials, by using a combination of synchrotron diffraction and neutron diffraction data, using also bond valence sum here. And the lithium, the lithiation, I didn't mention that before, is related to a decrease in the interlayer space, which is somehow surprising. But this is due to the shift of my hydrogen bond, which goes from oxygen 5 to oxygen 8, and that makes a better connection between my layers, and at the same time opens the space for my lithium atoms to be intercalated. And that should, in principle, also work for magnesium and zinc. Why not? We're still working on that. And so the extended hydrogen bonding mitigates the volume expansion, which is helpful in this case, and allows for this very stable cyclability over hundreds and thousands of cycles on this material. And if you want to further determine structures and crystal structures, the use of operando or neutron diffraction techniques is highly desirable to follow in operando, in situ conditions, the structure's evolutions, not only of HVO, but any other battery material. So, and not only for lithium, but also sodium, potassium, why not magnesium, zinc, aluminum, or whatever other technologies. So this is the end of my talk. So I thank very much again the organizing committee for inviting me here. And then my group. So Ignacio, he was in charge of the measurements at Circe Beamline before he moved to our university. Pilar Diaz Carrasco, he was in charge of all electrochemical experiments. Marc Casado now is working on magnesium battery intercalation, and my colleague Flaviano Garcia Alvarado from the Science Material Institute in Madrid. I'm very thankful to Virginia D for the DFT calculations, and also Isabel Sobrados and my colleague Jesus Sant for all the NMR staff interpretation, collecting all the experiments and helpful discussions. And also the beamline scientists at Munich, the neutron reactor, and here François from the beamline in Alba. And financial support is also for sure acknowledged. And I thank you for your kind attention. Thank you very much.
Thank you. It was a very nice presentations. So with your material, HVO, during the intercalation process, lithium intercalation process, so you also observe VO2 phase, right? VO2.
Yes, VO2F, you mean, or VO2?
VO2. Is
VO2.
It, yeah, which phase is the VO2? Is that B
VO2,
phase?
the monoclinic VO2P you showed this morning, or?
Oh, yeah, yeah.
Okay. That would be interesting, yes, for sure. I'm sure that, okay, I didn't have any calculations here, but maybe it will also work for this type of intercalation materials, yes? Why not?
Yeah, I think VO2 is a,
yes,
VO2B phase is the one
yes.
of the very exciting materials, specifically for the big foam-like structures here. Yeah. Okay, thank you.
Yes, we're working so in HVO and some other vanadium pentoxides. Yeah. Vanadium pentoxides. No. Yeah, but not VO2, not VO2, yeah.
Hi. May I know where does the proton goes when you disintegrate in non-aqueous electrolyte?
Mm-hmm. You mean the material, the synthetic approach, or what?
No, when you reduce the HVO material, when you reduce a non-aqueous electrolyte, the protons are also disintegrated, right, from the structure?
Sorry, I can't hear you. Sorry.
The protons are also disintegrated from the structure of the HVO when you reduce in the non-aqueous electrolyte.
Yes, so you refer to the structural refinements.
Yeah.
Yes, that was not as easy what I showed you here in one slide.
Okay.
There are big difficulties because since you have the nanowires, for example, and you want to measure that, for example, in calorie, okay, but that you're ordering really your nanowires, so you're introducing a strong preferred orientation, which is very bad for any structural refinement.
Mm-hmm.
In addition to this nano morphology, so you have an acicular morphology, then you have an anisotropic broadening of your diffraction peaks, which is again very bad. But okay, I can. Oh, sorry. Yes. I can explain you that afterwards, if you want, in the coffee session, how we try to solve this issue. Yeah, but,
Sure. Thank you.
Thank you, Alois, for your interesting talk. I have a very general question because you have a lot of experience in vanadium compounds. And we saw in this material that the reduction takes place in a very wide voltage range. Do you think it's possible this challenge of getting the two electrons in a closer voltage?
Yeah. Yes, you're right, because you have seen that here we have like a, okay, you have a slope P and different plateaus which are separated by different, yes, a significant voltage difference. It would be desirable for sure to bring them to closer to each other. For sure. This was your question, I guess.
Do you think this is possible in any vanadium material?
Yeah.
This is like we are for years trying to achieve this goal.
Yeah.
Do you think it's really possible that is any vanadium compound where we can get these two electrons in a similar voltage? Or this
Okay.
is impossible?
Okay, as you know, so everybody now says it's a cathode material, regardless of the voltage range, isn't it? So in our case, so this is different from your case. So you're cycling between 4 and 2 volts. So in our case, we are cycling in a broader voltage range. Okay, yeah. Is that still the cathode? Yeah. And the way to solve the question? Maybe theoretical calculation would be wonderful here, in order to even engineer and build new materials and making predictions about different and maybe modifications in the corresponding voltage ranges here. I'm not sure if you can, from the chemical point of view, I'm not sure if you can get that easy. No? I'm not sure. Yes. Yes.
A question, Alois. 30 years ago, we were collaborating with Hydro-Quebec in the frame of the US ABC project, and the Hydro-Quebec reported lithium polymer batteries based on vanadate as a cathode material, exhibiting on a prototype scale 1,000 cycle at 100% DOD. And so after this has been cancelled because after the invention of lithium iron phosphate by John Goodenough. But now revisiting this material, do you think that there is a future for this vanadate in lithium, for example, in lithium polymer battery?
Mm-hmm. I would say, why not? Yeah, so let's try it. So the advantages, I tried to show that in my brief talk. Synthetic aspect, so you have a very cheap synthesis, and it's highly reproducible. You can scale it up, the synthesis, and okay, you can try it.
Thank you again, Alois. So now if I...
So, as our morning sessions unfold with captivating discussions and presentations, I would like to announce a well-deserved coffee break. So the coffee and refreshment stations stalls are just in the cafeteria. So please take your time and grab a coffee. The coffee breaks are sponsored by Biologic. So if you have any product-related inquiry, you can ask Osman. Osman, right? I pronounce your name right. Yeah, Osman. So you can ask him. So he will help you.
You can ask him to reduce the cost of Biologic.
Yeah, Biologic instruments are too costly. Yeah, we all can ask. Yeah, for us only conference presenter, we can reduce the cost. So please be mindful of the duration of the break, and we have exciting lineup of talks planned in next, and we want to ensure we'll resume on time, maybe after 30 minutes, 20 minutes, so it's be fast. Okay, enjoy your coffee. I think you all have the good coffee break. Welcome back. You had a refreshing coffee break, I guess. So everybody is settling down. So I guess you had a chance to talk with each other and, have a good session. Now, as we resume our conference sessions, I encourage you to carry forward the energy and enthusiasm from the break into our discussions. I would like to invite Professor Buddhodeka Borua to take the role of the session chair for the next session. Please welcome.
Thank you, Vidhan, for this opportunity, and welcome again. So we have now very exciting series of talks now for the sessions. So first we'll go with Alexander. So he's from CSIC. So he'll be working on liquid electrolyte and interface for calcium metal anode batteries, which is really exciting. So we are looking forward to your exciting talk. This floor is yours. Thank you.
Thank you very much. Good morning, everyone. So it's first of all, I would like to thank, of course, the organizer. That's a great pleasure always to come back to Madrid. So yes, today I will be talking a bit about calcium and just a little bit about magnesium as well. So mostly focusing on liquid electrolyte in this case and interfaces. So why calcium and magnesium? So I will be quick here. I think we all know that mainly the main driving force here is the sustainability. So magnesium and calcium are respectively the 8th and the 5th most abundant element on the Earth's crust. So we try to be more sustainable, let's say, when compared with lithium. And more than anything, we still have hope to get the metal anode to be safe. So using these metal anode, we for sure can have a significantly higher specific capacity when compared to at least insertion type materials such as graphite in lithium ion. And together with the fact that calcium and magnesium have quite low standard potential, we can definitely think about having very high energy density cells. But working with calcium and magnesium is very far from being trivial. And many of the issues that we are facing actually in this field comes from the fact that we have a very high charge over radius ratio, so very strong polarizing cations. So these comes along with a variety of difficulty, mainly involving poor mobility of these cations, both within the electrolytes, but also within cathode host structure. So this is also the reason why in the early 90s, sorry, the group of Professor Auerbach stated that both battery chemistry would basically be killed if any kind of passivation layer is being built on the surface of the metal anode, simply due to the fact that this will basically prevent the migration of the divalent cation through such passivation layer. So this is, of course, in stark contrast with the lithium-based chemistry, where the so-called solid electrolyte interface, which is formed by accumulation of decomposition product of the electrolyte at the interface of the electrode, allows for the migration of the single valent cation through this passivation layer, and yet this passivation layer, being electronically insulating, allows for to prevent any further electrolyte decomposition. So this is definitely a key parameter to achieve cyclability of this cell. So since then, most of the electrolyte that has been developed in the field of magnesium-based batteries has been mostly focusing on electrolyte formulation that does not tend to form such passivation layer. So we need to basically have a fully thermodynamically stable electrolyte to prevent the formation of such passivation layer. So since the early 90s, a huge improvement has been made both in terms of Coulombic efficiency achievable for magnesium plating and stripping, but also in terms of electrochemical stability window of these electrolytes, starting from the Grignard reagents, which are I mean, they have a variety of issues associated with them. They're pyrophoric, very corrosive, very low stability window, and so on. To the last generation of electrolyte, mostly based on alkoxy borate and aluminate, which gives almost a 4-volt electrochemical stability window and close to 99% Coulombic efficiency for plating and stripping. So we are getting close to the application, let's say. But calcium is a bit tougher, I would say, because we have these huge difference between the two metal, which is this 500 millivolts difference between the two metal anode on the potential scale, which makes a lot of difference, because since you can find quite a lot of electrolyte formulation that would be fully stable against magnesium, it is actually very, very difficult, I would say virtually impossible, to find an electrolyte formulation that would be fully stable against calcium. So you'd always have to deal with some kind of passivation layer formation. So this is the main difference, I would say, with those two battery chemistry that you have to basically deal with. So we do need some kind of passivation layer that would basically enable calcium migration through it. So we try to come back to investigate this field in the early, well, in 2013, and we try to basically look at the migration issues to the passivation layer, but also at other potential limiting factor, such as the salt dissociation in the electrolyte, the migration of this cation complex within the solution towards the electrodes, desolvation energy that might also be quite challenging. So the removal of all the molecules present in the primary solvation shell of the cation complex in solution. Of course, the migration of the cation through the passivation layer, and the nucleation and growth of the metal. So all these steps can, I mean, at least contribute to poor kinetics in this battery chemistry. So as I was mentioning, in early 2013, 12, I don't remember exactly, we started to work on this with Toyota Motor Europe at the time, so in collaboration with Fanny Bardet and Professor Rosa Palacin, also at Institut de Ciencias de Materials de Barcelona. And so we had, well, we struggled a lot, to say the least, but we quickly noticed that one of the main issues that we were facing at the beginning was actually the salt solubility and the overall cation mobility within the electrolyte. So we noticed that the calcium cation tends to form solution with quite poor ionic mobility, basically. So one easy trick, of course, to overcome ionic mobility in an electrolyte is just to heat up the system. So that's what we did and we tried. And we were actually surprised to see that we started to see some redox feature from cyclic voltammogram. So you can see here at room temperature, perfectly in agreement with Professor Auerbach's work, a perfectly flat cyclic voltammogram, so no redox feature at all. And when you start to increase the temperature, you start to observe some plating and stripping, basically. So we also confirmed the presence of calcium metal with X-ray diffraction at alpha synchrotron. But the most important part, I would say, was that we did achieve these plating and stripping in a carbonate-based electrolyte, so in an electrolyte that we were fully expecting to form very stable passivation layer. And we did indeed obtain very stable passivation layer that was stable upon cycling. And with this electrolyte, we were able to achieve, well, at relatively high temperature, electrochemical stability window above 4 volts. So that was at least the first steps towards being able to test cathode material and so on. So since then, a lot of work has been, so the calcium community has been growing over the time. And several electrolyte formulation has been demonstrated, also operating at room temperature. And we were surprised to see that basically all or most of these electrolyte formulations were based on boron-based anions. So this piqued our interest, and we tried to investigate a bit what was the role a bit of these boron atoms. But first, of course, we needed to know a bit more about this electrolyte formulation and overall the cation solvation structure in solution, and what was the basic physical-chemical properties of these electrolyte. So as I was mentioning, solubility is not the forte of calcium salt. So this was the first big challenge for us, to find any decent electrolyte formulations where we get decent ionic conductivity. So from most of the commercial salt, only TFSI, BF4 or triflate-based electrolyte present decent amount of salt solubility. And ionic conductivity were reaching maximum at very low salt concentration, so roughly 0.4, 0.5 molar. So this is something that we needed to master and understand to make good electrolyte formulations at the beginning. So to try to understand better these solubility issues and the properties of these cations in solution, we went for Raman spectroscopy, which is a very useful technique when it comes to understanding the composition and the properties of the cation solvation shell. So here you can see the Raman spectra that gives you, for instance, dedicated bands for the free solvent molecule, the coordinated solvent molecules, the free anion molecules, and the coordinated one. So you can quickly grasp some ideas about the cation solvation structure and the degree of coordination of the cation and the type of interactions it forms with the electrolyte molecules. So here, basically, we also compared these calcium-based electrolytes with different cation-based electrolytes, so lithium, sodium, magnesium, calcium, and so on. So we kept the anion, so in this case TFSI, the same solvent, and we looked at the influence basically of the cation. So the main trends we observed, the main conclusions were that the cation solvent and the cation anion interactions, the Coulombic interactions, were basically following the polarizing power of the cation. So they are much stronger for magnesium than for calcium, than for lithium, and so on. So this is basically to say that we are more prone to form contact ion pair, so having an anion present in the primary solvation shell of the cation for divalent cation than for lithium and sodium. In addition to that, we also observed that we do have more solvent molecules in the primary solvation shell of calcium and magnesium. So we basically have a much more bulkier cation complex to move around in solution, which of course will have a strong impact on cation mobility overall and potentially also desolvation energy, since we have stronger interactions for divalent cations. So we can also try to investigate how the salt concentration impact these properties. So basically here you can see the Raman spectra for calcium TFSI in ethylene carbonate at different salt concentration, ranging from 0.1 up to 1.5 molar. And you can have, well, mainly two type of main observation, let's say, out of these data. The first one is that, as expected, we do tend to form more contact ion pair with calcium than for lithium and sodium, and we start to form contact ion pair for salt concentration as low as 0.5 molar. So this is very low. I mean, you start to see them with lithium and sodium well above 1 molar or even 2-3 molar. And also the fact that as you increase the salt concentration, you dramatically remove the amount of free solvent molecule in solution. So you you basically enter the field of highly concentrated electrolyte, where you do not have any more free solvent molecule in solution at a much lower salt concentration than when compared with lithium and sodium. So lithium and sodium, you enter this field at, well above 4 molar, while you already have these type of properties for calcium at about 1.2, 1.5 molar. So trying to be a bit more quantitative, we went for Raman spectroscopy spectra fitting. And what we can obtain from this is basically the solvation number with respect to the salt concentration. So here you can basically have the amount of the number of solvent molecule present in the primary solvation shell of the cation, and the amount of anion present in the primary solvation shell, and its evolution upon the salt concentration in solution. So we tested different solvents. We tested also magnesium for comparison. And the main conclusions we came up with is that, kind of as expected, as you increase the salt concentration, you always reach a concentration threshold at which you start to enter anion into the cation solvation structure. But this concentration threshold at which you start to form contact ion pair is strongly depending on the donor number of the solvent. So basically you can design electrolyte with higher donor number solvent, which will be more resistant, let's say, to contact ion pair formation. And then comparing calcium and magnesium, it was also interesting to note that, as expected as well, but not to this extent, I would say, magnesium-based electrolytes are much more prone to contact ion pair formation than calcium. So you do have contact ion pair formation for concentration, as low as 0.05 molar. So this is something to take into account when you design an electrolyte for magnesium-based batteries. Looking now at the passivation layer on the anode side, we started to look at this through these experiments. So we were quite puzzled by the fact that having the same solvent composition, same salt concentration, and comparing only two different salts, so calcium BF4 and calcium TFSI, we're obtaining very drastically different electrochemical response. So you can see this very nice, and both are perform at high temperature. So we can see this very nice flat CV curve for the calcium TFSI, although we would expect much better salt dissociation in this case, as this is a very well delocalized charge over this anion, so this is expected to be dissociated much more. But we do not have any redox feature, by contrast with calcium BF4. So we try to understand this by looking at the passivation layer being formed. To do that, we first start with a transmission electron microscopy study. So we used a small trick here. We used some metallic particles that were polarized in both type of electrolyte, and then we can take those particles and put them on a TEM grid and look at the age of these particles to have a close look at the passivation layer. So we can see that basically the passivation layer in the case of calcium TFSI based electrolyte is relatively thin, roughly 20 nanometers, fully covering the surface and very smooth, yet it is apparently fully blocking for the cation. And in the case of the calcium BF4, we have almost 100 nanometer thick passivation layer, but yet we do manage to have plating and stripping. From X-ray photoelectron spectroscopy, what we obtain is that the passivation layer formed on the TFSI-based electrolyte were clearly mostly solvent degradation product, mostly carbonate. While in the case of BF4-based electrolyte, we mostly observed some anion decomposition product, so borates and a little bit of and calcium fluoride as well, of course. So these was the main differences we observed. So we have basically the same component, except that we do have these borate compounds in the case of the BF4-based electrolyte. So we confirmed from energy electron loss spectroscopy and infrared that those were BO3 moieties, so we do not fully understand now the nature of these type of borates in the passivation layer. But we do know that we move from the BF4, the tetragonal configuration, to the BO3 configuration. We do suspect that we have a successive nucleophilic substitution of the labile BF bond, leading to some kind of polymerization and with these BO3 moiety, but this needs to be further explored. But we were interested to understand basically if this borate containing passivation layer was basically the key to achieve plating and stripping. So we tried to basically polarize two different, two stainless steel substrates, let's say, in BF4-based electrolytes. So we cover these substrates with a borate containing passivation layer. And then we cycle those electrodes again, so we rinse them properly, and we cycle them now in TFSI-based electrolyte or BF4-based electrolyte as previously. So not only do we start to now observe some calcium plating and stripping in TFSI-based electrolyte, but we do also observe a significant increase into the overall kinetics for plating and stripping in this case. So clearly the presence of these borates in the passivation layer is enabling the calcium plating and stripping, but the formulation of the electrolyte do also play a key role into the overall plating stripping kinetics. So one of the potential rationale we can have explaining this difference in kinetics also come from the understanding of the cation solvation structure. So from Raman spectroscopy, we do know that the TFSI-based electrolyte are fully dissociated, so we do not have contact ion pair in this case. So the calcium is fully solvated by solvent molecules, while in the case, at this concentration at least, of calcium BF4, we do have a large degree of contact ion pair formation. And from DFT calculations, we do know that the binding energy for these contact ion pair is much higher, so we will have to pay a much higher energetic cost for desolvation for contact ion pair than for fully dissociated salts. And here, as a side note, I will mention that, as expected also, the Coulombic interaction for magnesium are actually higher than for calcium. So we do expect that these higher binding energy, also in the case whatever the complex is, for magnesium, will basically decrease the overall kinetics of magnesium cell when compared at least to their analog calcium equivalent. So of course, pre-passivation is not an easy way to assemble a cell, so this is not a practical approach to prepare a passivation layer. So we try to investigate different type of borate-based additives. So here we started with the trifluoroborate diethyl ether with the calcium TFSI-based electrolyte. So we basically put these additives into the calcium TFSI-based electrolyte, and we come from these very nice flat CV curves to these red CV curves that is very reminiscent from the one we obtained from the calcium BF4-based electrolyte. So here, looking at the passivation layer, once again, we can see that the passivation layer obtained with the BF3-based additives is very reminiscent of the one obtained with TFSI. So it is very smooth, homogeneous, and slightly thicker, so roughly 40 nanometers or something. It does contain quite a lot of borate, actually, even more. So the composition is similar to the BF4-based electrolyte. But it does contain higher amount of borate, roughly 20%, compared to the one of calcium BF4-based electrolyte. So we do come again with this borate-based passivation layer using these additives. So our hypothesis here was that basically we would form an adduct with the BF3 and ethylene carbonate in situ, in solution. So we tried to confirm that by directly synthesizing this adduct. So this was done in collaboration with Matic Lozinček from Slovenia, who prepared directly this type of adduct through BF3 gas directly. So that's not something, well, I would say easy to do, but he was unable to do that. So we were confirming that through single crystal that XRD, that this was indeed the adduct we were obtaining from infrared spectroscopy as well. And if we use now these as a co-solvent and with calcium TFSI and ECPC, then we come back to the same, roughly the same electrochemistry as before. And we confirm through different characterization of the passivation layer that we come back to the roughly similar passivation layer as for the BF4-based electrolyte or the one with the BF3 additives. So our understanding so far, supported by DFT calculation, is that the BF3 complexation basically favor the ring opening of ethylene carbonate. So these would be basically the preferential species to be reduced at the interface. This ring opening will be followed by successive nucleophilic substitution of the BF bond, leading to some kind of borate-based polymer. So now with this understanding of apparently this importance of the borate-based component in the passivation layer, we came back a bit to look at what was done in the literature also. So this first work from the group of PG Bruce using calcium BH4 was first hypothesizing that actually the interface was calcium hydride on the top of calcium metal, and this was not behaving as an SCI, as this calcium hydride was continuously being formed and during cycling. But this hypothesis has been recently challenged, mentioning that actually this calcium hydride exists as inclusion into the calcium metal deposit. And at the interface, in fact, you do have a mixture of calcium borate, calcium oxide, and a little bit of calcium carbonate as well. So we were also, of course, tempted to think that these calcium borate were playing a major role here. But I wouldn't fully exclude the potential role of calcium oxide, even though it is quite strange to think that calcium oxide could be a good SCI component, since it does have quite high migration energy barrier calculated by DFT, so roughly 1 electron volt. You have to think also that these type of energy barrier that are thought, so typically you think about 600 milli-electron volt, 700 as being the maximum that you can allow for decent migration. This is thought, those are values thought for active material. So you have to think that the passivation layer is nanometric size, and basically you can actually afford much higher energy barrier for a very thin passivation layer. So these energy barrier, and especially if you start to heat up the system. On the other hand, the energy barrier obtained for magnesium oxide would definitely be fully prohibitive. So it's almost twice as much as the one for calcium oxide. And we do think that, these might play a major role into the engineering of these batteries, because it's very, very hard to get rid of any oxides in these systems. So now, as I was mentioning, the last generation based on alkoxy borate and aluminate, there is not much information about these interface. We do work now in collaboration with the group of Professor Dominko and BN Biteng in Slovenia to try to decipher these passivation layer obtaining these electrolyte formulations. I can already say that we do see some borates. So this is also quite promising. And very quick word about the cathode material. So we have been working recently with wonderful people from India. I think they are here in the audience, working on organic cathodes. So very quickly, those present quite promising, I would say, electrochemical performances, even at a relatively high C rate. And just to put this into perspective, I've been working now since almost a decade in calcium-based batteries, and I've been struggling quite a lot for inorganic type materials. So that's not common, I would say, to have something cycling, and especially at these high C rates. So I was actually quite excited to see that something is working with calcium. And just a few words on the importance of the cation solvation structure, also potentially for the cathode material. Here we tested different salt concentration for magnesium TFSI for these same cathode material. And we do observe that as you increase the salt concentration and you do increase the number of contact ion pair, these actually leads to much more passivation at the interface. So the presence of contact ion pair in solution is very important on the anode side, but it is also quite important on the cathode side, as it can actually lead to promotion of anion decomposition. So in conclusion, I hope that I do convince you that the understanding of the cation solvation structure is crucial, especially for these divalent cations, where we do have to think about the potential electrochemical activity of contact ion pair complex. So we can have +1 complex, +1 charge complex, so they can still be electrochemically active, by contrast with monovalent lithium and sodium, where contact ion pair would be neutral. These can come as handy to engineer the passivation layer. We can actually use this contact ion pair formation to tune the passivation layer composition. But in most of the cases, those contact ion pairs are actually highly detrimental, promoting higher decomposition rate, also leading to much higher dissolution energy, so leading to worse overall kinetics of the batteries. So we, of course, have a long way to go. Calcium and magnesium is far from being optimized, but please do remember that lithium is along now for 40, 50 years now. We still do not understand their passivation layer, so we have some work to do, but we hope we are on the right direction. And then with this, I would like, of course, to thank the people behind this work, so people from ICMAB and different collaborators and from all around the world, and well, mostly Europe, basically, and the funding agency, of course, and you for your attention. Thank you very much.
For your exciting talk on electrolyte for calcium batteries. So can we take 2 quick questions? So we can take the 2 quick questions, yeah.
Thank you for this very interesting presentation. I have a question about calcium tetrafluoroborate, because what I think is that in BF4 as in BF6 or is an arseniate, the last bond is a coordination bond. There is a possibility of disproportionation giving BF3 plus F minus. So I wonder, but I don't know, if there is some HF that is generated that can attack the...
I cannot say for the HF. I wouldn't be so scared about the HF, since we will basically precipitate calcium fluoride very quick. So I think this is a good thing in our favor, so that we won't be to deal. We don't have to deal so much with the HF, but these BF3 generation is indeed quite a challenge, especially in terms of drying of the electrolyte. So typically the BF4 based salt that you can purchase is very wet. So sometimes you order it and it comes almost as a gel. So it's very tough to dry, and we noticed that. So we spent quite a lot of time to dry the electrolyte basically, and this always comes at the expense of the salt concentration. You can do whatever you want with whatever drying agents you want. You will always start to decompose the BF4, leading to calcium fluoride and reducing the salt concentration. So that's also why we tend to move away from the calcium BF4, because it was super challenging to dry. Yeah.
So one more question. Okay.
Thank you, Alexander. Very nice. I have a curiosity. So basically, you already know the composition of your say layer, no? When you are using more or less, okay?
More or less.
Still, still there are some missing information, of course, about the microstructure or the fully. Have you tried to grow this layer as an artificial layer and go deeper in the study of the conductivity and so on?
The artificial SEI is, I mean, it's wonderful idea, but I'm afraid that this is some kind of myth, because to reproduce the microstructure of an SEI is a very challenging thing, and I don't think that you can think of. So I'm presenting this story like the borate is very interesting and everything. So you can think like, okay, let's do a thin film with borate, and that would be the best SEI ever. I'm not sure this is the case. I think that the composite nature of the SEI is something essential. So calcium fluoride here, for instance, might promote stability. And this is the case, for instance, for sodium fluoride in sodium-based passivation layer. If you don't have this sodium fluoride, you basically tend to dissolve most of the SEI component, the good SEI component, much faster. So I think each component has a role, and it is very hard to design an artificial SEI due to this interplay between the components. So this is very, interesting, but very, very challenging. Yeah.
Thank you very much. So let's thanks to the speaker now.
Well, okay. Sorry.
Maybe one more last question.
Okay.
Thank you, Alex, for the nice talk. So in your opinion, what is the most promising electrolyte for calcium platinum stripping? Is calcium TFSI plus this additive to form the passivation layer, or what is the most promising?
Regarding calcium plating and stripping, calcium TFSI-based electrolyte is not competitive for sure with the calcium.
But if you add this additive to form the...
No, even with the additives. I mean, this is very interesting in designing the passivation layer. Then the calcium alkoxyborate and alkoxyaluminate are giving you higher Coulombic efficiency. Now the idea would be but the passivation layer obtained with the calcium alkoxyborate and aluminate are not optimum, and you have a degradation upon time. I do think this is because you do not have a very stable and passivation layer, so it basically decay over time. No? So you increase the resistivity. So the idea now would be to try to get a stable passivation layer and to combine this with the optimum electrolyte, let's say. So none of them are optimum. We still need to work on that.
Thank you.
Thank you very much. That's thanks to the speaker. So let's jump to the next talk, Dr. Janif. So he's from CNRS. So again, talking about calcium polymer electrolyte, route towards rechargeable calcium and batteries.
Thank you.
Thank
you, Chairman. Excuse me. What is to move?
Yeah, which one? Which one?
Okay, thank you.
Next.
Is it this one?
Is the next.
Okay,
and
is the next.
the,
Okay.
The red is the
and the pointer
marker.
is there.
This one.
Okay.
I think so. No?
Thank you.
You can
So,
see.
it was a nice presentation of Alexandre. I will speak about other kind of electrolyte, also with the same objective. Is it possible to go to a rechargeable calcium battery? All the advantage and excuse me. So, I have not to move. Mobility is not possible. So, so we will go to this rechargeable calcium battery, and all the advantages have been described, so I will go more rapidly. So the title is Versatile Ionomers. Why ionomers? So I make a point because all the audience is not specialized in polymer. Ionomer is something as a nomenclature that is coming from the industry. It means that a polymer bearing ionic group. For example, in fuel cell is Lithium is a ionomer. And for us in battery is a single cation conductor if you fix the anion onto the polymer backbone. And then we selected why ionomer. Then I will go to a solvating polymer backbone selection because there are several possibilities. Then I will go to two types of ionomers that we developed and their synthesis. And comparison in first without any solvent between lithium and calcium, and then following a swelling of this ionomer by solvent, and then to conclusion. So, why ionomer? So, because there is two ways. One of the ways is to build an efficient SEI and to test a lot of additives to perform, if it is not possible, to perform the best SEI. Our approach was different, was to say, is it possible to build something that is very stable in order to make a thin film polymer for this kind of batteries? And so if you look at, you imagine liquid electrolyte. So what is this one? Liquid electrolyte. Liquid electrolyte, for example, I mimic that a kind of carbonate, an acyclic carbonate, calcium, and I-, except the halide, fluorine, chloride, bromide, iodide, that are intrinsically stable in reduction. All the other anions are not stable in reduction and will face chemical and electrochemical degradation. So in the case of a liquid electrolyte, also the solvent, as for example the carbonate, is not intrinsically stable and can react with the calcium. And therefore, when you have degradation, as you are in liquid electrolyte, the degraded material precipitate or is renewed, a new material is coming at the electrode, another degradation occurs. Now, what is a polymer electrolyte? The polymer electrolyte, you have replaced the solvent, the organic solvent, by a polymer, a high molecular weight polymer. That means that this material cannot induce any reptation. And in that case, you have also possibility of degradation of the polymer at the interface with the calcium, but due to the very high molecular weight, the chain cannot make a reptation. So they remain at the interface, they are not renewed. What is renewed is your anion that can react again with at the interface with the calcium metal. Now, if you go to cross-linked ionomers, that was the target, or target, in that case, of course, neither the unstable anion, neither the polymer chain can be renewed at the interface. So you can have a little bit of degradation, but it will be limited and the material is not renewed. This is stopped. Additionally, there is a steric hindrance of the anion when it is located in the polymer that make more difficult the reaction with the calcium. That was the hypothesis. So now, so first we have to select what is good. Polyether is not perfectly stable versus lithium or versus calcium metal. So we develop first a kind of tertiary polyamine, amorphous, but the result, this was, I think they were intrinsically stable versus any kind of alkaline or alkaline earth metal. But the problem is that the conductivity were low, and the stability, the anodic stability was limited as for all the polyamine. So we left this one, and we moved to the polyether. Polyether, first the reference material is polyoxyethylene, that is a high molecular weight polymer, about 3,000 grams per mole. It's not just a point, it's not enough to go to 5 million. We have demonstrated that even making a steering with a magnet, you cut the chain in solution, and they go down to 300,000 grams per mole, roughly. So it's not necessary to go to very high molecular weight in that case. And we explored different salts in this way, that is high molecular weight polyoxyethylene, and fairly good with this, that has value obtained with triflate. At high temperatures, there is a creeping that can be obtained, but this done fairly high conductivity, much higher conductivity than with triflate, lithium triflate. Now with TFSI is a little bit higher, but there is a creeping of the polymer at high temperature. And the conductivity with calcium iodide should be perfect in terms of stability in reduction, are very low. Then you have not high conductivity. Sorry, there's a problem with it. You have not high conductivity in this field because you are in the crystalline part of the material, semi-crystalline, and therefore mobility is hindered by the crystallinity. Now, if we go to amorphous polyether networks that we have developed, you can see that we have already high conductivity for a solid from room temperature. So this is what we have obtained at different salt concentration with triflate. We did also with TFSI, but triflate is enough for this application. So now that we have fixed the type of backbone, the backbone is endowed with high solvating ability. The solvating ability of polyoxyethylene is much higher than that of tetraglyme or THF or dimethyl ether. And so we built the ionomer. The option one, that was our option, and was to make the polycondensation, building a special ionic monomer able to react by polycondensation, IMO-P. And that was our first option. But then we have some problem, in particular, to exchange the cation, something that we have solved by the end of the project. And we go to a second option, was to make ionic monomer that react by free radical polymerization, and that we have to introduce in the polymer in the last step of the process. So the first one, IMO, this one, is a kind of triflate make, and we have two fluorines that can react by aromatic substitution, nucleophilic substitution. And this one has two double bonds that induce the cyclization during the process of polymerization, and this one has been done during the project. So now if we go, if we have to make the polymer, we need to have a cross-linked polymer, to get a network, we have to introduce double bond into the polymer. Our classical polymerization is done, is this one. You take a polyester, an oligopolyester, polyethylene glycol, for example, 400, 1000, you have a lot of available, and you make a Williamson reaction in solid phase, and you obtain this material with a double bond. This material is easily purified by dialysis or by ultrafiltration, and you can eliminate all the unreacted products, the byproduct also, and you have a solution, a water solution. And this is controlled by NMR. So this is important to see that this reaction cannot be performed at higher temperatures than 50, 60 degree maximum. If not, you have you begin to start polymerization of the double bond. So this one, the second polymer has been done with this monomer by making a polycondensation between the polyethylene glycol and the ionic monomer IMOP. And the problem is that we cannot react in the same time the double bond and this monomer because this reaction required to work at around 110 degrees. So we make a first block by a stoichiometric imbalance to make a first block of 5,000 grams per mole, and then you decrease the temperature and add the second one to make this kind of polymer that is cross-linkable by UV irradiation. Okay, so the problem, just a problem, is that to make this polymer, you need to have, for example, the potassium or the sodium form. Once you have the polymer on the potassium-sodium form, very easy for us, the change between potassium, sodium, and calcium was awful. That was the reason, and we cannot make the reaction with calcium salt. Therefore, this means why we go to the second way. So now if we go to the linear polymer in terms of differential scanning calorimetry, you can see that roughly at room temperature, you have something that is amorphous, and the crystallinity is still decreased when you go to the network and ionomer. And this one, you can see what occurs with this material. And that we do with lithium and calcium. And you can see the concentration is not the same because we have to look that we went to compare by the concentration in positive charge. As the calcium is divalent, the lithium is monovalent. When we went to compare, we changed the concentration by a double, okay? So, this one, so we did this salt, we prepared this salt. This was easy because first we obtained the SO2F form. The SO2F form, putting that in water, saturated solution of calcium hydroxide, we go to the calcium form. For the lithium form, it's very easy. When you have the SO2F form, you put that in THF with a powder of lithium hydroxide, and you have a quantitative reaction. So in that case, also, you can see that you can get amorphous material from room temperature. And surprisingly, the gas transition temperature of the calcium ionomer is slightly lower than the lithium one. That is surprising because you can, in addition to the cross-linking by bonding, you can have a physical cross-linking due to the divalent material. But this is not, can be observed on the linear ionomer by rheological approach, but not by DSC. So now if we go to the conductivity comparison between both, that is the free ionomer and lithium, that is the ionomer with calcium, and indeed we make a kind of semi-interpolated, not a blend with polyoxyethylene in order to keep enough mechanical properties. And you can see that the conductivity are very low for the calcium. So it cannot be used at this stage. And if we go now to the cross-linked one, the conductivity obtained are awful. They are very low, and this cannot be used. And this is obtained whatever the kind of ionomers. So how to consider that with lithium, calcium salt dissolved in polyoxyethylene provide very high conductivity, and I observed that 30 years ago already. And now when you make this as a ionomer, this does not work. So my assumption is that indeed you have an equilibrium in the electrolyte between the divalent cation and the monovalent species, that is anion plus Cr2 plus, the whole making a calcium plus, a total species with one monocharge, and this in equilibrium with the other one. In the case of solution of salt into a polymer or into your liquid electrolyte, all these contribute to the conductivity. In the kind of ionomer, he has to let on one side one anion, one side of the second anion to move to a second one. And I think my opinion is that is detrimental to the conductivity. So contingency plan is to try to add high boiling point solvent, and this is, for example, with N-methyl formamide. So as I have few time, I selected a limited amount of characterization. What we observe is, for example, the gain when you use tetraglyme, that is high donor number material, solvent, or we use better polyethylene glycol of molecular weight 700. We increase the conductivity, but not so much. What we need is not an increase in mobility, we need an increase in polarity. So the best, for example, PC is not so good for us. Ethylene carbonate, that is whose dielectric constant is higher, is better. And we get about the same value with ethylene carbonate. So with that, we can say that we can get, for example, we see in blue, we can see that we can get materials that can be used, excuse me, in green is material without solvent, and indeed this one is the material with N-methyl formamide. So, so we have. Okay, thank you. This was our hypothesis. So we wanted to have a cationic transference number to 1, even if I add this solvent to the material, I have this. Now the risk is that when you use you swell a cross-linked material with solvent, you lose mechanical properties. But in that case, we have the use of crystalline nanocellulose that provide very high molecular, high modulus. For the polarity, this is bring by the solvent, and I think also that the donor number of the polymeric backbone contribute. So at this stage, we have not proved that is working. That the last result were obtained this last year. So, but what we can say is that from now on, the cationic conductivity, I mean the product of the conductivity by the cationic transference number of the calcium ionomer are insufficient, are not sufficient, and but once welded, they reach very high cationic conductivity. What we can say in addition is that the calcium ionomer electrolyte can be upscaled and can be processed by extrusion. We did the rheologic study shows that it's possible. And also what is possible is an alternative, a green process, to mix all the components in aqueous solution, and after evaporation to cast the film without using COV solvent. Thanks also to crystalline nanocellulose, mechanical stability is retained, and we can consider film from 10 to 20 micrometers. During the process, I was challenging. I did a film of 1 micrometer that was able to endure 90 degrees Celsius. But the problem is that you have no surface perfectly regular at 1 micrometer, and indeed also I had a short circuit when I did the measurement. But I think this means that it's possible to lower the thickness and therefore to decrease the ohmic resistance contribution of the electrolyte. So additionally, crystalline nanocellulose allows suppressing dendrite in lithium polymer battery. So that is a recent paper that we did with Stefano Passerini in this field. So now we have to select the best solvent, or perhaps the best additive, to combine with our ionomer in order to cycle calcium metal negative. The problem of temperature should not be a problem because we are able to go at 100 and more. The results that you obtain in Barcelona were obtained at 100 degrees. And also the other result of VDCAT, I have to emphasize the nice work done by my colleague Stefano Passerini in Ulm, and that qualify the calcium vanadate as a cathode material. And also a recent result of Polymer that means that it's possible perhaps to cycle the calcium electrode, calcium metal electrode, but this is not absolutely proof. We have to repeat. Thank you very much for your attention.
For your interesting talk. So maybe we can take 2 quick questions because of time limitations. Sorry for that.
Thank you for a nice presentation. Oh, I'm here. I was just wondering, so you mentioned that you measured the transport number?
We measure we measure the transport number on the same material on the basis of on lithium. It is not possible by pulse field NMR to measure the mobility of the calcium. The isotope that is
terrible for calcium.
As you are not sure to plate efficiently, you cannot use the Peter Bruce method, for example. But we did exactly the same material in which we exchange lithium and calcium, so the same material. We did that on the lithium one, so we can infer from that we have cationic transfer number close to 1. That means it's 1.
Because that's already quite a good thing, because that's, I mean, liquid electrolyte, I'm pretty sure it's well below 0.1.
You try to do by...
No, because I don't have also the means to do.
So if you have an idea to find a way to measure
that's
this,
an important point, much more than ionic conductivity. Yeah, I agree.
Thank you.
Very quick one. So you were mentioning dielectric constant as well as an important parameter for the solvent.
Yes, because in our idea, my idea is because when I built the project, in the risk mitigation, I say perhaps I will not obtain the good result. So I propose to use chelating agent because we can keep the cationic transfer number of 1. And to keep, for example, looking at aspartame, that is a very high boiling point system, and also PEG, for example. And surprise is that this does not improve the conductivity. You improve, but is limited. So I think this is explanation. You have the cation that's still attached on one anion that is fixed, and it cannot move.
It's kind of
and therefore,
the charge, no?
what is prevalent is the dielectric constant.
Okay. Thank you very much.
Thank you. Any more question? Okay.
Very nice talk. My question is why you have so high limitation in doing thin films? Why so you can reduce thickness?
Why I can? Because in battery, people forget the geometric factor. For example, you are specialized. If I make ceramic for a big battery, I cannot go, despite the very nice performances of the electrolyte, I cannot decrease, I think, due to the brittleness, I cannot decrease the thickness down to 100 micrometers or 200 micrometers. So I have high conductivity, but when I compare, I look at the ohmic drop in the electrolyte, it will be very important. You understand? So
you can support the electrolyte on the electrode, for example.
Supporting the electrolyte. I did that by the past with porous, the swollen tissue for the woven tissue of polyamide, for example, 60 micrometers and minimum. But polyamide are destroyed with lithium electrolyte. And so, but I did that. So no, I think the main interest when you use crystalline nanocellulose is that you can disperse in your material. After evaporation, for example, you have formation of the red, and you can get, I got with polyoxyethylene storage modulus of up to 200 megapascal, up to 150. And I do not lose conductivity because there is a separation. One is in charge of the mechanical strength, and your polymer is in charge of the conductivity. When I cross-link, I can increase also the Young modulus, but when I cross-link, I can go to 10 megapascal, for example, but I will lose 200, factor 200 in conductivity. So it's not interesting.
Thank you.
Sorry.
Yeah, let's thank to the speaker. Thank you. So next talk will be from Dr. Javier. He's from CSIC, and he'll be talking about scalable polymer materials for sustainable electrochemical energy storage systems. Floor is yours, please.
Thank you.
I'm really sorry for not giving time to ask a lot of questions. Maybe during the lunch time will be the best time to discuss more things about in details. Sorry for that.
Which one?
I think
any of that?
Yeah. Maybe the last one.
This one is better, no? Yeah, this will work. Yes. Report.
Maybe check this one.
Yes.
So let me check because maybe it should be fine if you. It's okay. I think.
This one? Sure, no?
Yes, I hope. I copied this morning, so.
Now, if we miss some slides, we'll discuss in the lunch. Okay?
Yes. Thank you.
No, welcome.
Okay, thank you very much. With hand, congratulations for the organization of this interesting event, and also the group, Alejandro, and the rest of the members. Okay, thank you very much. Okay, my name is Javier Carretero. I work at the Polymer Science and Technology Institute in Madrid at the CSIC. I belong to the Polymer Composite group. This is a big group with many different researchers with different backgrounds and skills. There are engineers, physicists, chemists, but there are like two main research lines. One is dedicated to the development of multifunctional materials that has strong mechanical properties, cell healing or acoustic properties, and there is another line related to the development of organic-based polymeric or organic electroactive materials for different applications, and I am leading the group of the battery, polymers for batteries. So we develop electrodes, electrolytes, and different components that can work in batteries. So this is the the people. So we have different projects. So there are some people working on microporous membranes for redox flow batteries, for instance, electrochemical CO2 capture. So we more or less dedicate our time to do research on polymers that has some electrochemical properties that can improve the current system or develop a new one. So our motivation, I know that most of you are familiar with this picture, but this is what is guiding our daily motivation every day, okay? So we try to answer the question of how we can scale up the energy storage because it's expected a huge demand on batteries, so we need to fabricate tons of batteries, and the current components that we are using in the manufacture of these batteries are purely sustainable. So we try to overcome these limitations, and this is just one very, very well-known example of the impact that, for example, has the extraction of cobalt in Congo. There's an environmental impact and also human issues related to the presence of cobalt that is needed in most of the high voltage cathode components in the batteries that we use every day. So as I said, sustainability is our prime criterion, okay? So, and in fact, most of the current critical points related to battery are related to this pure sustainability. Okay, we are using scarce and expensive metals. Okay, we need to study vanadium, of course, so I'm not saying that we don't need to do fundamental research on vanadium because we can translate later to the other advanced projects. So, but most of a big part of the elements that we are currently having in our composition and the battery composition are, as I say, expensive, scarce, toxic, steel, the energy that we are using to fabricate a battery is more than the energy that we can store on it. And this is also, there is an emission of greenhouse gases that are also very well, they are correlated to this battery manufacturing. Safety is also a sustainable issue somehow, because if we cannot, if we don't have safe batteries, it means that the lifetime of these devices are short, and this has an impact also in the sustainability, because we need to fabricate the new ones, okay? And also we have a pure, a very less extent effort on the development of new diagnosis methods to understand how battery works and why batteries fail. And this is also related to sustainability, because if we understand why the batteries fail or how the battery works, we can extend the life of these batteries. So as a scientist, we need to think on, put our effort in a circular economy, let's say, frame, okay? So in the next years, almost 80% of the vehicles in our street will be electrified. So, and still, most of the batteries are coming from Asia. In Europe, there is no clear regulation plans, as far as I know. If someone knows, please tell us later. And we need to not only put efforts on recovery, on recycling, on reuse of our batteries, we need to have in mind, when we start a new research, how we can prevent the wrong things, the mistakes that we have done before, okay? So I know that it's not easy, but we try. Of course, from the sustainability point of view, sodium is an alternative to lithium. Still there are lithium, so we can continue working on lithium, but sodium has an advantage as the use of an aluminum current collector that decrease the weight and also the cost, but still we have the penalty coming from the voltage, the energy penalty. Potassium ion batteries is an emerging technology that it has been already exhibited from the voltage of insertion versus lithium in propylene carbonates electrolyte, that we can go even deeper in voltage, which means we can maybe in the future make potassium ion batteries with higher energy than the lithium ones, once we solve many problems as for the calcium technology. But because I am a polymer scientist, I want to tell you that polymers are crucial components in batteries from the beginning of the development of this technology, okay? We have a polymeric binder that provides cohesion and adhesion to the different components of the electrode on top of the current collector. We have a polymer electrolyte in polymer metal ion batteries, or gel electrolyte in some of some batteries that you have in your computers. And the porous separator, or the separator in most of the batteries is made of a polypropylene or a polymer made of polypropylene and polyethylene. What is less developed is the organic electrodes or the polymeric electrodes in the batteries. There are I think that there is no commercial ones, although in the 80s some companies commercialized polymeric batteries based on conducting polymers, okay? But as I've said at the beginning, once the inorganic analogs appears and the people show that the performance was better, so they took over on these polymeric batteries based on conducting polymers. Batteries are flourishing in the activities related to the development of this organic and polymeric electrode because of what I said at the beginning, sustainability. We need to improve this aspect in the technology. So, okay, I am going to talk about what we are doing in our laboratory. Some years ago, we started in collaboration with the Complutense University. We start doing research and trying to develop coordination polymers that can act as a cathode material based on metal, based on the combination of a transition metal and tetraoxolane linkers. Okay, we use ligands that are quite abundant and cheap that you can buy at a large scale, and what we get are different crystalline structures with different dimensionality. Okay, we can have 3D structures with 1D motif, 1D coordination polymer change, or 2D that can store lithium ions. Okay, the most important thing was how easy it is to synthesize these coordination polymers. So in this case, some of them are MOFs. Sergio, if he's still around, can confirm this fact, because it's just an acid-base reaction very mild, under very mild conditions. You can synthesize these materials from room temperature to 90 degrees using water or some other alcohols, and you can get highly crystalline compounds, okay, which that it has this XRD pattern and this layer morphology. But as most of the time happen with our research, the properties are very pure, okay, in terms of lithium storage, okay. Most of these materials, we were able to store about like 1 lithium atom per formula unit, okay. The iron, those MOFs containing iron can store a little bit more than the others containing manganese complexes, okay? Although the manganese analogs, because they are isostructural, can store lithium a little bit relatively higher potential. But we learn a lot from the properties, okay? And after study different compounds, we observed that those materials, those crystals containing these one-dimensional motifs show higher reversibility and show higher reversible capacity than the analogs that has 2D structures, okay? So, and from all this information, we were able to improve we changed some parameters, okay? I cannot tell you now. I would like to tell you, I will tell you soon, okay? But we are waiting for the the patent in the results. So we were able now, these are not the best results we have so far, but now we are able to store not only lithium, we can store sodium and also potassium for this family of materials, and we can go up to 5 atoms of each of these metal-alkali ions. Okay, at that time, while we were doing this research, we have in our laboratory a very highly talented postdoctoral researcher, Paula Navalpotro, that was, she's an expert in redox flow batteries. Because we observed that these materials are synthesized sometimes in water, we say, wow, these are, this component, this crystal has a high stability in water. Why don't we try to prepare a colloidal dispersion of these solids, and we use these crystals as let's say, redox electrolyte materials in flow batteries, okay, at neutral pH, okay? So, well, I think that if you are related to, if you more or less are familiar with the redox flow battery field, you know that the membrane is a highly cost element, okay, component in this type of battery. So why we decide to prepare this suspension of particles is because by this way we can use a porous membrane like these membranes that you use in dialysis in your separation process or purification process in your laboratory, and by this way decrease the cost, because as you know, most of the membranes used in this technology are based on perfluorinated polymers that has a high cost, okay? So, okay, we start just trying to disperse these particles in water, and we fail, okay? The particles after 72 hours precipitate, so we just change the solvent in the synthesis, and chemistry works, and the size of the particles decrease by 1 order of magnitude. Of course, we check if the structure was still the same than before, in order to be sure that the crystals are the same, even if we change the size and the reaction conditions. And now we try to disperse again, and the manganese analog doesn't stabilize, but the iron one keeps stable in water for a long time. And we check by cyclovoltammetry the redox properties of this suspension, and we observed that there were like 2 main redox waves. So we decided, okay, let's try to use the same crystalline material as a single component in the redox flow battery by using this porous membrane. And well, we add some nanocarbon, like carbon nanotubes and also as a supporting salt to improve the conductivity of these redox electrolytes. And we built a cell. It shows reversible capacity, good capacity retention, but after 50 cycles fails because most of the material precipitates. So this is an aspect that still it needs to be improved, because the colloidal suspensions are not stable for a long cycling period of time. Okay, the last part of my talk, I think still I have time. Okay. The chairman should know, no? Oh, chairman.
So you have 5 more minutes.
5 more minutes. Okay. I also want to introduce to you a few examples of the activities that we have done so far in biopolymer batteries. Okay. The main objective of this research that we have been done in these last years is try to implement directly a biopolymer from nature, or from, if it's a little bit manufactured, it's okay, but a biomaterial that is abundant and cheap into as an electrode or as an electrolyte material in an electrochemical cell, okay? So this is an example. We were able to combine, for example, lignin. As you know, it's a polycatechol material that, if you see here, when you study the redox properties of lignin, you can see different redox processes at different potentials. So what we did is we combined, well, first we hybridized lignin with PDOT, it is a conducting polymer, and then we prepare electrode materials containing both at different ratios, of course, that contains this lignin composite with partially reduced graphene oxide that it was reduced also under mild condition at 150, 160 degrees, just enough to provide some conductivity in the electrode. And what we observe is something similar that this is what we observed is what we were pursuing, although this is from a paper of containing molybdenum, but the idea was have electrode showing these multi-redox processes, okay? So by this way, you can have a linear variation of the potential with the amount of charge that you are storing, and this was the results when we make a symmetric cell containing this, let's say, multi-component electron material. So again, the properties, the capacitance values are much lower than the commercial electrochemical double-layer capacitors made of highly porous, microporous materials, but we prove the concept of this multi-redox state with these biopolymers, okay? And the last example that I wanted to show you is about thin ion batteries. I saw you guys are very excited about thin ion batteries, so we also did some work recently. So the objective was prepare an electrolyte. It's not fully solid, but because it contains 90, it's a gel-like electrolyte. It contains about 90% of water, weight percent of water. So what we did, we prepared a compact hybrid by combining alginate and chitosan that everyone knows that are biopolymers that are abundant. This is from the sea. It's a biomass that you can extract from the sea, and basically you can prepare by microfluidic mixing, but also you can prepare directly by mixing and stirring. And what you are able to form is a coacervate here. And then later, you can just add, during the preparation, you can adjust the content of your zinc salt. And we were able to optimize the mixture in order to have a reversible plating stripping. And well, this was just electrochemical linear sweep voltammetry to infer what was the composition with higher electrochemical stability window, and we were able to go up to 2 volts at maximum. So the help of theory, well, it tells us that the transport number was close to 1, but the most important thing was that we leave asymmetric cells running for several months, and even with 2 power shutdown in the CSIC, the power shutdown is very common. I don't know if in your laboratories or here in the university, but at the CSIC, time to time, you have a power shutdown, and still even with the power shutdown, we were able to cycle. Here, when the publication appears, we were able, well, the cell was still cycling, but it keeps longer until 10,000, so but we published 7,000. So just to finish, I want to just to inform you that this year we will also organize the Superbad course, okay? That this was, the 3rd edition was last year in October, but the 4th edition, if you are interested, it's a free course at the moment, I don't know, but most probably yes. So it's a free course. If you are interested, you can write an email to this address, and the most important is that it will be in Barcelona, and even more important that will be in Barcelona is that it will be organized by Alexander Pont-Roche. So thank you very much for your attention.
Thank you, Professor Javier, for your exciting talk. So maybe we can take 2 more questions now, quickly.
Thanks, Javier, for your wonderful presentation. I really enjoyed it. I wanted to know what or how is the impact of the particle size in the case of iron, magnesium, and such coordination compounds in the final application?
For we didn't assess this. I mean, for the electrochemical, for the flow battery, let's say, or for the flow application, the particle size was of this order. I mean, now before to change the solvent in the synthesis, we have this micron size, let's say, particles, and then we went almost one order of magnitude lower. But we didn't realize a deep study, a routinary study about. But it could be, of course, very important because it can affect to the stabilization of this colloidal suspension, and then it can work. But think that during the oxidation and reduction of these particles, you are also changing probably the charge at the surface, and this is affecting also to the stability of the colloidal suspension. But we didn't go deeper.
Okay.
And in the case of the lithium storage, the particle size is in this order of, I mean, it's micron size particle. They are not nano size.
Okay, thank you.
You're welcome.
Two questions. First one, regarding the dialysis membranes that you use in the redox flow battery. What is the cutoff of your membrane?
Maybe someone in the public is I think it's a cellulose based membrane. But
no, my question is to know the objective of this dialysis membrane.
I think it's 10 nanometers or something like that. It's to block the big particle.
The big particle, or polymer. You use big particle rather than polymer.
I don't know the number exactly, but it's in the order of less than 100 nanometers, let's say. So the maybe some nanoparticles that are in the suspension maybe could go through but most of the particles are in the micron size scale. Oh, and this is nano. I don't remember if it's 20 or...
Okay, you can adapt to the size of your particle.
In principle, yes, because there are, when you buy this, it's a dialysis membrane, you choose the cutoff. It's the MCO, but I don't remember if it's 2,500 now, the number of, but it's nano, okay?
Okay. And the second question, rapidly, you say that you have a cationic transport of 1 for the zinc.
Yeah, 1, this is what theory said. But probably it's not 1, maybe it's 0.1. Let me...
Okay, because it's strange for me. You can show the polymer, please? Excuse me.
Yes.
In that you put that.
We have some free anions also, but very little ones. The concentration is very little. We have some acetic acid during the preparation of this coacervate, but the concentration is very. I mean, compared to the value of the range of the zinc chloride, is much lower. We are talking about millimole to compare to molar, so very little amount of. It could be there, but we don't know the amount.
Thank you.
Thank you very much. Thanks to the speaker. So we have one more talk before going for lunch. So this will be Nagaraj Patil. So he'll be talking about polymer electrodes for practical lithium-ion batteries.
He needs to remove there.
So Nagaraj, for is yours. Please go ahead.
It's in the same. Use this one.
Where is the USB? Okay.
Good afternoon, everybody. I am Nagaraj Patil, Senior Assistant Researcher working with Rebecca Marcia and Risis Palma at Imedia Energy Institute. First of all, I would like to thank Bodha for the kind introduction and also Alejandro for giving me this opportunity to speak in this first edition of the workshop. I am going to speak about polymer electrodes for practical lithium-ion batteries. I work in Imedia Energy Institute that is located in Mostly, south of Madrid. Immediate Energy is mostly dedicated to work research and developmental activities related to the energy and environmental applications. That is divided into 8 units, and I belong to electrochemical processes unit. In our electrochemical processes unit, we are more than 20 people, headed by Risis Palma and Rebecca Marcia. She is also here. We work on electrochemical technologies for various applications, including energy and environmental applications. In energy storage, we work with supercapacitors, static batteries, and redox flow batteries. Rebecca Marcia and myself are leading the research activities related to the polymer electrodes for lithium-ion batteries or other type of batteries. Here is the outline of my talk. So I will try to introduce briefly the organic electrodes for lithium-ion batteries and what are the challenges and requirements for practical lithium-ion batteries or practical organic electrodes that is quite far from inorganic electrode materials. And I will try to convince you or show you my own results with polyimide as a high-performance organic cathode in lithium-ion battery. You are all familiar with state-of-the-art lithium-ion batteries. So it's the technology of choice for the electromobility and portable applications because of its high energy density, good cycle stability, and also technological maturity. As Javier is mentioning, most of the electrode components in the state-of-the-art lithium-ion batteries, they contain toxic and scarce elements like cobalt, nickel, that doesn't support sustainability. So in order to improve the sustainability, one option is to go from inorganic electrode materials to organic electrode materials because they are organic and they can be sustainable depending upon their characteristics. Organic electrode materials have very good advantages compared to the inorganic materials because they can be bio-based or they can be easily synthesized in the lab, so they could be cheaper. They are mostly made up of carbon, nitrogen, oxygen, so they are very light. So also they don't contain any heavy metals. They will support the sustainability, and we can make use of our organic synthesis knowledge or polymer chemistry knowledge to tune the properties of the electrode in general. But they also have very important limitations. The electronic conductivity of organic polymers is quite low, so we have to process them with a lot of carbon additives in order to improve the electrical conductivity of the electrode. And sometimes they can be also soluble in the electrolyte, so that leads to poor cycle stability. Since I said they are made up of light elements, they are very light, so their density is very low. For some application where the volume and the energy is, volume and the area is very important, for example, electromobility, they can't be the best choice because of their low tap density. So their practicability is also quite poor in the applications where volume and area is very important. Organic electrode materials can be having any form. They can be a small molecular compounds, they can be linear polymers, they can be supramolecular assemblies or the porous polymers. Each class of organic materials have their own advantages and disadvantages. For example, small molecules, they give the highest capacity because of their lowest molecular weight, but since they are very small, they can dissolve into the electrolyte, leading to the poor cycle stability. One way to increase their stability is to polymerize them to get better cycle stability. Today I will try to focus mostly on the linear polymers. In the literature, there are a lot of linear polymers have been tested in lithium-ion batteries, ranging from conducting polymers to carbonyl polymers. In the Ragon plot, conducting polymers and radical polymers, they are characterized by high voltage and low capacity. Their kinetics is very good. That's why you see their specific energy is very good, but specific power is good, but specific energy is quite low. Organosulfur, it has a high capacity, you can see, but the voltage is medium. Still, the energy density is very high because of their high capacity, but their redox kinetics is low. That's why the specific power is very low. Quinones, they have the compromised performance in terms of energy and the power. But for future applications, if you want to have a high performance zone, you have to move diagonally in this direction to increase the specific energy and specific power simultaneously. That is really challenging. It's not easy, as you will see. At this point, I should also emphasize that most of the literature done in the lithium-ion batteries with organic electrode is at the material level. What I mean at the material level, you only consider the active material. You don't consider the carbon additives, binders, or other components in the electrode. So most of the times you improve the property of the organic electrode by optimizing its structure just to have the high capacity, high rate capability, and also the high cycle life, so that people are normalizing all the performance metrics based only on the weight of the active material, not considering the total weight of the electrode or the total weight of the battery. But for a practical application or for commercial device, what is very important is the performance matrix at the battery pack level, or at least at the cell level. So if organic materials wants to go from material level to practical level, we have to consider optimizing their performance even at the electrode level, or even and also at cell level, and finally at the battery level. So at the electrode level, we have to optimize the polymer content and polymer loading to have the highest polymer loading and highest polymer content to get the capacities at the electrode levels higher than the material level. But there exist only few studies in this electrode level. At the cell level, when you assemble a full battery, most of the time people focus on material level activity, not like practical level. High mass loading, they don't prepare high mass loading electrodes when they assemble a full cell. Most of the times it's at the material level. So it's important to balance the full cell and also evaluate the compatibility of both electrodes with electrolyte. For the final application, what is very important is the energy density. That is depends upon the application, and the cost. Cost is very important for the commercialization. So finally, what is important is how much it costs per kilowatt hour. That is also very, very important for the final applications. So in my knowledge, probably there is no practical organic battery at the moment competing with state-of-the-art lithium-ion battery. So how we can reduce the cost of the battery? So this is a material cost per kilowatt hour, and how we can evaluate or decrease the cost of the battery when we increase the aerial capacity for a particular combination. So as you know, energy density depends upon the electrode pairs. Always is better if you have a highest energy density for a particular pair. But for a given pair, if you try to increase the mass loading, then you can achieve some value of aerial capacity that can lead to the reduced cost. How? As I said, most of the state-of-the-art material is having low mass loading and low polymer content. So the aerial capacity is quite low. For this combination, let's say it's 1.2 milliamp hour per centimeter square. For a practical battery, this cost is very, very high. But for some application, if you want to reach low cost and certain aerial capacity, you have to stack many of these small cells to get that particular aerial capacity. This will always lead to higher cost, because you have to add lot of inactive materials into the cell. That will lead to the higher cost. On the other side, if you prepare a very thick electrodes of having higher aerial capacity, so it will drastically decrease the price of the battery, because you have only the thick electrodes without having additional non-active materials like this. So one way to improve the cost of the battery for a given pair is to increase the mass loading to achieve that kind of aerial capacity. But is it straightforward? No. When you increase the mass loading or thickness of the electrode, always the electrons and the ions have to move along the thickness of the electrode. That is quite torturous, and there are a lot of limitations. So you don't utilize the material properly if you have the very large thickness. So the rate capability can be poor, and also if there is a volume expansion in the thick electrode, it will disintegrate very rapidly, and the cycle stability can be very drastic. So with our approach, I will try to show you how we able to prepare the thick electrodes without compromising the lot of electrochemical performance. So polyimide is a naphthalene polyimide is a N type of polymer that Alex already introduced this morning. This can be reduced by taking 2 electrons and 2 lithium. So it gives you quite high capacity, around 150 or 160 milliamp hour per gram, and also redox potential is quite okay, 2.5 against lithium. It's not very high, but it's quite okay voltage. So once we decide the active material, we have to optimize its composition. So we process the electrodes with a different weight percent of polymer, ranging from 28% to 88%, and mixing it with nanocarbons. We mostly use single wall nanotubes plus reduced graphene oxide as a carbon additives. So then, when you normalize the capacity by the active material only, by the polymer in the electrode, As you expect, when you increase the polymer content from 28% to 88% for 1 C rate, let's say 0.1 C, you decrease the specific capacity. Also for one mass loading, if you increase the C rate, you decrease the capacity at the active material level. So it's quite known that when you have a high polymer content, the electrons and the ions are not moving very properly, so you lose material activity. That's why rate and the capacity utilization is very good at low polymer content and high carbon content. But as I said, for the practical application, what is very important is the capacity at the electrode level when you consider the carbon and other additives. So it's obvious that the electrode that contains 88% of the polymer, because it contains 88% of the polymer and the rest is 28% is non-active. So the capacity at the electrode level is the highest for the electrode with 88% of the polymer. So we have to choose a compromise between the capacity at the electrode level and also the rate capability. For this reason, we choose 68% of polymer and 48% of carbon, because it gives us a good compromise between the rate and also the capacity at the electrode level. Once we fix this composition, we try to prepare bucky paper electrodes of different mass loading, ranging from 1.2 milligram per centimeter square till 55 milligram per centimeter square. You can recognize that 55 is quite thick electrode. How do you prepare them? We mix our polymer with the carbon nanotubes and we disperse them with a sonication, and you filter them with the help of vacuum. You finally have a composite bucky paper that doesn't contain any binder or current collector, and also is also very lightweight. If you try to use the conventional Dr. Blade method to prepare a thick electrode, you always have a problem with the cracking or the delamination. So if you want to prepare a high mass loading electrodes, I think making use of a carbon and bucky paper approach is a very good one. Once we prepare this bucky paper electrodes of different mass loading, we evaluated the gravimetric and the aerial capacity with the mass loading. So the gravimetric capacity decreases obviously with the mass loading, but this decrease is very, very small, only 15% at the highest mass loading. This means that the aerial capacity is increasing very linearly with the mass loading at this low current. 0.03 C is like 30 hours for the charge and 30 hours for the discharge. It's very slow charge and discharge. So we evaluated these with the different C rates, the rate capability experiments. Nothing strange, it's expected. When you increase the mass loading at a given C rate, you decrease the specific capacity, and when you increase the C rate, you also decrease the specific capacity. So you get the best performance with the lowest mass loading for the rate, but you also have a reasonably good performance at the highest mass loading. But when you convert this value into the aerial capacity, we still get a very good aerial capacity, around 5 milliamp hour per centimeter square at this practical current density at the highest mass loading. Once we have this half cell experiments, we try to compare the results in a Raygon plot with the state-of-the-art materials. In terms of specific energy, we have 415 watt-hour per kilogram. Here it is. It's still an interesting number compared to the literature, but in the literature there are a lot of other polymers which can give you higher specific energy than this polymer. But when you go to the aerial performance, because we have a high mass loading, we have a high aerial capacity and also high aerial energy density. So this is quite away from most of the literature we reported in this context. What is also very important for the volumetric application, tap density is very important, because organic polymers are very light, so they have a very low tap density. But with this particular polymer, we achieve very good tap density of 1.2 gram per centimeter square. That means that volumetric performance was way much better than most of the literature, most of the reported polymers. So these polymers can give you very good gravimetric capacity, and also aerial and volumetric performance is also quite good. Cycle stability was extraordinary. It can cycle for 300 days with 76% of capacity retention, but this was with a low mass loading electrode. What I mean low mass loading, when you assemble against a lithium metal, the capacity of the lithium is so high, and also amount of the electrolyte was used so high, it's like a non-practical condition. That's why it cycles very, very good in this condition. When you try to cycle the high mass loading electrode, in this case you see the capacity ratio between the lithium and our cathode is very small, and the amount of the electrolyte is very, very small. And you see there is a rapid capacity decay with a cycle number when you use this high mass loading condition. So in order to understand this loss of capacity, we disassemble the cell and we reassemble with a fresh lithium and fresh electrolyte with the same cathode. and the capacitor recovers, story is the same. We do it again, and the story is the same. This tells that our cathode is quite stable. Whatever the problem is coming is from the lithium side, and it's already well known in the literature that lithium forms dendrites, SEI, and also there is a continuous consumption of the electrolyte. That's why the cycle stability loss is because of the lithium metal side. Fine, yeah. So once we optimize the performance in half cell, we decided to assemble a full cell, but not all organic battery in a semi-organic configurations. We assembled two type of cells, one with polyimide as an anode, and we combine with LFP or NMC. We also assemble our polyimide as a cathode. In this case, we use a graphite as a cathode. I'm going to show the results of only graphite with a polyimide. We assemble two type of cells: coin cell with small area, 1.2 centimeters square, both with low mass loading and high mass loading cathodes. Also, we assemble a pouch cell. In the pouch cell, we assemble very high mass loading electrodes up to 99 milligram per centimeter square, and also a little bit larger area than the coin cell. The voltage output of this battery is 2.2, not so high, it's quite reasonable, and nothing much strange. When you go from a coin cell low mass loading to coin cell high mass loading and the pouch cell very high mass loading, gravimetric capacity decreases, but increase in the aerial capacity is quite huge. And since we increase the area also, the increase in the total capacity is quite 280 times compared to the coin cell. Rate follows the usual trend. When you go from coin cell to pouch cell, gravimetric capacity decrease, and the rate also get worsens. Nothing much strange here. But good thing is that even at this mass loading and C over 10, you can still get the capacity around 100 milliampere per gram is a quite high number. Cycle stability is also improved, so it can cycle up to 120 days in this configuration in this strict condition. The capacity ratio between the anode and the cathode is quite close, 1 is to 1.1, and the amount of electrolyte is very small also. So we can assemble a practical battery with good cycle stability for the coin cell, and for the pouch cell is also quite reasonable. It can cycle for 100 cycles. Of course, it's not as impressive as in the coin cell, but still we need to optimize the performance, cycle performance in the pouch cell. So finally, again, we put our polymer or our full cell into the perspective, comparing in the Regan plot with the semi-organic batteries or commercial batteries or even with all organic batteries. In terms of specific energy, the energy density are above 200 watt-hour per kilogram is a good number, so it's quite competitive with the literature. As I said, our advantage is the mass loading and the aerial capacity. So the aerial performance was much better. So our polymer perform our semi-organic battery performs much better than the state of the art. Finally, the cost. As I said, cost is very important. Since we increase the mass loading and the aerial capacity up to 40 milliampere per centimeter square with a low porosity, so finally we able to achieve the cost that is less than $100 per kilowatt hour with this high mass loading condition. So this cost is quite favorable for electromobility applications. But also I should mention that in this electrode we use 60% of the polymer and the rest was the carbon. So another way to increase the capacity and decrease the cost is increase the polymer content to high, let's say 90%, so that you decrease the carbon content to 10%, because this carbon cost more. Carbon nanotubes are more expensive than the polymer. So I think we are now working in this direction. I hope we will be able to decrease this cost in this more practical electrodes. So we will see how it works. It's my last slide about the summary. So I hope I able to convey the message that of course organic batteries are promising, quite competitive, but competing with the state-of-the-art lithium batteries is quite far away. So we need to work on electrode level, material level, and finally at the battery level. So we are in that way. So our material performs much better than the state-of-the-art, both in the half cell, also in the full cell. With this, I would like to thank David Messeres and Nicola, because these are the persons who gave us the polymer to work. Also, we can buy it from the polymats, from the polymat, and also from from Polykey. So we can buy some commercial polymers now from Polykey. Of course, I should thank my supervisor Rebecca and Rusis for giving me this opportunity and the financial support. And thank you for your kind attention.
Thank you, Nagaras, for your kind, exciting talk on high mass loading base. electrode material. So maybe we can take 2 questions quickly.
Okay. I would like if you can explain again how do you fabricate the electrode, because you do it with filtration. You put any substrate or?
Yeah, we put a polyethylene membrane. So
And
all the material stuck to the membrane, and it's easy to remove from the membrane.
And this is really put as electrode?
Yeah, directly
okay.
you use it as electrode.
You don't put
current,
any
current.
aluminum
No,
or substrate,
no,
nothing?
nothing.
Okay,
Yeah.
very nice.
Yeah, that's the reason I said you at the battery level, it reduces the cost of the current collector, because current collector also weighs more than the active material sometimes. So
Yes,
the final weight of our organic electrode is much lower compared to the conventional doctor blade with the current collector, with the
Yes,
current
and you
collectors.
remove the step of the
Yeah,
doctor
step
blade.
of-
Very nice,
yeah.
thank you.
You are right. The real capacity is often neglected, so it's important to build thick electrode. And but I have a remark. You use something that I have forbidden in my laboratory. Is the use of single-wall carbon nanotubes. Is not healthy. This is very dangerous.
It's dangerous because of the problem it causes to the health, or yeah, I agree, but now there are some industrial techniques to be used in a proper way, not in a regular lab. But we try to optimize different carbons. We use carbon nanofibers, multi-wall nanotubes, single-wall nanotubes, and of course we got the best performance with the single-wall nanotubes compared to the multi-wall nanotubes. Maybe for the cost and for the health purpose, it's better to use the multi-wall nanotubes or even other nanotubes, which are better with a little bit yeah.
So be careful.
Yeah, sure. Yeah, we always use the mask when we use the nanotubes. Thank you.
So one more quick question from my side. So use. Okay.
It's just really short. Have you measured the porosities that you usually work with these electrodes?
We did not measure, we calculated from the theoretical value. So we know the theoretical density of the polymer, and we know the tap density of the total electrode. So theoretically, we deduce the porosity. But we can measure it practically. So theoretically, it was less than 30%.
Okay. Okay, thank you.
Okay. So you mentioned that single-wall carbon nanotube shows better responses as compared to multi-wall, right? So ideally, single-wall carbon nanotubes are semiconducting kind of behavior, so limited conductivity as compared to that of the multi-wall carbon nanotube, which is metallic conductivity. So do you know what is the reasons why you are observing better capacity in the single-wall carbon nanotubes? Any idea?
Probably it should be related to the percolation network that it forms with the polymer. It's more related to the percolation rather than the conductivity value. So we did not measure the electrical conductivity comparing different ones. So we mostly rely on the electrochemical output. So from the literature, I know if a particular type of nanotube can form a good percolation network, that's the case with the single wall nanotubes. Maybe the performance is better with the single wall than the multi wall, in my opinion. But
okay.
my answer may be wrong. Okay.
Okay. Yeah. Okay. Okay. Thanks. Then thanks to the speaker and a very nice talk.
So I hope you have found this morning session enriching and enlightening, as I have. So now we head into the lunch break for 30 to 40 minutes because we are a little late. But anyways, after the conference, maybe we can go to a buffet restaurant for a party if you are available, and we can discuss more because, sorry, we are giving so less time for you to interact together, and I really like it, discussions and all. Anyway, in the lunch, we're going to discuss more. So it's a 30 to 40 minutes lunch break, and coupons are with me. Please take from me, and I will be there with you. Okay, thank you all. no? So I just give a little bit of. Yes, so you can turn it on. You give some time, I think. It's a green. It takes some time, I guess. Hello. Yes. Yeah. Yeah. You speak near to the. So you can see it here, no, directly.
I must address.
Yeah, you can do this. No, not this one. I think this one is the light, LED.
Yeah.
And this is left. Means next. This is left, means backward, so you are going forward, no? So this.
And the LED set is there.
Okay, so let me announce. So I think everybody is settling down now after the lunch. So I trust you enjoyed a delicious lunch and had the opportunity to engage some meaningful conversation with your fellow attendees. We have an exciting lineup of presentation ahead, covering a diverse range of topics and perspectives. Before we go into the next segment of the conference, I would like to extend an invitation to Professor Ricardo to take the role of the session chair for the upcoming session. Thank you.
Thank you very much. Thank you.
After some time. Yeah, now we can.
Okay. Thank you to the organizers. And it's my pleasure to present you Professor Sanz. I know that many of people here in this conference knows Professor Sanz. Now he's an emeritus in our institute. Now he's has made a very large and important work on NMR application to solid state systems, not only batteries, also in catalysts and many other application of the NMR in solid state. So it's again, it's a pleasure to listen to him, and I can say that I have learned a lot. I work with him for many years, and it has been always a pleasure to discuss with him the research results, and he's a very influent person to me. Okay, thank you.
Thank you. Well, I would like to thank first the organizing committee to invite me to present data published in our group. And as you see, my specialty is centered in the characterization of the solid electrolyte. And I work in the Institute of Material Science of the Madrid in Consejo. No? First, I would like to show that the role of the electrolyte is to force electron to go to the external circuit and to pass the lithium ions to the cathode. In this case, it's a closed system that differs considerably to the fuel cell, where it's an open system and where hydrogen and oxygen go in and water is extracted. For the choice of the lithium electrolyte, I have presented this plot in which I show you the point in which we are interested, that is the conductivity of the solid electrolyte, be of the order of the then -3 Siemens by centimeter. In particular, we will be interested in the perovskites and in the case of the Nasicon, and I think that a comparison of two systems will be of interest. Our approach is based mainly in the use of different techniques, and in particular the diffractometric techniques, NMR, que es in spectroscopy, at the ion conductivity in order to characterize the solid electrolytes. And NMR is a specific place to study the structure that could be related with the data deduced from X-ray or neutron diffraction, and the study of the ion dynamics that could be compared with the ionic conductivity. When we have obtained the model, it will be justified by the application of the DFT or molecular dynamics techniques. In particular, in a brief summary, the NMR technique, we try to deduce the interaction of the atoms with the environment. In particular, we will be interested in the study of the dipolar interactions, nuclei, the chemical shift interaction in the nuclei with their electrons, and finally in the quadrupolar interaction of the nuclei with the oxygen that surround him. In particular, in the case of the lithium, we will be interested in the, well, we can obtain different parameters, but in general, they will be more interested in the isotropic chemical shift, and after the line broadening, that is the dipolar S2, second moment, and the splitting of the quadrupolar interaction that will indicate the strong, if the interaction with the network is important or not, and the symmetry of the site. Finally, we will be interested in application of the mass NMR technique, is the rotation about the spinning magic angle, in which the principle is to rotate the sample during detection in order to modulate the experimental envelope and by spinning side band that are more separated when the spinning rate increases. And at the end, when the spinning rate is sufficiently high, we will obtain one line for a narrow line for each environment. Well, now we would like to characterize the perovskite structure, but as I have said before, we'll be interested in order to make always the comparison, because one technique cannot solve the problem completely. And in this case, we will try to compare the result obtained with neutron diffraction, and in which the perovskite, the lithium lanthanum titanate, when you analyze the Fourier map differences with the structural model without lithium, we obtain the position of the lithium at the unit cell. And in particular, we can see that in this case, the lithium occupies the faces of the unit cell, but not the position of the A sites, indicating that the lithium is very small to fulfill the coordination with 8 oxygen, and prefers to move to the faces and to adopt a 4-fold coordination. When you increase the temperature, you see that the lithium begins to move at the 100 centigrade considerably, and at 700 Kelvin is not possible to localize lithium at the structure. When we analyze the NMR spectroscopy of the lithium, we observe that the mobility of the lithium, contrarily to what has been said by neutron diffraction, the mobility is produced at a lower temperature, minus 73 degrees, and at room temperature the mobility is very high, indicating that must be present the local motions that are not detected by X-ray diffraction, because neutron diffraction, because detect the position, the occupation of position. But if you decrease the occupation, it still remains the bands, but here the polar interaction are completely disappear. That when we analyze the low temperature. Distance between lithium is 3.8 angstrom. That is the same that the unit cell parameter. In order to characterize the lithium mobility, we have studied the T1 and T2 and observed they are 4 different regions in the plot. In the low temperature, this lithium is fixed. In these 2 regions, the local motion of the lithium are produced with a 0.14 electron volts. And in the case of the high temperature, they are extended motions with a higher activation energy. And I would like to underline this region, named near constant loss, in which the lithium is moving, is hopping inside the unit cell. When we analyze DC contribution to the conductivity, we observe an interesting thing for 3 analyzed series, the pure LTO, the high lanthanum content series, and the low content series in which partially lithium is substituted by sodium. And we observe that the mobility is relatively important in all 3 series, but decrease dramatically when we approach certain values. And that is a percolation effect, but that when we analyze not the lithium, but lithium more vacancies, both contributions follow the same pattern, indicating that the lithium and vacancy or vacant sites play the same role. And one thing interesting is that independent of the position of the vacancies, because here they are more vacancies than in this one, that independent of the vacancy, the mobility of the lithium is quite similar, indicating that it's a peculiar system in which lithium and vacants play similar roles. It must be said that in this case, the occupation of the lithium of the unit cell phases produce the vacancies at the A sites, indicating that the lithium, the vacancies can be of 2 types. The vacancy, nominal vacancy given by the formula, and the vacancy associated with lithium. That is the reason why, in this case, the conductivity depends so clearly with the lithium more vacants parameter concentration. And the 2 decrements correspond to a ternary 3-dimensional system and a bidimensional system. In order to confirm that by NMR, we have observed the lanthanum poor sample or lithium-rich samples, and we observe that the quadrupolar interaction disappears strongly when we approach to the percolation threshold. It is that when the vacancies are percolated, the lithium mobility is very high, and with the percolation of vacancy is not produced, the lithium does not move. That is visualized in this case, in which when the number of vacancies are important, the number of the conduction channels is important, but when the vacancy decrease, the number of conduction channels decrease at the end. When the number of vacancies is below the percolation threshold, the conductivity disappears. In order to to give a model for the conductivity, we have observed that in the case of the lithium 0.5, lanthanum 0.5, normally we have the tendency to assume that the lanthanum ions must be suffer of the lithium-lithium repulsion, and electrostatic interaction will force the separation of the lithium ion. But in this case, the in alternation of the lanthanum and vacancy will not produce any conductivity. indicating that this model does not comply. And that other reason, disordered of lanthanum and vacancy must be produced in order to give experimental results. And I have given a model in which we have assumed that around the vacancies, all the phases are occupied by lithium, and in the case of the lanthanum, any of the phases are occupied by lithium. And in the lithium, there will exist two positions, one favorable for the lanthanum lithium diffusion, and the other one, it will be restricted mobility because the presence of the lanthanum ions. Well, in the case of the lanthanum rich samples, they are a differentiation of the two planes in which they are rich in vacancies or rich in lanthanum. In this case, the rich in the vacancies, you see that the bottlenecks, they are bigger than in the case of the lanthanum rich sample, indicating that the lithium mobility must be very high in this plane, but not in this case. And that suggests me that the lanthanum must be disordered in order to be accumulated in certain direction or planes, and the vacancies in another one. That is the precursor, the small ordering that could be explained this differentiation of the rich plane in vacancies and lanthanum rich planes. When we obtain the Fourier map difference in the plane rich in vacancies, we observe that the lithium can be localized very clearly in the sample, in the diffraction patterns recorded at 200 Kelvin, but when we increase the temperature, the number of possible sites for the lithium increases. And in the case of the high temperature, they are the lanthanum in which the lithium is not occupied, but in the case of the vacancy, they are surrounded by a strong amount of lithium, indicating that there exists some modulation of the sites by the presence of the lanthanum vacancies and the unit cell of this system. That indicates, based on this type of things, that it's important, the mobility in this electrolyte, when the number of vacancies is important. And in this case, must be considered the nominal and the vacancies created by lithium ions in the unit cell. Well, now we pass to see the behavior of the other structure, the nasicon, in which the structure is a little more complicated, in which we observe is composed by lantern units in which 2 octahedra are bonded by 3 tetrahedra, and the connection between these units produce the conduction channels in which M1 site in the ternary axis and this one, they are more significant sites, but there exist intermediate or position for the lithium. The M12, because they are at the bottleneck, triangular bottleneck between M2, M1, M2, and the M3 that could be interested to be investigated. In this case, one important thing is that M1 and M2 is adopt this configuration, and the importance of have the vacancies and the M1 site, because it's the crossing of the conduction channels, and that will improve considerably lithium conductivity. if they are vacancies here, the mobility is important. If the lithium is there, they not necessarily improve the conductivity so much. Well, they are two different positions for the lithium. M1 is very symmetric and is clearly deduced by the system with the germanium instead of air, at titanium, and two other systems, they are triclinic, in which lithium adopt more distorted sides. When we observe the T1, we observe again the transition of the triclinic to rhombohedral phase here too, and in the case of the rhombohedral only is observed one behavior, but in the case of the titanium, the mobility of the lithium is more important. And here there exists an important thing to be considered, that the local and extended motion of lithium are very well resolved. That is not produced in the case of the perovskite. And contrarily to the perovskite system, in this case, the occupation of the M1 site by the vacancy is important. It's not important the number of vacancy, it's important the location of vacancy. That controls completely the physicochemical behavior of the system, indicating that in the case of the rhombohedral, the lithium occupies M1 site. In the case of the triclinic, occupies the M1 site. But when we increase the temperature, it produces a phase transition of first order or in order disorder transition to give the activated state in which the difference between potential walls is very small and the lithium mobility can be increased considerably. That is produced by temperature, but could be produced by chemistry substitution. And in this case, we have again analyzed the one thing is important, that in the Nasicon system there exists the phosphorus that are connected to octahedral cations. And if we put trivalent instead of tetravalent, the number of sodium can be improved. In this case, we observe that in the series appear 5 lines, and as a consequence of the different number of zirconium and indium, and in this case, they are 4 zirconium, 3, 2, 1, and 0. It is for indium coordination, and from the analysis of intensity, we are able to deduce the composition of the Nasicon phases. That is important because, and to deduce the type of the distribution of the octahedral cation. In the case of the random distribution, the lithium mobility will be higher, indicating that the entropic factor can be important. Well, in this case, the sodium mobility at the M1 and M2 sites is not produced at room temperature, but when the sample are heated to the 100 degrees, the exchange between both sides is produced. Now, we have continued to analyze the series titanium-germanium for 2 tetrahedral substitution, and in this case, the number of lines were them, path 5, indicating that beside the titanium-germanium, they are a differentiation of the oxygen charge of the O1 or O2 oxygen, indicating that with this technique, the phosphorus can be a very useful technique to deduce the distribution, that in this case was completely random. Well, in order to illustrate the utility of the NMR technique, we have presented in the series of the titanium indium, and depending on the amount of the indium, we can have rhombohedral, orthorhombic, and monoclinic phases. And the lantern, the structural units, they are always in the same direction, but in the other two, they are inclined in two different positions. When we observe when we analyze the Rydberg patterns, Rydberg analysis, we observe one interesting thing. That is that the rhombohedral phase in which the lithium mobility is important, is the more important, there are some saturation of the amount of the trivalent cation, indicating that the lithium cannot go further than 0.5. But simultaneously appear the orthorhombic phase in which the amount of the indium and the lithium is higher. And in this case, they are an interval of composition in which is predominantly rhombohedral and a small amount of orthorhombic. That decrease the amount of the rhombohedral, increases the orthorhombic, and in this case is mostly orthorhombic one. And it is that will be surrounding particles, but at the end they are formed the nuclei of the orthorhombic. And about this composition, the orthorhombic is transformed in the monoclinic phases. That means that the neutron diffraction could explain different properties of different type of sample that display different SEM images in which they are small particles in the case of rhombohedral, some agglomerate aggregates in the case of the orthorhombic, and the appearance of a new morphology in the case of the monoclinic phases. In the case of the phosphorus, the spectra seems to be very complicated, but we detect two lines for each type of environment in the case of the monoclinic phases and orthorhombic. But in the case of the rhombohedral, plotted by dashed lines, they are only one position. That indicates that in the rhombohedral phase, they are only one phosphorus site, and in the other samples, they are two differentiated phosphorus sites. The conductivity, again, is higher in the rhombohedral phases, but decrease in the case of the orthorhombic and monoclinic, and sometimes core shell structure are detected in the case of the monoclinic. In this plot, we will deduce the activation energy, indicating that in the case of the rhombohedral, the activation energy, they are one of the best of the literature. In order to explain the behavior of the conductivity, we have plotted possible channels for the lithium in the case of the rhombohedral, and we observe the system of different planes. They are relatively near, and they are connected by another position between both, lithium-3. But when we observe, we analyze the case of the orthorhombic, we observe two planes. They are more separated than in this phase, and the system of the channels, monodimensional channels, indicating that the loss of the conductivity is mainly due to the disposition of the conduction channels in this sample, indicating or suggesting that the reason of this behavior is mainly due to the connection of the conduction channels. I would like to prevent that the old people try to go until 2 lithium, but that in the rhombohedral is not possible to go further to 0.4, indicating that, that they are a limitation of the conductivity, the number of carrier in this type of things. And if we try to obtain rhombohedral phases with a big amount of the lithium, we obtain a lot of secondary phases, indicating that in order to optimize the behavior, electrical behavior of sample, you must proceed with analysis of this type. Well, finally, I would like to indicate that in the case of the lithium lamp Nasicon with titanium and aluminum, we detect with the neutron diffraction technique, the lithium is occupying lithium 1, but beside this type of position, they are lithium 3 that we have indicated at the beginning. And when we analyze the occupation of the structural site, we observe that the increment of the lithium of the structural site named 3 produce a decrease of the occupation of the lithium at the crossing of the conduction channel. And that is the reason, in our opinion, for the improvement of the lithium conductivity by changing the composition, not by increasing the temperature. That indicating that in this type of things, there exists some competition between lithium bonding, lithium-lithium repulsions, and the creation of the vacancy at M1 site is the main reason for the extended motion. But when you don't optimize the composition of sample, the secondary phases are producing problems. In order to detect, 1 minute, to indicate that we can deduce the diffusion coefficient, we can measure with the pulse field gradient technique made by 3 pulses and 2 gradient pulses that decrease the homogeneity of the magnetic field. And from these dependencies, we are able to deduce the diffusion coefficient with this technique when we analyze the intensity of the echo signal as a function of the intensity of the gradient, pulse field gradient. And we observe that in the case of the perovskites, the lithium mobility is lower than in the case of the Nasicon. In the case of the bidimensional system, they are an easy diffusion and a more difficult diffusion, that in the disordered sample, the diffusion is lower, but in the case of the Nasicon, with an appropriate composition, the vacancy increased considerably lithium conductivity. Well, in the solid electrolytes, the conductivity remains 2 orders of magnitude lower than the liquid electrolytes, indicating that in our case, we have obtained then -12 square meter by second. That is very good and could be applied for the all solid state batteries, but that is a little different, still remains different from the liquids. Well, when we analyze the diffusion coefficient as a function of the delta parameter, we observe some decrease like that, indicating that there exists some confinement of the lithium in the inside particles, and that is a consequence of the confinement. And changing the temperature, we detect some diffraction peaks on namely the literature, from which we can determine in the position of the minima the size of the particle that define the confinement. And in order to improve, we could change the sintering agent and try to go a continuous medium to improve the conductivity, but it's not easy. But I can stop, and we'll be happy if you have some questions. Thank you very much.
Thank you. Okay. Now it's time from few questions. You have any, please? Anyone? Yes.
Thank you very much for this interesting talk. You have been talking about the traditional lithium traditional conductors for lithium. And my question is, do you think any of these materials is appealing for, let's say, magnesium? Because now that everybody is trying to move to beyond lithium-ion batteries, what are your expectations, for example, for Nanostructured? Would you recommend to take any of those materials for magnesium or other
The problem
materials?
is that the lithium, the signal is very narrow and the diffusion coefficient can be determined relatively easily. In the case of the sodium, the line becomes broader due to the quadrupolar interaction, and the determination of the diffusion coefficient is more difficult. In the case of magnesium, the signal intensity is very small because the amount of the isotope, the concentration of this isotope is lower. I think it must be not determined in a very precisely way the diffusion coefficient. But it could be if we can improve the temperature, eliminate the quadrupolar interaction, and proceed to determine the diffusion coefficient.
Thank you.
Yeah.
More questions? Okay.
Just a general question. So at the end, the main limitation of the solid electrolyte probably is just the grain boundary, no? So especially in the polycrystalline.
You have observed the decrease of the diffusion coefficient with the particle size.
So the question is, how do you, from your point of view, and you are an expert on this, how can help this technique in order to analyze the grain boundary? Because at the end, the grain boundary is very small respect to the bulk. So probably you see very well the bulk materials, but not the grain boundary. So
Well, it has been published by a German group, I think, in which the elimination of the boundary in a single crystal, the diffusion coefficient are constant, does not decrease. And in this case, all treatments, all oriented to the elimination of the boundary would produce an increment of the plots observed to the single value, indicating that you will be possible to analyze the grain boundary limitation. No?
Okay, I think we move to the next talk. We have the speaker again. Our next speaker is Professor Elena Arroyo from University Complutense of Madrid. She's going to talk about first principle computational research of energy materials.
Thank you very much. First, I would like to thank also the organization committee for inviting me to this exciting day. And my warning was, okay, I'm going to talk about first principles calculation. So I hope you will enjoy the talk, because I did try to prepare an overview what we can expect from first principles calculations with the objective of identifying promising materials, not just for batteries, but for other types of devices. And that was all, end of the talk. Okay. Fine, going up. ¿Por qué me salgo todo el rato? Okay, it was quite easy, sorry.
Yeah, so this one is the next.
Okay,
This is
okay,
previous,
fine.
and this is the marker. See this one. This one is marker.
Okay, fine. I think I am...
Yeah. No, not this, that one. This one is the marker. You see?
No, I don't see.
No, no.
Okay, fine.
It's very small.
It's very small, and
Yeah,
okay.
and the next one is the next. This one is next.
Okay. Now I have the attention of everybody, so that's fine. Okay. So I started defining what is a first principles calculation, and in particular, the density functional theory. We start from composition and structure of a material. Let's say the crystal structure and what type of atoms do we have in any position in that crystallographic structure. Then, by applying basic laws of quantum mechanics, we have the outputs of the calculation. And these outputs are the total energy, the electronic, and the crystal structure. Okay. And this is density functional theory, and we say it's first principles because we only need composition and structure. That's the meaning of first principles. I will show you today that with these outputs, we can get insights into the performance of energy materials for different applications. In particular, metal-ion batteries, photocatalytic hydrogen production, and solid oxide fuel cells. Obviously, these are many different applications, and the requirements for the material are going to be also very different. We have also materials that are, in some types, always oxides, but there is an important difference, and this is that we, for example, in this application, we have stoichiometric compounds, but for this application, oxygen non-stoichiometry is going to be important. At the first sight, this seems to be not so problematic from, let's say, the point of view of synthesis of characterization of materials, but in terms of density functional theory, there is a big difference between calculating a material for a metal-ion battery or a material for a solid oxide fuel cell. I start with batteries. This morning we were talking, we were having two talks about calcium, electrolytes, and now polymer and liquid electrolytes, and now it's time for the cathode materials for this proposition of calcium ion batteries. From density functional theory calculation, we can infer the main characteristics of the cathode material: voltage, capacity, ionic mobility, electronic mobility, structural stability, and even thermal stability. This is for any metal, let's say lithium, sodium, potassium. In density functional theory, we don't have those drawbacks that exist in the experimental world. So it's the same to use sodium or potassium. We don't care for the computational approach. And as example, today I talk about calcium batteries, assuming that in the electrode material there is the intercalation of calcium ions. Let's say we fix that this is a calcium that is going to be intercalated into a host. The results I'm going to present belongs to a European project that was finished a couple of years ago. And in this project, we were doing the screening of potential materials for cathode application. We started from materials from the inorganic crystal structure database, and these were our targets in terms of voltage, volume variation, theoretical specific capacity, and migration barrier for the calcium ions. At the end of this result, we saw that compared to lithium materials, there are many materials in this search that fulfill the requirements of voltage, volume variation, and even theoretical specific capacity. The key aspect here is the migration barrier, which is normally too high to expect a good performance. Let's say that calcium ions are moving very poorly in this type of inorganic materials. Let me give you some numbers. This is a map, let's say a map, a representation of theoretical specific energy that we infer from the calculated voltage and theoretical specific capacity. And here we represent the calculated migration barrier. There are the results from different groups, and what we can observe is the prediction for materials with very large theoretical specific energy. For example, this compound here. We have materials with very, very large calcium migration barriers. For example, the silicate here. And most of the oxides are in this area. The target is 0.65 eV for the migration barrier, because with this value, we can, let's say, ensure more or less a good cutoff performance. What happens if we move to higher barriers? Experimentally, in this project, we could observe that for any barrier above 1 eV, there is no activity. Let's say,
This material may work well, but if we move from this line to the right, there is no activity. It's not a question that it's going faster or slower, it's just that there is no activity at all when we use those materials in calcium batteries. And there are interesting materials exactly at the borderline, and as example, I want to show you this calcium 4, manganese 2, oxygen 7. As I said, calculation of voltage, this is very straightforward. We have the theoretical specific capacity, manganese 3 plus, manganese 4 plus, and we start localizing the different pathways for calcium diffusion. This is along the z-axis and also in the plane of the structure. These are the numbers. These are the barriers we calculate from density functional theory, and the lowest barrier is 1.1 eV. This is exactly at the border between being active or being active material. I should say that this structure is related to the perovskite structure. These are layers of manganese in 5-fold coordination. These are 2 layers of calcium ions, and again, the manganese layer, again, manganese 3 plus in 5-fold coordination. This is the view of the plane, and this is the most favorable pathway. Further, from density functional theory, we can reproduce the intercalation reaction. If this is the initial structure, we remove calcium ions, and as a result, the output of the calculation is the new structure. Now, this is manganese 4 because of the oxidation, and it's quite interesting that there is a complete reconstruction of this plane. This is not so surprising because manganese 4 has a strong trend to occupy octahedral sites. And here, everything is 5 coordination. How the system evolves is towards the octahedral coordination for manganese 4 plus. In practical ways, this is telling us that if we use this material in a calcium battery, assuming that we can remove calcium ions, the material is not going to be stable. This is the translation of the computation to the real world. And with this in mind, with a material that maybe could be or could not be active in the battery, when we think that the intercalation is going to be irreversible, we attempted the experimental results. This is the result for the experimental work. This is performed by the group of Rosa Palacín in Barcelona. And experimentally, I show you here the synchrotron X-ray diffraction results for the operando experiment. This is the calcium cell. This is the electrolyte that was used for this experiment. We start charging the cell, and it can see the oxidation. There is apparently some activity with time, and this is the characterization. We see how there are some changes in the structure when we attempt the oxidation of the material. After that, during the discharge of the cell, these changes are irreversible. So obviously, according to this, something is happening in the material. We went then for steam evaluation of our material, and this is the pristine material. This is the oxidated sample. We see that there is a very well-ordered layered structure. There is an amorphization of the surface. We concrete that there is the oxidation of manganese 3 plus. This is ex situ, of course. This is the oxidation. This is the pristine material, and this is the manganese oxidation at the end of the charge of the cell. And what is interesting is that from EDS experiment, we see that there is fluorine in these structures. So with this information, it was possible to refine the XRD data. And in the end, what is happening in this material is that there is activity, but the activity is not due to calcium insertion, but to fluorine insertion in this material. And this makes sense because, as I said, we have here 5-fold coordination. Remember, I told you probably there is a rearrangement so that manganese goes into octahedral coordination. This indeed is achieved when we think in fluorine insertion. Fluorine is here. This is making the octahedral coordination of manganese. And not only there, because fluorine is very small, there is also the evidence of fluorine in between 2 calcium planes. So as a result, we can use DFT to anticipate materials, but is essential to perform experiments because sometimes we can have different answers. But in any case, this preliminary screening is very informative to anticipate what can expect from a particular material. So now, very fast, I go into another application. This is a photocatalytic for hydrogen production. What the requirements now are to have a semiconducting material with band edge position that are in good position respective to the water redox potential. More or less, this is the view. We have light, and then we have the promotion of electrons from the valence band to the conduction band. Typically, just to see how this works, I show you a very easy material. This is tantalum 5+. These are, again, perovskite slabs in the material. These are strontium 2 tantalum 2 oxygen 7, and another perovskite type slab, tantalum 5 compound. The idea is that from first principles calculation is very, very easy to determine the band gap of one structure. This is one of the most easy things we can do. Obviously, for photocatalysts, there is always the recombination of electron and holes, but we want to do a very basic screening, and for this, we are only looking at the very basic properties. This is the result of the first principles calculation. This is the calculated density of states for the two materials, and if we look here, the conduction band is wider for this barium strontium material, and in principle, we expect, according to with these representations, that the material could be a photocatalyst in the ultraviolet region, and if we compare the two materials, this one should have a better behavior. Further, the position of the band edges is also good, so let's see if we have experimental results according with the prediction. This is the experimental band gap in excellent agreement with the calculated band gap. And this is the hydrogen production, and as we anticipate, the barium compound has a superior performance than the strontium 2 tantalum 2 oxygen 7 phase. So I just wanted to show you something very easy to do with first principles calculation. I move to the other extreme, something that is much more complicated. Investigation of electrodes for solid oxide fuel cells. In these materials, as I said before, there is no calcium mobility, there is no metal, there is no electron and holes, but we have the mobility of oxygen vacancies, of oxygen interstitials. Oxygen is going to play the main role in this type of application. Is this important for DFT? Of course it is. This is completely another world. It's not the same to move calcium ions in one structure than to move an oxide vacancy. And this is much more challenging. Maybe this is the reason why there are not so many papers using DFT to investigate this type of materials. Here there is a big jump from DFT to the real materials. Fortunately, regardless the complication of having materials with bulk pathway and surface pathway, I want to talk about electronics descriptors. This is the focus that we are using in density functional theory in the last years. An electronic descriptor is a number extracted from the calculation that correlates to the properties. Let's say, this is the calculated density of states. This in red is the partial contribution of oxygen. This is copper, iron, oxygen. From this plot, we read the centroid of the oxygen contribution. In this particular case, is this here. And this is what is called the oxygen to p-band center. This is just a number we take from the calculation. Then, for the different materials, we read this number. And here is the representation of the property. This is a work from Dave Morgan in the University of Wisconsin. This is the property, these particular properties, but there are many other properties, and in all cases seems to be a good correlation between this number, the oxygen to p-band center, and the property. Here there are experiments, and this is some prediction of promising materials. So far, this is very nice, but there is a problem that most of these materials are very easy perovskites, AbO3. What happens if instead of AbO3 perovskite, without oxygen non-stoichiometry, with a perfect E and B lattices, we have a more complex material. Are these electronic descriptors still working? And this is the question we are trying to solve. Let's move to a more real material. This is, again, perovskite of layered structure, iron, strontium 2, copper 2, oxygen 7 plus delta. This means that we are moving from oxygen 8 to oxygen 7. In this material, this is octahedra. When we create oxygen vacancies, we are in a tetrahedra. This remains the same. Obviously, there is an important and drastic change in the electronic properties of the material. And this is a challenge for DFT investigation. The material, by the way, was proposed for some intermediate oxygen composition for electrode for solid oxide fuel cells. But my focus now is here. This is quite difficult because there are two transition metals. There is oxygen non-stoichiometry, and we have to reproduce the metal to insulating transition. So we need to make an assessment of DFT methods. I just show you one result. Okay, this is how it looks like when we use different density functional theory approximations. These are just the functionals. This one is not valid. Why? Because this should be a metal, okay, it's a metal, but this should be a semiconductor. Here we have a metal. We go to these other two functionals. This is metal, okay, this is a semiconductor, this is a semiconductor. For the electronic properties, these two methodologies are valid. But if we think in the magnetic properties, we look here, in this, the green line is iron. We can see that in this approximation, this peak represent localized electron density on the iron cations. But in this other, there is electron delocalization. This means that this approximation is more valid than this one. And this is a nice result, meaning that even for this type of complex materials, we can do a density functional theory calculation. But if you ask me, this is 1 year of work. The calcium battery material I showed you before was about 2 months. Okay? And so far, we proved that density functional theory is valid for these materials. What is the oxygen to P band center? As I said before, looking in the calculated density of states, we just need to read what is the centroid of the oxygen contribution. These are the oxygen to P band centers, and according with this, we go back to the same plot I showed you before. With these numbers, this system, even for intermediate oxygen contents, we are in this area, which means that these materials would be good for this application, although they are supposedly to be unstable. Okay? I don't go so far, but whenever a material is here, the property is very promising, but this is indicative of instability of the material. So I want to conclude here. Just some key remarks, because we don't have so much time for conclusions. I did try to show you that using the density functional theory, we can identify promising materials according to the basic requirements. Obviously, there are many others, but we just think in the basic requirements. There are easy and difficult materials and applications, so not everything is the same for density functional theory. There is an open challenge in the investigation of materials for oxygen evolution reaction and the oxygen reduction reduction, because, as I said, working with this type of materials is more difficult than with materials for batteries. And obviously, experimental work is always mandatory in order to verify the computational screening. That's all. Many thanks for your attention. Here, I think we don't have time, but okay. Of course.
Thank you very much, Elena, for this talk. Now the paper is open for discussion. Do you have any question? Okay, I have one question. When you make in this last very difficult part of cathodes for solid state fuel cells, when you make the calculation, which is the boundary of the atmosphere that for the cathode? For the cathode is going to work in very high pressure of oxygen, and also have to stand very low pressure. sometimes.
Okay, this is the idea. We don't have any pressure because this is a calculation even at 0 Kelvin. So the idea of the electronic descriptor is that taking this, which in the end depends on the covalency of the bonding, you can really go to those properties that occur at high temperature and with different atmospheres. So something like it really works because if it is a reality, this makes very fast the determination of new materials. But in the calculation, there is no atmosphere. You can work later with the chemical potential, but in the real calculation, this is just 0 Kelvin, and the calculation procedure is the same. Doesn't matter if you are in the solid oxide fuel cell or in a lithium battery. So from there, you have to construct what is happening in the application.
But even in the DFT, you don't know if at high temperature it's going to have a phase transition.
Yeah, of course. You don't know, but you can make the exploration if there is a phase transition at high temperature, because for that you have to think, okay, rhombohedral to monoclinic. So you can compute both phases and you can make some inquiries if this is going to happen. For example, high pressure is very easy. You can anticipate transformation under pressure.
Thank you. Any more questions in the audience?
Yeah, thank you for the nice talk. So a question outside from the topic DFT, because I'm out of the topic, but I'm curious about if DFT could be applied for exploration of some high entropy ceramics, which are now being proposed quite actively as an electrodes for solid oxide fuel cell and electrolysis, and if it makes things more complicated or more easy.
These are another type of difficult materials, because in high entropy alloys, what you have is disorder. And because we need crystal structure as the input for the calculation, everything has to be ordered. So to simulate disorder is quite complicated. You need a very large cell, so you introduce like disorder that is ordered, and this obviously is computationally very costly. So those materials are difficult.
Any more questions? Okay, we thank the speaker again. There's going to be an announcement.
So, hello everyone. So, due to the logistic problems, we need to take the coffee break now. So, after that, we'll resume from that. After that, I think we have 3 speakers and flash presentation. So, we'll resume from this part. So, have a nice coffee break. Just outside the same area. And it is sponsored by Biologic. Thank you.
micrófono, avísame antes de que baje el otro.
Es que no tiende a moverse porque como así, como miráis a la transparencia. Tenéis que hacer como los del tiempo, mirar a esa pantalla. Sí, pero bueno, deja acercar, vamos a pedir. Por favor, we take seat, please. We can begin. Okay, we start the session. Okay, our next speaker is Alodia Orera from the University of Zaragoza, no? The Institute of Nanoscience and Materials of Aragon in Zaragoza. I want to talk about high temperature solid state electrolyzer for green fuel production.
Thanks for the introduction, and thank you, Alejandro and Vidan, for the invitation. And thanks also for giving coffee to everybody before my presentation. I really appreciate it. And first, I apologize for my voice. I hope it lasts till the end of the presentation, but I'm not sure. Well, today I'm presenting here this work, but this is, of course, the work of a whole group. It's a PROCACEF group in Institute of Nanoscience and Materials of Aragon. And the main research lines of this group are these ones here. We have a research line which is dedicated to the study of microstructured materials, mainly from directionally solidified eutectic ceramics for different applications in energy, environmental, photonics, and so on. We can fabricate with these materials CO2 separation membranes, selective emitters, metamaterials, and so on. And we have these very nice self-organized materials with these structures, and what is more important, we have very interesting interfaces between different phases with also interesting properties. Another research line is hydrogen. That will be the one that I will be talking today, with different projects, both from public and private funding. We have also a research line in energy storage, mainly batteries, including lithium batteries, which is a more fundamental work, and also more conventional lead batteries in collaboration with some companies and the Consortium for Battery Innovation. We are developing, or we are studying some inoperando studies of these real batteries using neutron, and also some contracts with Excite technology. And also the fourth main research line, which is quite transversal, is laser processing that we use for solidification, marking, surface modification, microstructuring of very different kinds of materials, from ceramics to polymers. Well, most of our research is devoted to materials and devices for energy applications. And this is because we think that our energy system has some important problems. One of them is that it's responsible for 60% of the greenhouse effect emissions. This comes from the use mainly of these energy sources, oil, coal, and natural gas, which are responsible for up to 98% of the CO2 emissions. If we want to change this, we want to achieve the decoupling of the economic growth that any society wants to achieve from the bad side effects that has this energy consumption. We have to avoid the use of fossil fuels and look for new energy vectors. Among them, hydrogen is probably one of the most interesting ones. Of course, we also have to increase the use of renewable energies, as we have seen before here today. These renewable energies need a lot of energy storage in order to be able to use this energy when there's no wind or solar energy and so on. And also hydrogen can play an important role in energy storage. We can use this energy that is not being used in peaks of production or valleys of demand, and use this energy to produce hydrogen that can be stored to be used afterwards. We have seen lots of different storage technologies here in this conference, but if we move to high capacities and have discharge times, we need to move to power-to-gas technologies in the form of hydrogen or in the form of synthetic natural gas. And we really need to go to big capacities, because if we consider that the national plan says that up to 50% of the total energy consumed in our country will be met by renewable energies by 2030, we are going to need lots of storage. Of course, we need to produce this hydrogen, and from the different techniques or ways to produce it, looking at the green hydrogen, which is produced by renewable electricity to perform the water electrolysis, is the most interesting one, because of course the output doesn't have any kind of pollutant. At the moment, the production capacity for this green hydrogen is not very high, 8 gigawatts per year, but it's expected to reach 60 gigawatts by 2030. How can we do this electrolysis? We can do it by using fuel cells that, as everybody knows here, can be used in a direct mode, where you provide hydrogen and then you get electricity, or in reversed mode, where you provide electricity and then produce the water electrolysis to produce hydrogen to be stored. From the different technologies of fuel cells that go from polymeric membrane electrolytes to alkaline electrolytes to solid oxide electrolytes, we have chosen this last technology, looking at the electrical energy that is needed to produce 1 kilogram of hydrogen. We see the advantage of using this solid oxide. And this difference is very important if we think that in the electrical energy consumption is today more or less the 80% of the price of the produced hydrogen. This higher efficiency is clear if we look at the thermodynamics of the water electrolysis reaction. The higher the temperature, the lower the fraction of electricity that is needed to carry out the electrolysis. Even if we work at voltages below the thermoneutral voltage, which is the voltage at which the heat that is produced is enough to keep the reaction going, if we work below this voltage, we can get electrical efficiencies above 100%. In reality, in operation, the voltage of the cell will be higher because, of course, there are some irreversibilities in the system, some losses that will increase this voltage. Looking at these losses is important in order to optimize these systems. But before optimizing them, we have to be able to fabricate these systems. We do it in two different architectures. On one hand, microtubular cells that we do in collaboration with Alejandro's group in Universidad Carlos III. They prepare these anode supports by extrusion, and then we make our cells that are used, for example, in this project for the fabrication of 15 watts stacks that are going to be used for the final product being an auxiliary power unit to power electricals in isolated regions. Here is a very premature prototype of 12 watts in our lab. And this is in collaboration with some companies. We can also produce our cells in a planar architecture. We are at the moment getting 5 centimeters by 5 centimeters cells, which after some very dark months, now they make them very happy. We are able to produce them in a quite standard, with quite a standard methodology already. And we are using these planar cells in another important project in our lab, which is the fabrication of an electrolyzer with up to 2 kilowatts in a project in collaboration with Universidad Complutense and CEU San Pablo and the National Center for Renewable Energy. Well, if we look at some of our research lines that deal with optimization of these systems, if we look at the electrolyte, we have different research lines. One of them is the use of laser machining to improve the performance of the system. On one hand, what we do is we reduce the ohmic losses by decreasing the thickness of these electrolytes in electrolyte-supported configuration. We are able to decrease, for example, an electrolyte which is 150 micron in some regions which are not mechanically compromising the cell. We reduce them to 20 microns, and like this we get a reduction in the area-specific resistance from, for example, 1.5 to 1. We also use this laser processing to change the geometry of interfaces. For example, instead of having a flat interface between electrolyte and electrode, we get this microstructuring. That means a surface increase of 22%, which means also a decrease in the polarization resistance of the electrode of about 28%. We use this laser technology also in another project that has just started last September, in collaboration with these other groups. And here we use different technologies to design new 3D architectures in these energy devices, not only fuel cells, but also batteries. I just wanted to show you here, as there are lots of people working in batteries, the microstructuring of LS, lanthanum lithium zirconate, solid-state electrolyte by laser. Also, we not only look at improving the performance, but also improving the durability, which is one of the key issues for implementation of these systems into market. And last decade, it was quite clear that one of the main problems of these electrolyzers is the formation of oxygen overpotential in their interfaces, mainly between electrolyte and the oxygen electrode. What we have been developing is a new spectroscopic technique that, using the luminescence or the Raman signals of spectroscopic probes that we put inside the structure of the electrolyte, is able to monitor this oxygen potential with spatial resolution inside the electrolyte. For that, we are using the Terbium 3, Terbium 4 plus pair, which has been shown to have a good resolution in the luminescence signal at high PO2s, which is the range that we were interested at that moment. If we move now to the improvements that can be done in the air electrode, when we are working in electrolysis, the oxygen evolution reaction introduces lots of losses in the air electrode. There are lots of different processes that take place in this reaction, and all of them bring some polarization losses. A way of reducing some of them is the introduction of catalyst nanoparticles inside the electrode that are going to have a positive effect both in the resistive charge transfer process and the activation components of the polarization of the electrode. We have done this with different metal oxides, for example, praseodymium oxide, manganese oxide, and we can see here in this plot the effect of introducing praseodymium oxide into a conventional cell made with lanthanum strontium manganide cathode. In the voltage intensity curves, we see that the dotted lines are the standard cell, the continuous line is the infiltrated cell. We see that we improve the performance quite significantly by introducing these nanocatalysts, and this means, for example, that we could reduce the operation temperature, if we were interested, in about 100 degrees. This is the curve at 800 degrees for the infiltrated cell. This is the curve of the standard cell at the same temperature. Reducing this operation temperature has a very important effect on the durability of these systems. If we look at this, one of the main problems of these cathode, the materials, is that there is, with time, there is segregation of some elements, mainly strontium, to the surface of the electrodes. And we see here how reducing the temperature, how decreases this segregation enormously. So the effect in durability is quite good. If we look also at the reversible mode, so both working, the system working in fuel cell, as an electrolyzer, we see that our systems are completely reversible from one mode to another mode. And we see that how introducing, in this case, 2% of manganese oxide nanocatalyst, we can reach the highest reported performance values for microtubular cells in the literature, much higher than other cells using more advanced, in theory, electrode materials. We are also going a bit further, and we say, okay, all these carbon capture and storage technologies, we are now able to separate CO2. Some of our membranes that I was talking at the beginning in the first slide can be used for this separation of CO2 in these systems. We can capture, we can transport, we can store the CO2, but this is not a long-term solution. We are trying to look for other uses of this CO2 apart from storing it, and we are exploring the co-electrolysis of CO2 and water in our systems. So this is just an ongoing work. It's not finished yet, but I can say at this time that we are getting very, very promising results with our cells working in reversible mode in the CO2 water co-electrolysis, which could be used as a way of using this CO2 that can be captured from other applications. So just to conclude, I hope I've been on time. This is the team I would like to thank. This is the people involved in this work, and all the funding that has been used for these research lines. And of course, thank you for your attention.
Thank you very much, Aloia, for this interesting talk. It's open, the talk for questions. Any question?
Thanks, Alodia. It was very interesting. I don't think I've seen before the structuring with the laser in the garnet.
Mm-hmm.
So I don't think I asked you this question before, but have you checked if amorphisize or if it loses lithium, reduces, or do you have any chemical or structural information?
We have checked mainly by Raman, okay, because we think Raman is a surface technique, and also is very can detect very light elements, as you know. So we are quite confident that we are not changing the structure of the material. Of course, the conditions of the laser processing has to be very quick. Mm-hmm. So you have ablation, no, you don't have like a fusion and evaporation. So it's ablation, so it's very quick. Mm-hmm. So you don't change the material around, okay, nor even in the channel where you extract the material.
You don't cool it down, no? Like you don't.
No, you don't need to cool down. No.
Okay.
No, it's room temperature.
That's great. Thanks.
Thank you. Another question from the audience?
Thank you, Alodia, for a very interesting talk. And I'm again with the laser sintering and all the possibilities. It is open with the laser sintering. So my question is about if you try also with electrolyzer of fuel cell based on proton ceramic conducting oxides, and if it is worth in these cases, because this is a great problem of sintering, and maybe lowering the temperature would be really interesting.
We haven't checked any sintering. In fact, that's the part of this new project that has just started. With ceramic proton conductors, we have done ablation in the past for other applications, for other kind of membranes, not for fuel cells, but for gas membranes. And we have done ablation, that's sure, but we haven't tried sintering yet.
Make the sintering at lower temperature, and also to be compatible maybe with some metallic support, so that may be really good. Yeah, thanks.
Any question?
mentioned that you got record numbers in electrolyzers, but I don't have. I didn't get if it is because of the new material that you are using or the new processing method, or what is the key of this success?
The nanocatalyst.
The
nanocatalyst.
The catalyst that you include,
Yes.
but other authors also include catalyst in their formulations,
Well,
right?
this is a record in microtubular cells.
Okay.
Microtubular cells
That
normally.
I guess is a narrow field of research, right?
Well, not so narrow.
No,
narrower
I'm
than
out of the
narrower than the
I'm
broad
out
spectrum,
of the
but-
field, so
Yes. No, there are two different architectures, so microtubular and planar. So normally microtubulars are a bit lower than planars in literature. So inside this field is a record. It's almost comparable with planar cells at the moment.
And what is the advantage of tubular?
Well, mainly the seals are much easier because you can seal the cell in a cold region. So seals are much easier. And also the thermal shock resistance is also much better. Cylinders are mechanically robust compared to planar thin surfaces.
Thank you so much.
Any more questions from the audience? Okay, so we thank the speaker again. Our next speaker is Dr. Blanca Isabel Arias from Iberian Energy Storage Research Center in Cáceres.
In Cáceres. Sí, yo creo que... Hello and good afternoon, everyone. And first of all, I would like to thank you, Bitham, Alejandro, and all the organizing committee for this invitation to participate in this talk. So, as said, my name is Blanca Arias, and today I want to give like a little details about a work and the potential of a piece of work, and this is correspond to the potential of strontium vanadate and strontium titanate anodes for the operation of solid oxide fuel cells fed by biogas, and present the recent advances. So this work started already back in Aveiro, in the University of Aveiro in Portugal, and is still going on now at CI, where I'm still now currently working. So let me first take a few minutes, since CI is a new center, so to give a few words about this center. So as said, CI is a new center, it's an Iberian center. We are not the only one. We have like a little brother, let's say, and it is the INL, the Nanotechnology Center in Braga, that was created in 2005 in Portugal. And now in 2022 was signed a pre-agreement to construct and to develop the second Iberian center, which is CI in Cáceres. And the pre-agreement was signed the 4th of November of 2022 by the government of Spain and Portugal. So has an initial funding of 80 million euros. So far, so good. We are really new, but we are already more than 40 researchers and engineers, and we expect to reach 135. These are the plans by 2025. The scheme, apart from this funding, from this government funding from Portugal and Spain, this has a funding, a combined funding strategy, combining public and private funds. And again, we are new, but we are already present in some organization at an European level. For example, the Hydrogen Euro Research and the Energy Alliance, the ERA in Europe, and or the Batteries European Partnerships, and some others in Spain, such as the Platform for Hydrogen and the CO2 Platform, Battery Plat, or IPPAL. So the idea is just to come and collaborate and with all the ecosystem, research ecosystem already in Spain and of course internationally. And this is the plan. So we are now located at the University of Extremadura. But this plan here, it is already in construction. So this is 3 buildings, as we can see in the picture now. There will be a main building with the research laboratory and offices for researchers. There will be a building for the pilot plant here, and there will be another building as a business incubator for the companies wanted to be located close to the researchers to develop together some technologies. Briefly words about what TI it's gonna be doing the next, hopefully, many years. So this is divided in three pillars of technologies. The first one is electricity storage. Here the colleagues will be developing materials and solutions for advanced materials of metal air, zinc-air, lithium-ion, sodium-ion, and flow batteries, as well as a concept related with circular economy and supercapacitors. There will be a second pillar related to the whole value chain of hydrogen and power-to-X technology. Here the colleagues, including myself, because this is the area where I belong to, I will develop solutions for electrolysis and fuel cells, both at low temperature and high temperature, which is my topic. Also the hydrogen storage and transport in relevant molecules. For example, here we have some examples here in metal hydrides, adsorbent materials, liquid organic hydrogen carriers, ammonia, methanol, and some other molecules which are of interest. And then the last two is the CO2 capture and utilization, and the last one is the producing of chemicals and synthetic fuel using this capture CO2 and the produce hydrogen. And the last one, there will be colleagues in the thermal storage department developing solution with regard to the materials. We have capacity to storage in the long term and short term storage for sensible heat, latent heat, and thermochemical heat materials. Apart from these 3 pillars, there will be let's say an horizontal area which is correspond to the pilot plants. There is 5 already planned at CI to develop all these kind of technologies, 1 for flow battery, 1 for hydrogen and power-to-X technologies, 1 for thermal storage, another 1 for circular economy and recycling of batteries, electrolysis and fuel cells, and the last one, this is a microgrid to integrate all these technologies into the grid and simulate it into the renewable energy system in different conditions. I would say that one advantage of TI may be one particularity that will be there will be round tables of researchers in different disciplines, and in this regard there will be also horizontal tables for people interacting and developing and trying to scale up solution. So there will be a group related to the, let's say, the lowest TRL level, synthesis and characterization of advanced materials and also prototyping the solution. The second one, there will be also a team of people collaborating. So these lines are neutral, let's say, from a technological point of view, and will collaborate with everyone in modeling, including atomic and materials and CFD modeling. And the last one will be the colleagues related to the life cycle assessment, techno-economic analysis, energy system analysis, and regulation. So I will say this is opportunity to all interact together. And now just come back to the topic of the presentation. As said, this is a collaboration between Aveiro, where I was working for several years, and this will be continued at TI. So starting just few work about biogas and why biogas with solid oxide fuel cells, or normally biogas, and this is according to the last report of the European Biogas Association, it's mainly used in combined heat and power plants, which is really, really low inefficient technology with efficiencies below generally 40%. And as an alternative, instead of doing this purifying and polishing of the, to obtain methane, which is quite highly demanding, one alternative can be the utilization of pure biogas in a solid oxide fuel cell, taking the advantages of the flexibility of the fuel in this kind of technology. Of course, we have some additional challenges if we want to go this way, and some of the main challenges are related to the huge electrode degradation here, mainly because of carbon deposition, sulfur poisoning, the slackness of the electrochemical reaction, and the thermal stresses occurring in this kind of operations. If we go to the conventional, let's say, anodes in solid oxide fuel cell, nickel YZ, they have some pros and cons. So they are reported to exhibit a very good electrocatalytic activity for hydrogen oxidation, and as well as a high electronic conductivity. However, it has some drawbacks. For example, the most common drawbacks, they are known to be extensive volume changes in redox cycling from nickel to nickel oxide and vice versa. And this occur together with a big microstructural instability, such as here we have some example. Oops, sorry. We have some example here of cracking and delamination. And in addition to that, in biogas-fed operation, these materials suffer from really fast cooking and sulfur poisoning, which really spoil the performance and electrochemical performance and make these common anodes impossible to use in this operation. As an alternative, and without going deep into the state of the art, just one of most last promising anodes in this operation are perovskites. Here are some example, chromides and molybdates, vanadates and titanates, and some years ago, we just select these vanadates and titanates and try to make a system out of them. Because we just saw that has a really good resistance to sulfur poisoning and carbon deposition, which is really two of the main challenges faced in this operation. Starting with the vanadates, they have a high electronic conductivity under full electrode operation. But we have a drawback, a really significant drawback, which is the limited stability. So they have really easily decomposed when exposed to air and oxidized into strontium-2, vanadium-2, oxygen-7. And this oxidation goes together with a strong dimensional changes in operation, which make, again, this kind of materials alone not suitable for this operation. On the other hand, we have the donor-doped strontium titanate perovskites. Here we have this material are known to be really stable in a wide range of oxygen partial pressures and have good thermomechanical properties which match one of the YZ, which is the common electrolyte in solid oxide fuel cells. But on the other hand, this has the main drawback to have a really comparatively low electronic conductivity, about 10 Siemens per centimeter. So the idea of this piece of work I would like to present here today. So it is just going and take these two systems to look for a compromise between high conductivity of strontium vanadates. So this was the driver of the design of the material and the good stability of the strontium titanates. So far, we already check some facts and some realities, and regarding the solubility range. So it is, what? Here. So there is really an entire range of solid solutions of titanium and vanadium in this system. This was synthesized and in reducing condition, starting from raw oxides. And all has a cubic, in principle, perovskite structure, and there is no evidence of any impurity. So this is a full range of solid solution. What happened with the electrical conductivity? We also observe something. And here we have the system. So what we observe is when we increase the content of titanium, the conductivity naturally and dramatically goes down. And this also substitution of titanium results in a gradual transition from here a metallic behavior to a semiconducting behavior. For example, from only 10% of titanium, the conductivity is quite moderate, 100 Siemens per centimeter, and already for intermediate composition goes down to 20 Siemens per centimeter. So really, really makes an effect of decreasing the conductivity. The same we observe for phase stability. So again, we confirm the same that we were looking for. So the stability of the strontium vanadates, so they compose quite at a relatively low oxygen partial pressure, and we observe and we prove and we just as was result. So titanium substitution result in a really nice gradual shift of stability boundary, making the material and the solid solution more and more and more stable at higher PO2 levels. Nevertheless, there was not so all good news, and there was also observed some irreversible changes in air. So after processing the materials in reducing conditions, we put it in oxidizing conditions, and here it is what happened in terms of conductivity and TGA here. So what happened is, after reducing, we expose it to air, and it seemed to decompose, and when we go back to reducing conditions, seems to apparently conductivity goes back again, and the mass go back again. But in reality, what we have is, at the beginning, we have a single phase perovskite, but after reduction, there is like irreversible change, and we make a separation between two phases, one rich in vanadium and one rich in titanium. That was that we make some decisions, and we just go for a different approach and try. The second thing was just to try to keep moderate vanadium contents to make the material stable enough and with moderate conductivity, and prepare the materials directly in air, and assume that we have a composite and we don't have a single phase material at the end. So here the phase composition. So now, as we can see here, we prepare the materials in air. And here, so what we observe by XRD, sorry, here, XRD, we have like a composite made of the main strontium titanate and two oxidizing vanadium phases, one strontium 2 vanadium 2 oxygen 7, and so one pyro and one orthovanadate here. That was also confirmed by observation. This is the microscope, sorry, the microstructure, and here we have the segregation, indeed, of these blue titanium phases and these two mixed together of vanadium-rich phases. So what happened with the conductivity then after reduction? We prepare a set in air, then we reduce the material again. So we observe the really increase of conductivity again, as we expected. From oxidizing to reducing condition, being the most conductive, so the conductivity reached moderate values of 3 Siemens per centimeters with vanadium contents of 0.3. The same was observed for the TGI. So what happened when we heat the material in hydrogen? This is an example at 1,000 degrees C. We observe a slow reduction and relaxation processes. Yeah, so that's the reason is after XRD, we just made the confirmation of the transformation of these strontium vanadate phases into these rich other vanadates, so transforming into a strontium vanadium. So I'm going a bit fast. And the microstructure, so what we got is a huge agglomeration of vanadium phases. Now I will share just little bit tips of how we could improve the performance and electrochemical performance of the material. So we have huge agglomerate of vanadium in a prepared sample. We try to mill to try to improve the conductivity. We succeed in this operation, so that's makes a point of the importance of the pre-processing and the possibilities we have. So then that was proof that from 3 to 10, after just simple milling, trying to make a better dispersion of the vanadium phase into the strontium titanate. And the last part of the presentation is just some electrochemical properties of the material. So making symmetrical cell using YSZ, or what it is, YSZ here, electrolyte 1 millimeter. This is how it looks. This is electrolyte and this is the electrode. So some just very, very few pictures. So we have here the impedance, and we have the polarization resistance and the ohmic resistance of this material. So best results was obtained for intermediate. We have for the higher temperature, unfortunately, we have an increase of reactivity. So again, it's not, so agglomeration of vanadium phase, probably melting of this phase, which is now shown in the screen, and the formation of the strontium, zirconium, strontium dysperoxide, which is isolating. And yeah, lowering the temperature is not good because we have better, not good addition, so this is the reason to have not good result. But this result, again, is quite competitive, but still we could do, so this is just an example how looks the electrode, and we can still go further, and this is similar to what the previous speaker presented. So this is the infiltration approach. In this, we are showing here the filtration of an ionically phase plus a catalyst, which is the nickel. And this is a really, really huge improvement in the decrease of the polarization resistance, which is a way to go. And we can still are planning to infiltrate a different type of catalysis, not only nickel, but vanadium, molybdenum, and so on. And the last approach we try is play with the sintering profile, so make like a fast heating, not maintaining in time, just to promote addition, and then just keeping for a long time here, just to prevent the reaction. And again, here that looks a promising approach as well, especially in the low temperature ranges. We have quite, let's say, competitive values of polarization resistance. And that's the conclusion. So maybe I can skip just reading the conclusion, but just going for the takeaways. So there is still plenty of room to improve this system, but not only this system, but other similar systems for solid oxide fuel cell with biogas, maybe with ammonia as well, and another kind of fuels. And yeah, the importance of preprocessing, so it is always something to do next. And yeah, so thank you all for your attention. Thanks all collaborators, especially people from Aveiro, Javier Macías, Jorge Frade, and Alexei Yarenchenko. And thanks now my new colleagues. So this is the only one photo available. So that was our only and first lunch in Christmas. And yeah, so thank you all again. And sorry for the delay.
Thanks, Blanca, for your presentation. I was a bit surprised when you are doing all of this to avoid nickel, no, in the anode, in the fuel electrode, and then when you end up infiltrating catalysts, you choose nickel. So why do you choose nickel? And if you don't have any carbon deposition problems over these nanoparticles?
Yeah. So far we choose nickel, and we start with nickel because was the better. So the better result was with nickel, unfortunately. And yeah, we try a different more catalyst. We try molybdenum, we try vanadium, extra vanadium. We tried some kind of copper. Result so far was not good, but we are still trying. So yeah, unfortunately, nickel was the best one. And yeah, so we try to keep, just to say something for the good of the job, so we try to keep the amount really low. So I was a bit fast over the last part. So here it is between 5 and 10% in weight percent. So we try to keep it a small quantity, and we also play here with the cation ratio between cerium, gadolinium, and nickel 911. So we make some tests, but so far nickel was the best.
So at least you avoid the problem with reoxidation, with the change in volume.
Yeah.
But I guess the carbon deposition you will have it quite.
Yeah, that's yeah. So now the next step is try to make some tests with biogas. Try to make some not only symmetrical cell but some full cell working with biogas to see maybe degradation.
Any more questions from the audience? Okay, I have one. It's about when you make when you have a degradation of your your solid solution and you have more vanadates that are segregated, you know the properties of these materials?
Yeah, so the strontium zirconate is isolating, so this is why it spoils the behavior at high temperature sintering electrodes. And the vanadium is a good electronic conductor, so that's maybe a good point, so this is beneficial. And the strontium titanate acts more like a skeleton of compatible and chemically compatible skeleton with the vanadium phase. So just to keep this compromise, yes. So, but yeah. So one way to go, it's also now can be try to synthesize these two materials, since we know this is composite separately, and have a better control of the particle size and so on, and then mix up together in a maybe a more optimized ratio. Yeah.
Okay, thank you very much. Any more questions? So we thank the speaker again.
So, hello everyone, that concludes the session number 3. And now we already had the coffee break, so now we are directly moving to the session number 4. So before going to the session, so one news is that Professor Julie from MIT, he has to go to China for a sudden trip, so he can't come. But he sent a presentation to us. I can play that presentation. It's a 40 minutes, so it's already late. Anyways, this year I will gonna work with him, and I will maybe share some news with the research of him. Anyway, so now we move forward to today's conference. I kindly ask my colleague, Cynthia, to assume the role of session chair and bringing her expertise to guide us through the upcoming discussions and presentations.
Good afternoon, and thank you for attending this last presentation. And now I would like to welcome Dr. Ainara Aguadero from the Instituto de Ciencia de Materiales de Madrid, and she will present factors affecting interface ion kinetics in all solid-state batteries. Thank you.
Thank you very much for the introduction and for inviting me to be here. It was great to see some friendly faces that I haven't seen for a while, and to engage in the interesting discussion also. So what I wanted to discuss with you today is how the interfacial addition between two solids is key when we are developing all solid-state batteries, and keeping that good interfacial addition can prevent the formation of current constrictions and the premature death of these devices. So I wasn't going to discuss very much why all solid-state batteries, because I had a previous presenter that I thought was going to introduce the matter, and a lot of you know what it is about. But at the end, what we want is to substitute a flammable organic electrolyte by a solid that isn't flammable, trying to increase the safety, although this is something to study in more deeper detail. To be honest, we don't know exactly what are going to be the safety hazards, most of all because to gain in energy and power density, we really need to substitute the carbon-based negative electrodes by alkali metals. And that is another hazard that you have to include into your system anyways. So even though there are some advantages, so if we manage to include these alkali metals and cycle these cells in a safely way, we are introducing a lot of trouble. And this is associated to that we have created a lot of complex solid-solid interfaces that can generate a lot of problems in the systems. And this can be associated to the fact that we are putting together two dissimilar interfaces. We can introduce some contaminants in our processing. Voids can be created because contact is not perfect. The dissimilar interfaces can react. We can form secondary phases that can have higher resistance. But then also we start cycling and we start having change in volumes. And how a rigid structure is going to accommodate that is a question to be solved. And generally what we have is the creation of a lot of voids that leads to the formation of current constrictions that eventually leads to the formation of dendrites and death of the cell. Yeah, sorry. So in our group at the moment we are working in solving the problems in both the positive and the negative electrode, but today I'm going to focus on the alkali metal solid electrolyte interface, and specifically in how to keep this interfacial addition between the alkali metal and the solid electrolyte so that voids are not formed so easily and dendrites are not formed so fast, and so we can try to avoid this premature cell of these cells. So since we are talking about interfacial addition, that is like the tendency of two surfaces to remain together, and this is associated to the surface chemistry of the surfaces and the bonding that is established between them. No? So how is that interface, what is thermodynamically how those interfaces are, is going to determine very much how they interact and how the weighting is going to behave. So if we are looking to interfaces that are non-reactive, when we are looking to alkali metal like lithium or sodium with other inorganic materials, there are very little examples of those. But we have some examples of kinetically stabilized interfaces, and this is the case of the garnets or the sodium beta alumina with lithium and sodium metal respectively. In this case, we have a non-reactive interface, and so we have a non-reactive wetting happening. When both interfaces are put together, they have a driving force to react, they start reacting, and depending on the interface that is formed between them, they can either continue to react, as it happens, for instance, with LATP, in which, in contact with lithium metal, it will reduce until it's completely decomposed, or it can form a stable interface that is self-passivating, as it happened with the organic liquid electrolytes, for instance. And in that case, depending on how that interface is, we can create a stable interface that then has to wet both the alkali metal and the solid electrolyte in both cases. We have another possibility that is also that we artificially are manipulating our surface chemistry and to create interlayers that either lead to a non-reactive or reactive wetting, depending on what we are looking for in our system. I'm going to talk to you about two cases. One is non-reactive and the other one is reactive, to try to see what are the factors that are controlling in both of them. So a non-reactive case, as I mentioned before, is when we are looking to the garnets. So the LLC2 typically has a very low driving force for reaction with lithium metal, and so it's kind of kinetically stabilized. And so what we have observed is that what is dominating the wetting between the lithium metal and the garnet is the presence of contaminants at the surface. So in the garnets, the good thing is that they have very good lithium mobility in the solid state. They can have around 1 millisiemens at room temperature. But that also leads to a high reactivity with moisture. And it forms lithium hydroxides and lithium carbonates. And so the good thing is that when this lithium carbonate is forming the surface of the garnet, we can eliminate it and clean the surface. And that allows us to study how the wetting is changing depending on if the surface is clean or not. This can easily be done by heating. Yes, you can heat up to above 600, you already clean the surfaces. And you can use different techniques. In this case, we use secondary ion mass spectrometry to study the surface chemistry to bulk change. No? So here we are sputtering from the surface to the bulk, and you can see here when we still have the lithium carbonate on top of the garnet, we have a lithium-enriched surface. The rest of the elements are not present because are covered by the lithium, and we have to sputter through to the bulk to start seeing the rest of the elements, and then we have the bulk. When we condition the material, we have a flatter profile because we don't have a segregation of lithium on the surface. We can follow that also with XPS because at the enzymes that gives you a chemical information but not a chemical environment. We don't know the form of the lithium. No? And so here we can see that when the degradation has happened, we see carbonates present that are eliminated when we heat up the samples, and we can do that in situ by XPS easily. What is interesting to see is that when you take a liquid lithium metal and you put a drop on these surfaces, what you see is a big change in the wettability. So when you have a lithium carbonate surface termination, we have a much worse wetting than when we don't have it. And this is directly related to how the impedance looks, so how the polarization resistance at that interface behaves. So we have very large polarization resistances when we have very poor wetting, and when we condition the sample, we go down, and we can see here that the resistance at the interface has decreased several orders of magnitude. What is interesting is that also it has been proven that this resistance is not even associated to how resistive it is for the lithium ion to go from the lithium to the garnet, but it's associated to that there is still some voids. And if you apply enough pressure to the system, you avoid these voids and you go to interfacial resistances that are zero. It's only when you start cycling that you create voids again and the resistance starts increasing again. And so if you don't apply pressure upon cycling, the resistance will increase. But if you do apply, it will keep constant, zero, and it will be fine. What is the problem? That you have to keep apply pressures of 35 megapascals in a cell that, you know, maybe for commercialization of the cells is not so easy. And if we don't apply this pressure, the presence of these voids makes that the dendrites grow very fast. So even for currents of around 0.1 milliamps square centimeter, we start having the death of the cell due to the growth of dendrites. So non-reactive wetting, it looks good, but it's not so good. We have another case scenario, and this is the Nasicon. The Nasicon with the sodium metal. In this case, the sodium metal and the Nasicon will react. They are not thermodynamically stable when we put them in contact. So we are going to look at a reactive wetting. And what I'm going to show you is that depending on your surface chemistry, that reactive wetting is going to behave in one way or another. And so controlling the surface chemistry, maybe we can control how the system behaves. And this is thanks to a work that we did with Jülich. So Quan Lima and Frank Dietz developed an acetone with very high sodium conductivity that had an excess of sodium and phosphorus, of a sodium phosphate. And thanks to that, when you were thermally activating this system, the Nasicon was growing with a surface termination that was sodium and phosphorus rich. The good thing is that you can have this sodium and phosphorus rich termination when it's thermally activated, but then you can polish it down and you have your book and you don't have any surface termination anymore. You can follow that with different techniques. This is an example of the XPS that we analyzed, and you can see how the sodium and phosphorus enrichment decreases when you polish the surface. And you can also do a more surface sensitive technique that is low energy ion scattering that proves the first monatomic layer composition, and then you can spatter and go a bit deeper. But you can see here that when we look at the surface, we only see oxygen, sodium, and phosphorus really, and we have to spatter them to start seeing the rest. So you have the surface termination until you annihilate it. What is interesting is that when you put this Nasicon sandwich in between two sodium metals, so you do a symmetric cell, and you look at the resistances that you get, you could have the bulk grain boundaries of the interface resistance, and what we see is that the bulk contribution, we don't see it because it's very fast in the frequency range that we are looking at. For both cases, we see a grain boundary resistance, but when we have a thermally activated pellet, we cannot measure an interfacial resistance. We do have it, it's below 1 ohm square centimeter. When we polish out this surface termination, we start having resistances that can vary depending on how deep the polish goes, from 20 to 1,000 ohms square centimeter. This is directly related to how the cell later behaves and how fast it dies. So when we don't have polarization, or we have polarization resistances that are very low, we can go up to 8 milliamps per square centimeter, which I remember that in the case of the garnet with lithium, we were in 0.1, starting to grow then, right? So it's a big change. It's also sodium, has a better mechanical properties. The creep is much better, it's more malleable, and that makes a big difference also. But the system behaves much better. And when we start polishing down, we start having much lower critical current densities. So trying to understand how that interface is, we did an operando XPS experiment in which what you do is to place the sodium metal underneath the Nasicon pellet, and you use the electrode flow gun of the XPS as a virtual electrode. So you float electrons to the surface, create a surface potential, forcing the sodium to go and plate. And that allows you to plate very little sodium metal, so you still can see the interface that is forming underneath with the XPS. So you follow the formation of the interface. This is what we get when we have the float can off. So this is what the Nasicon looks like in the XPS. And when we start allowing the sodium to plate, we start to see how the sodium metal start to grow and the rest of the elements start to decrease. We are going to look at that in a bit more detail here. So this will be, what we are looking at here is that we are supposing that we are growing sodium metal, underneath there may be or may not be a growing of an interface. And we are going to try to understand how this is happening. For that, we measure first the sodium, the Nasicon bare Nasicon alone, and analyze it properly. And also, we analyze properly the sodium metal, the bare sodium metal alone, and analyze it properly. And then we feed the spectra. And what we see is that apart from the peaks associated to the zirconium and the sodium that is leading to associated with the sodium metal and the Nasicon respectively, we have also the formation of some interfaces there. Some interfaces there. And so what we can see here is that how the sodium metal is plating, how the rest of the elements, the area of the rest of the elements is decreasing, and how the interface is growing with time. In this case, I didn't say it before, but we are looking at the Nasicon in which we have polished out the sodium and phosphorus-rich layer. And we are going to compare now both of them. But the conclusion that we can subtract is that the Nasicon is not stable against sodium metal, as we knew, is reacting, is forming an SEI layer, and that SEI layer is eventually stabilizing. It forms, and then it does stabilize the concentration. So if we compare when we have a sodium phosphorus-rich surface termination when we don't have it, what we see is that first the amount of degradation that is happening at that interface is much lower. If we look to the kinetics of formation, we also see that whereas for when we don't have this sodium and phosphorus-rich surface, we have a growth of this interface, and it takes a bit longer to stabilize, to self-passivate. For the case of the sodium and phosphorus Nasicon, there is a straightforward formation, and it's stable for the whole experiment. And I mean, it makes a sense in a way. I mean, the Nasicon is expected to react with sodium metal, but the sodium phosphates, depending on which one it is, which we don't know, because it's not structurally easy to characterize the material, they are not supposed to react with sodium metal in any ways. What is interesting is that we can also correlate this to how the impedance is behaving with time. So when we look at a system in which we don't have an optimized surface chemistry with the sodium and phosphorus rich, we start with an impedance, and this impedance increases until it stabilizes in a longer time. Whereas when we have this surface termination, it's self-passivated much sooner and it doesn't grow so much. It's much thinner. In both cases, we do believe that we have the formation of a small SCI. In one case, it's much thinner, allows much faster transfer of the sodium ion, and in the other case, it grows for much longer. It's a worse SCI layer. But what is more important is that at the end, this effect makes this system behave much better and allows for much higher critical current densities before the cell die. So I guess the most important message here is that reactivity is not always bad. Reactive wetting actually is better. It allows a better wetting if you can control it in a way that you form an interface that is good enough for you to see. But what is very difficult is to really be able to identify what is going on in the interface, and so we need to develop more high-resolution operando analysis that allow us to really look at these dynamic interfaces properly. I just want to thank you for your attention and acknowledge the work that has been done by this group of fantastic people. The XPS analysis was very rough, it was very difficult, and it was a protocol developed by Nicholas Williams that if you want to use is available free and is here. So yes, that's for that. Thank you very much.
Nice presentation. We are now open for questions, for discussion. Yes.
Excuse me, I am not specialized in solid electrolyte, and I wonder if did you try to, because the melting point of sodium is fairly low, to melt to create a good interface?
If you melt it, you can go to huge critical current densities. So it really is very controlled. The critical current density is very controlled by the formation of these voids, and if you melt it, the formation is almost annihilated, and you go to huge critical current densities. You do. I haven't done it, but it's been published by Jürgen Janek. It happens the same with lithium and the garnets. You have to go a bit high in temperature. Yes. Yeah, but yeah, definitely temperature is a factor that is fantastic. The only thing is that not for all the applications that you need to use a battery for, you can actually maybe, or you want to be at higher temperatures, and then you have the leakage problem that theoretically was one of the good things of the all solid-state batteries, no? That you avoid, and suddenly you have a melted, reactive alkali metal there, and so that's why now the idea is to try to go through the way of surface engineering and trying to achieve that through interfacial addition.
But if you plan to use this sodium battery with solid electrolyte grid scale, do you think that is the best way is to use the ceramic directly in contact with the sodium metal, or to use the so-called hybrid, mixing the ceramic powder into a polymeric matrix?
We are working in both things, to be honest, because at the end there are so many things. It's mechanical, electrical. There are many things to consider. One thing that I think that is good is like the garnets are very stable with lithium, and that you can understand it well and the nasicons now they are well understood. So I like them because of that. So I will continue to develop these kind of cells because that side we understand well and we can go farther. So Christina is going to present now. We are now going to anode free with these systems in which you can play with the surface to improve. And so.
Thank you. Any more questions?
I have some curiosity. Just why did you choose this composition just from the nasicon?
For the nasicon, it was a coincidence. So we were, Frank Dietz came when I was at Imperial to visit us, and they developed that nasicon with that composition, and they were having a lot of problems understanding what was going on because sometimes they were polishing and sometimes not, and they were having very high resistances at the interface or very low. And so we started collaborating with them and trying to understand what was going on. And eventually we discovered that to be able to densify them, they were adding some excess of sodium and phosphorus. And with surface analysis, we detected that there was a different surface chemistry, and then everything started to connect. So, but it was coincidence, and we work with them because that composition has a fantastic sodium conductivity. Yeah. So it's like 5 millisiemens, I think.
Yeah,
so
it's really good. No, especially because we have some experience with the same, similar composition, but doped with yttrium. And so in fact, this reduces the grain boundary. And then I guess that this is exactly the same case. No? Probably the total conductivity is really very low. No? Okay, thank you.
Thank you. Any more questions? Okay, we thank you again for your presentation. And now we are starting with flash presentations.
Your presentation copied you? Copied? Okay.
Okay, then we welcome Cristina García from Instituto de Ciencias y Materiales de Madrid, who will present engineering of interfaces on sodium solid-state electrolytes for anode-free batteries. Whenever you want, thank you.
Hi, I'm Cristina García. I'm a PhD student at Instituto de Materiales here in Madrid. And the topic of my talk would be the interfaces on sodium solid-state electrolytes for anode-free batteries. Well, anode-free batteries generate in situ the metal-alkaline anode during the first charge of the battery. So it improves the safety and cost effectiveness by eliminating this reactive alkaline metal during assembly. So, challenges include a significant nucleation overpotential and an inhomogeneous distribution of this metal anode in the surface of the electrolyte, highlighting the need to study interfaces of this electrolyte and to improve the adhesion and have a better anode nucleation. So, to start, we have to study the electrolyte that we are going to use. In this case, it's a sodium nasicon type solid electrolyte. And, well, it has been synthesized by solution-assisted solid-state method. To characterize it, it has been mainly by XRD and Rietveld adjustment, revealing that we have a two-phase mixing, with a monoclinic phase being predominant in the structure, but we have also a rhombohedral phase as well. To the electrochemical characterization, we have done impedance measurement with blocking electrodes in order to know the total ionic conductivity, which is 1.8 millisiemens per centimeter in this case, and an activation energy of 0.37 electron volts. Well, to start with the study interface, Ainara have just talked about this, but we are studying the interfaces between the nasicon and the sodium metal. in order to reduce this resistance and improve the wetting. So we have compared 3 symmetrical cells, one with the pellet as sinter with this sodium nasicon phosphate layer, which grows when sintering the pellets, then one polished, and another one annealed after this polishing. So we can see a huge difference between the 3 of them, because in the polished one there is a huge resistance. Then in the as sintered, we don't see any resistance at all in the interface. And in the annealed one, there is resistance, but it's so much lower. So we can say that this sodium phosphate is growing again in the interface with a thermal activation of the pellet. Then we start with anode 3. In this case, we choose the annealed surface and did a gold spattering on it with a thermal treatment of 450 degrees for 5 hours in order to create gold clusters to facilitate the nucleation of the sodium and reduce this nucleation over potential. We can see that before the first plating we have these gold clusters on the surface and the resistance is very high. But when we start plating this sodium, the resistance is starting to decrease as the area is increasing. And after the first plating, we can see that the resistance is so much lower. Well, also say that the nucleation over potential in this case is very low. It's only -7 millivolts in the first plating. And well, we have cycled this cell, and at the first cycles it seems to be stable. Well, as a conclusion, the electrolyte was correctly synthesized and characterized with a total conductivity of 1.8 millisiemens per centimeter. We used the thermal activation to optimize this interface between the sodium metal and the nasicon. And well, this solid electrolyte with gold clusters current collector has been used in these anode-free batteries and verified that the sodium has nucleated properly in the surface, and we have cycled this cell successfully. And I would like you to thank you for your attention.
Thank you very much. Do you have any questions, please?
Just a curiosity, the role of gold here is just is mainly current collector or is a nucleation agent, and in that case, if it's the best option to have gold, or you can think of other metals.
Well, in this case, it acts as a current collector, but also with these clusters helps the nucleation, because if we have an homogeneous layer of gold, the sodium will have to push up this layer to grow. But with these clusters, we have the current collector, and also we have like space for the sodium to grow. And we are not sure now, but probably the gold is alloying with sodium, and this also helps to decrease this nucleation over potential. And yes, of course, we are thinking about using other current collectors or oxides or something to improve this nucleation of the sodium.
Thank you. I'm sorry because I'm not familiar with this research, so maybe my question is very naive. What is an anode-free battery? You can have a battery without anode, or?
Yes, you only have the positive electrode, and you grow this metal anode, in this case is sodium metal, in the charge of the battery.
So this is an in situ anode.
Yes.
So you start with that anode, but when you charge your battery, you are creating the sodium anode. So
Yes.
it's a battery with anode.
Yes.
In situ generation of anode. let's
Yes,
say.
because when
Okay.
you do
Okay, okay, I understand now. Okay, you are cycling. Okay, thank you.
well.
Any more questions? Okay, thank you very much for your presentation. Now we can welcome Said Azerblu. Please.
Can I insert this one?
Yes. Okay, Said Azerblu, he comes from University Hassan II of Casablanca, and he will present phosphate-based electrode materials to boost the electrochemical performance of sodium-ion batteries. Thank you.
Thank you very much. Hello, everyone. I am Said, PhD student at University Hassan II of Casablanca, Morocco. I am working on phosphate-based electrode materials to boost electrochemical performance of sodium-ion batteries. So my presentation plan is I will start with an introduction, then I will be talking about the phosphate-based materials used in sodium-ion batteries, then the challenges and the opportunities of these materials in sodium-ion batteries. I will wrap up my presentation with a conclusion and a perspectives. So, as you know all, the world population is growing, so the energy demand will be doubled by 2050. Energy demand increasing, that means that there will be a giant CO2 emissions. The giant CO2 emissions will lead to climate change and global warming. So, to avoid this global warming and these issues, we should switch from fossil fuels to renewable energies. But the problem is that these renewables are fluctuating. They are not stable over time. So we need to introduce storage systems, storage batteries. The problem is that with the increasing of the cost of metals, these batteries will be more and more costly. So we need to search for sustainable batteries with sustainable materials that are more cheaper than the traditional ones. Among these materials are the phosphate-based materials used for sodium-ion batteries. These are some timelines of the using of phosphate-based materials in the batteries, starting from 1976 with the introduction of sodium intercalation. Then the research are continuing over time to arrive to introduction of Nanostructured type batteries with that containing fluor. The most studied phosphate-based materials are orthophosphate, Nanostructured type phosphate, pyrophosphate, fluoride phosphate, and mixed phosphate. These are some materials used in batteries, including ortho and Nanostructured type phosphate, specific capacity with the range voltage. This for pyrophosphates with the functional materials of P2O7. that fluoride in mixed phosphate. Then I will be discussing the opportunities and challenges of using these phosphate-based materials in sodium-ion batteries. These phosphate-based materials are promising candidates for electrode batteries due to high structural stability, due to very strong PO bond. Then the 3D framework of this phosphate can introduce, which can receive the ions, sodium ions in the battery. Also, that benefits the structural stability of these materials. Then these materials offers a long cycle stability, appropriate operating voltage, a thermal properties due to the stability, and then the reducing likelihood the CO2, the oxygen release, liberation from the structure. The major challenge of these materials are the low and the poor intrinsic conductivity. So it is important and effective to improve electrochemical performance of phosphate-based materials to improve the capacity of these materials. There are some techniques to improve this poor and low conductivity. Example by coating using different agents, coating carbons, nanotube carbons, using silicon, using the other materials, or the modification of the surface to avoid or to reduce the SEI formation that affect the chargeability of the battery. Also by adding some almost transition metals to increase the performance of these materials, or by morphology control, the electrolyte modification. We have seen some presentations, some interesting presentation today, so that introduce these electrolyte modifications. As a conclusion, we can say that sodium-ion batteries are considered among the best candidates power source because sodium is widely available, it is cheaper, then it exhibits similar contents as lithium-ion batteries. Phosphate frameworks materials are full of variety. We have a lot of materials, phosphate materials, nasicon, pyrophosphate, oxyphosphate, or that one orthophosphate. To address the low intrinsic electronic conductivity of phosphate-based material, there are several strategies, including improvement of surface by coating, control of size in morphology, tailored synthesis, also the modification of electrolyte properties. In perspectives or outlooks in the Moroccan context, as we know all, Morocco is the leading manufacturer of vehicles in Africa, so it is expected to shift from the traditional vehicles to electric vehicles. Also, we dispose the raw materials that are the disposal for the materials or for the batteries research or synthesis. Also, we have an ambitious production plans with an international cooperation for electric vehicles batteries productions with Chinese companies. Also, a decarbonization of products and activities of the UCP for phosphate groups. The focus of our team is the synthesis and the characterization of phosphate-based materials for high energy density batteries. These are our team members, and we are open to collaborative ventures for advancing our cutting-edge ventures, research. And thank you for your attention.
Thank you very much. Do you have any questions?
Thank you for your talk. I fully agree phosphates are very interesting for sodium batteries, but it's quite interesting because lithium iron phosphate has a drawback of very large volume expansion upon cycling. So why volume expansion is a problem for lithium cathodes phosphates, but it's not, according to your presentation, for sodium phosphates? Because I would expect that the volume increase would be even larger than for lithium intercalation.
Thank you for your interesting question. So our focus of research is to develop phosphate-based materials both for lithium and sodium-ion batteries. We don't have a specification for sodium-ion batteries. Just for the presentation, I choose to talk about the sodium-ion batteries, because here we are focusing on high energy density batteries without any specification of the type of the batteries. We are kind of the both, so either lithium or sodium-ion batteries.
Which kind of phosphates are you working on? Pyrophosphates, orthophosphates?
All type of phosphates.
Okay, so I send you an email, that's very interesting. Okay, thank you.
Thank you. For this one, is the synthesis process of XRD is for anoxyphosphate. Yeah.
Any more questions? Okay, thank you very much for your presentation. So now we move to the next presentation, which will be held by Julián Acevedo. He comes from Universidad de Antioquia, and he will present the effect of mineral matter in an activated carbon from palm kernel shell on the electrochemical properties of lithium-sulfur cells.
You know how to use it? So this is the cursor, and this is not standing. Okay, thank you. So hello everyone. As I've been presented, I'm Julián Acevedo. I'm a master's student in the University of Antioquia in Colombia. So I'm here to talk to you about some of my research about lithium-sulfur batteries, specifically in a sulfur host that is composed of an active carbon. So first, I use the palm kernel shell as the source to produce a sulfur host, an active carbon material, but this kind of materials has some mineral content that is about 9%, and it could be composed of many different elements. But the principles are silicon, aluminum, and iron. But in the literature, there is no much report, or they don't say much about what is the effect that this inorganic matter or these inorganic elements has on the impact and the electrochemical performances of these materials in lithium-sulfur batteries. So I want to know what is happening with these materials in the application. If there's some pore blocking, decreasing of conductivity, and also it could be as a catalyst, especially for the iron. So the methodology for this work, it comes from a pretreatment for the biomass by a hydrothermal treatment to degrade the lignocellulosic matrix to perform the acid washing to remove the inorganic elements. Then the chemical activation using potassium hydroxide, and after that we obtain the activated carbon for sulfur infiltration, the painting for the cell assembly in lithium in coin cells, reference CR 2032. For the results, we use hydrofluoric acid to remove the inorganic matter because the majority of the elements was silicon, iron, and potassium, as I told you. And hydrofluoric acid removes most of the elements in comparison with hydrochloric acid and nitric acid. We obtained two activated carbons, one demineralized and the other one without acid treatment. We obtained that the textural properties are nearly the same. The microporous structure is the same for both materials, but one has a higher specific surface area and also a higher pore volume. Both materials, one has an ash content about 22% and the other one nearly 4%. And the material demineralized has a lower deorganized portion in the Raman spectroscopy, so we have a material that is more graphitic and also could be more conductive. And for the XRD measurements, we obtained that the material without demineralization processes has some little peaks around it. This could be related to some crystalline form, but due to the low resolution and the very lower intensity, we cannot specify what kind of material we have. But for the CIM images, we see that for the material without the acid treatment, we obtain a little spheres like this. And looking at the EDS spectrum, we see that these spheres are made principally from silicon, and also the silicon content is higher in this material. So for the electrochemical measurements, first in the TGA, with the materials with sulfur, we obtain sulfur loss around 500 degrees Celsius. This is related to sulfur interacting chemically, maybe with the silicon and on the carbon. And this could be related to a lower specific capacity, as can be seen here in the cyclic voltammetry. With this, we also have the cycling for the battery. We have higher capacities with the material demineralized than the activated carbon without acid treatment. And also, looking at the EIS spectrum, we see that the material without acid treatment has a higher resistance for charge transfer that is related to the high silicon content and the lower graphitization degree. And well, we can see that upon cycling, we obtain that the silicon content could be lowering we can have a deposition of some non-active material on surface of the electrode. And for that, the mineralization process leads to an increase in specific capacity, around 50%. And for conclusions, as I said before, hydrofluoric acid is the most effective acid to reduce ashes. Demineralization leads to higher surface area per volume and graphitization degree. And the mineral content affects electrochemistry. The absence of inorganic matter increases capacity by 50%. And finally, we acknowledge the Ministry of Science of Colombia for the funding of this project.
Thank you for this nice presentation. We are open to discussion. Do you have any questions?
Thank you. It's always very nice to see new ways of getting carbon. And you are a master student.
Yeah.
Okay, so this is, do you plan to go ahead with your thesis on this topic, or what is the perspective to further go on batteries? Or it's very nice, it's master, congratulations, and what are your plans for future?
Okay, thank you.
It's a master student, this is why I mentioned this.
This is my final semester for my master. So now I'm here in Spain doing an internship in the ICB Institute for finalizing the characterization and also electrochemical test for these kind of materials, and also to know more deeper knowledge about the chemistry inside these kind of materials. In my mind, I want to finish this research with my master, and also I want to do a PhD in, I don't know if in electrochemistry or in other field, but I am open to it.
Okay, well, I'm going to make you a scientific question for your master. Okay, did you compare your results with other forms of activated carbon that we can get from, I don't know, from biological waste or something? Because there are many ways of getting carbon. So
Oh,
did
yeah.
you compare? Is better, worse, or same?
Yeah, well, the majority of materials used for this are synthetic carbons that are like carbon nanotubes, CMK3 carbons, and they are expensive. So we propose, well, we don't. the scientific community has been using biomasses for the production of carbon materials, but most of them have this issue with ashes. And a carbon which doesn't have many ashes and a lower inorganic matter content, it is the, well, I don't know the name in English, but it's the skin from the cocoa beans. Mm-hmm. Yeah. It has only potassium, and you can reduce it nearly as a full percent with no potassium on it. So maybe that could be a better source to produce carbon. But also you can use many sources like bones and yeah,
okay.
So much stuff.
Thank you.
Any more questions?
It's a nice presentation. Just I have some one electrochemistry like a question. So you in the electrochemistry graph, your Coulombic efficiency is more than 100%. Can you explain that one? Here.
Oh yeah, the Coulombic efficiency.
More than 100%.
Yeah, it's more than 100%. We think that it's because the carbon could be acting as a supercapacitor, so it could be retaining some charge. So that could lead to the Coulombic efficiency higher than 100%.
And the next question is, you use hydrofluoric acid, right?
Yeah.
So you know how much dangerous this is?
Sorry?
How much dangerous this acid is, how much toxicity it has, you know that already.
Yeah, so hydrofluoric acid is
so
really
it's
dangerous, but we're using a concentration really low, nearly below 1% by hydrofluoric acid in
But
volume.
still it's very dangerous. It's 1 million billion times stronger than hydrochloric acid or sulfuric acid. So if you touch to the hand and it will go to the bones. So you have any future alternates to replace this HF2 using molten salt method or something else to replace this method to get the same results but with something passive inorganic chemistry and all?
Yeah, we tried the mineralization with a base, but because of the biomass, we obtained some saponification reactions, and the processing of the material was a bit difficult, so that's why we use hydrofluoric acid. Mm-hmm.
Any more questions? Okay, we thank you again for your presentation.
Okay.
And now I would like to welcome Maud Ubaidullah.
आगे पीछे कौन सा है?
He comes from King Saud University, and he will present the topic waste PET, plastic-derived MOFs for energy applications. So whenever you want.
Hello everyone. The title of my talk is waste PET plastic-derived MOFs for energy application, polyethylene terephthalate plastic. University at a glance, King Saud University, it was established in 1957. Around 40,000 students are there, and 7% are international students, and it has different streams or courses. So the outline of my talk is this section first, about the current energy scenario, then energy storage, and plastic waste material and its recycling for energy storage applications. And section 2 comes about the achievements and challenges and case study of supercapacitor. And section 3 about the plastic waste material recycling and its application in energy storage. And section 4 is conclusion. So the current energy scenario is that there is a huge concern about the environmental energy issue, that two most challenging issue or most serious problems we have in 21st century. Demand and for energy conversion and storage, why it is like so important, because severe like environmental pollution caused by this widespread use of fossil fuel and other materials, and what are the consequences. So consequences by using these fossil fuels are rapid depletion of fossil fuels, carbon emission, and global warming and environmental issues. So what are the solutions? So solution, there is a video, small video here, if there is, or sound is there or no?
We can protect the resources we share by creating smarter packaging, by choosing ingredients that meet high environmental and social standards, and that enables a circular economy. We can protect the climate we depend on by switching to low-carbon transport, by building state-of-the-art factories that use less power and greener power, by empowering manufacturers to explore sustainable technologies. We can protect the resources we share every day by using products that save water and energy. Experts predict there'll be more than 9 billion of us sharing this planet by 2050. That means we need to protect it more than ever. So let's put the power of 9 billion minds together. Whoever you are, wherever you are. This is your planet. It's our planet. If you love it, protect it every single day.
Well, I think this is a strong message to all of us. Yes. So energy storage is the rational use of clean and renewable energy, and development of sustainable energy storage systems to have emerged as a global goal for addressing energy and environmental issues. So the main focus of this talk is just to use the waste plastic which we are using in our daily lives, and to produce some energy materials of metal organic frameworks for supercapacitor and batteries. So here I am discussing about the supercapacitor. So plastic pollution is one of the biggest problem, and around 400 million metric tons of plastic production is annually, and it is the serious concern, and we are it is the prediction that in coming 25 years it will be threefold. So what are the harms of of these plastics which contains benzene and vinyl chloride? So it may cause cancer, birth defects, and damage of nervous system and others. So and how we can recycle it, and it is slowly degrade, or low, it has low biodegradability. So it is often said that the plastic problem is a third world country, third world issue, but we are facing these challenges everywhere around the world. So what are the recycling of plastic materials? So how we can recycle this one, and how we can recycle waste plastic in a green and sustainable way. So this is the important challenge we have. So high value added conversion of these plastic to produce some material which can be used in supercapacitor, or phase change material, or fuel cell, or hydrogen generation. So what we have done so far, so we have recycle this plastic, and to depolymerize this PET plastic into the benzene 1,4-dicarboxylic acid, which is the basic unit of this one, and we use this one to synthesize metal organic framework as a organic linker. So after producing these MOFs, different kind of MOFs we have produced, like MOF 5 and zinc MOF, nickel MOF, cobalt MOF, and zirconium MOF. So then we have done activation, and after activation we have like used these MOFs in supercapacitor studies. So these are our results. So the first study about the MOF 5 and cobalt MOF, and then we have carbonized it to make the zinc oxide mesoporous carbon and cobalt oxide mesoporous carbon, and use in the electrochemical studies or supercapacitor studies, and check the performance. And we got for zinc oxide mesoporous carbon, we got the specific capacitance about 97%, 97 farad per gram. And for cobalt oxide mesoporous carbon, we got around 180 farad per gram specific capacitance at 5 millivolt scan rate, 5 millivolt per second, using 6 molar KOH electrolyte. So this is the cyclic stability and the charge discharge stability and Nikas plot, and this is the power Regan plot about the energy density and power density. It shows very good energy density, around 68 watt hour per kilogram, and power density 149.1 watt per kilogram for the cobalt oxide mesoporous carbon. Another study is about the nickel MOF, and by nickel MOF I'm trying. So this is nickel oxide nitrogen doped porous carbon, and we have synthesized by the same method, and by using the plastic derived benzene 1,4-dicarboxylic acid as a organic linker, and by this solvothermal process, and these are the results. And come on the electrochemical studies. So for supercapacitive performance, so in 2 electrode systems, it shows around in 3 electrode system, it shows around 581.30 farad per gram specific capacitance at a scan rate of 5 millivolt per second. And in 2 electrode system, it shows around 291 farad per gram specific capacitance at 5 millivolt per second. So this is the conclusion of my talk, discussing about the current energy scenario for energy storage and plastic recycling, and to produce the value added MOFs by using the metal nickel, zinc, and cobalt, and some different. So here we are discussing just about the nickel, zinc, and cobalt, and make their oxides with porous carbon, and check their supercapacitive studies. These metal possess excellent specific capacitance and good cyclic stability, and their high performance can be attributed due to their high specific surface area. So this work not only provide high performance electron metal for supercapacitor, but open up new avenues for the current in the battery direction. So these are the benefits of converting of recycling of plastic, converting energy, lower emission, conservation of resources, reusability, save landfill space, and create jobs opportunities. So I would like to acknowledge first of all my university, King Saud University, Riyadh, Saudi Arabia, and of course University Carlos Madrid, and our funding agency Deanship of Scientific Research, King Saud University, through project number this, and Professor Alejandro, last but not least Professor Alejandro, who invited me and gave me a chance to present my work, and my professor, Professor Abdullah Al-Enezi, and Dr. Bidhan Pandit, of course, for invited me of this talk. Thank you so much. I tried to make it fast, but I don't know.
Thank you very much. We have time for one very, very fast question. Do you have any question?
Just a remark. It's not so easy to recycle, to depolymerize the PET,
yes,
even if it is a polyester.
Yes.
And globally, I don't think that polymers are responsible of the world pollution.
Yeah.
I think that if you use glass instead of polymer, we will have much more energy consumption.
Yes, sir. Yeah, actually this is the PET plastic, polyethylene terephthalate, and it is commonly used in food processing packets and all, So in our daily life, so it is like not too much biodegradable. It is slow biodegradable, and we depolymerize this by like glycolysis and acidolysis process, and then use this like the basic units of as an organic linker to produce the metal organic framework of different metal ions.
Okay.
Thank you very much.
Thanks a lot.
And now please welcome Jorge González Morales from Instituto de Cerámica y Vidrio. He will present the topic, Synthesis of Sustainable Catalysis for Zinc-Air Batteries. Okay.
Hi, my name is...
You may start.
Okay. Hi, my name is Jorge González. I am from the Instituto Cerámica y Vidrio of Madrid, and I want to present my work already displayed. The state of art of the batteries consists in a really low energy density that doesn't allow the correct competition with gasoline and other fossil fuels. This can be mitigated with the use of zinc-ion and lithium-ion batteries that have around 3 times and 10 times the energy density of conventional lithium-ion batteries. This is also involved in a constant and growing demand for more batteries and other energy storage systems. Our purpose is the use of zinc oxide batteries, in your case composed of a 3-dimensional zinc anode that allows the interaction of all the active material with the aqueous electrolyte, and an iron electrode that allows the interaction between the oxygen supply, the electrode-electrolyte interaction, and the electron supply in the surface of the iron electrodes. In this field, we have assembled a battery consisting of a metal anode, an aqueous electrolyte, and a porous iron electrode, as we can see in this image. Our experimental results consist in a working electrode of nickel foam. This nickel foam supports the catalyzer, in the case an iron catalyzer. We use as a counter electrode a zinc pellet with comfort of particles around 150 microns each one. And we use a reference electrode that allows us to measure the working potential and the counter electrode potential and see the process that occurs during the cycling of the battery. As electrolyte, we use potassium hydroxide just because it's really cheap and it's really optimal for this kind of batteries. We operate between a voltage range of around 1 volt and with a current intensity around 0.2 milliamperes per square centimeters. This is the configuration of a battery, and this is the results. These are really good results, really new results that indicates that our battery is capable of cycling around a few thousand cycles. We don't know the limit because these batteries are already cycling, but this is really positive because usually a zinc battery operates around a few 100, 200, 300 cycles. And also, the use of reference electrons allows us to measure the counter potential, and we see that the counter electrode that usually is expected to be more or less stable once it starts cycling for several cycles, around a few hundreds, it starts cycling, changing between the potential of zinc oxide and zinc metal. And if we analyze, we confirm our conclusions that we have an efficient catalyst for oxygen evolution reaction and oxygen evolution reaction, and that we have a battery that is capable of cycling at least a few thousand cycles. And this is all that I want to present for this presentation, and I only want to thank all the parts involved in this work.
Thank you very much. We are open to discussion. Do you have any questions? Okay, so I have one curiosity. Have you addressed any kind of study regarding environmental impact when comparing this kind of technology with sodium, lithium?
I mean, we use materials. We use minerals. These minerals that's the growth in gardens. We use materials produced by heavy industry with a high impact. But, and this is a big but, these materials are more sustainable. We have, its impact is high, but it's infinite. Well, infinite. Sorry for this expression. It's in comparison with lithium is extremely low. It's also really more accessible. In fact, all our investigation, all our research is based on the Critical Raw Material Act. This is the reason why we don't use PGMs, we don't use cobalt, we use every single material that is accessible in, I hate this phrase, but in the European context. Okay? We try to minimize the impact, but also we have to maximize the impact, the effectiveness of our material. For example, we use nickel as a material support instead of carbon. It has a higher impact, but for the operation of the battery, it presents a longer stability that is, in the long term, better for us. So we measure all the impacts, but we also try to maximize the efficiency.
Thank you. Any more questions? No.
Why you use a zinc pellet instead of zinc foil?
Because the biggest problem, or at least for me, for my experience, of zinc batteries is the passivation of the zinc anode. In fact, if we go here, we used to stop working here because we thought that this is the moment in which our battery died, because we used to operate with only 2 electrodes. So when the counter electrode starts to cycling like this, we see a huge drops in the working potential due to that is counter and reference, and we thought that the battery was dying. The problem was that we obtained several layers of zinc oxide that passivates the anode, and we thought that it was a failure of the working of the system. But no, it's just that if we use a porous electrode or pellets, we have a bigger surface and bigger active material, and we discovered that this was the solution. Because if we measure this with zinc foil, we only see a really fast passivation of the electrodes. I know.
Okay, I should think about that.
Thank you.
Any more questions? Okay, then we thank you again for your presentation.
¿Por qué aplaudo yo? Vale.
And now we welcome our last presenter, who is Antonio Fernandez. Antonio Fernández from Universidad Carlos III de Madrid, and he will present ultra-thick additive-free ceramic LCO electrodes obtained by powder extrusion molding. When you want.
Good evening, everyone. I will briefly explain what we are doing on the preparation of thick electrode by powder extrusion molding. Okay. One strategy to increase the energy density of the current lithium-ion batteries is the use of thick electrodes. As an example, for a battery with an electrode of 40 micrometers, the amount of inactive material is around 60%. If the electrode is thickened to 210 micrometers, this amount of inactive material is reduced to 30%. However, by the conventional tape casting method, the electrodes are limited to the range of 50 to 100 micrometers of thickness due to the critical cracking thickness, which is the maximum thickness that can be reached without the lamination during the drying process, and due to the limited penetration depth, the maximum distance the lithium ions can go through, limited due to the tortuosity. We shouldn't forget that this method uses N-methylpyrrolidone, which is toxic and has environmental concerns. So one technique that doesn't use N-methylpyrrolidone is the powder extrusion molding, which is easy to scale and cost effective. First, there's a first step of mixing of the binder system with the active material, in this case, lithium cobalt oxide. A rheological study is required to determine the maximum powder loading that we can use without inhomogeneities. In this case, it was 60%. Then, secondly, there is a extrusion step to obtain what we call the green sample. In this case, they have a thickness of 500 micrometers. Then there is a solvent debinding to remove partially the binding system, and a thermal debinding, and we evaluated 2 different atmospheres, under nitrogen and air. In the case of nitrogen, we have some residual carbon that can be beneficial to improve the electrical properties of the final electrode. Then, fourth step is the sintering. We evaluated different temperatures. First, under nitrogen atmosphere, we can observe by XRD the formation of a secondary phase, cobalt monoxide, that increase with increasing the temperature. This is due to the reducing effect of the remaining carbon. And so this atmosphere has to be ruled out. So in air, we don't observe by XRD any secondary phases. So for a first evaluation in lithium half cells, we used electrode sintered at 1000 degrees, which has a porosity of around 35%. We obtained, as we can see at the right, capacities at low voltage for around 100 milliampere-hour per grams, but the capacity decayed drastically at a high rate. So using electrodes sintered at 900 degrees, which has a higher porosity of near 50%, at C/12, we can reach capacities, areal capacity, which is important, of 13 milliampere-hour per centimeter square, which is much more than that compared to the conventional electrodes, which is usually between 1 and 2 milliampere-hour per centimeter square. So finally, to conclude, so we developed successfully electrodes of 500 micrometers of thickness by this method. We determined the optimal powder loading of 60%, the atmosphere that we should use, and we confirmed that we have to use low sinter electrodes to have a good electrochemical performance, and an electrode with high areal capacity, much more than those commercial were obtained. And finally, I'd like to acknowledge the author of this work and the founding source, also the member of our group, SIDMAT, and the members of our department. And thank you very much for your attention.
Thank you very much for this nice presentation. Do you have any questions?
I don't know if I can ask a question, being belonging to the same group, but I have a question. I have 2 questions. Do you need to have the carbon that remain, or for the electronic conductivity, or the electronic conductivity of the lithium cobalt is enough?
The main limiting factor is the ionic conductivity in this case. So the porosity is much more important than the carbon. So the LCO has, in theory, a good conductivity. If we keep the prepared electrode in an atmosphere that they don't get carbonates, the conductivity is okay.
Thank you.
Any more questions?
What is the area of the electrodes that usually you prepare with this technique?
The
area, the size of the electrodes.
The size of this electrode. We use a very small square of 5 by 5 millimeters. So to do the test, of course, we can prepare, but the mold we have to do the extrusion have this size. So we take this, but they could be bigger if we do intrusion instead of extrusion. They could have the size of the coin cell.
Is it easy to scale up the area of the electrodes?
Could be possible to scale it, yes. Very easy. This method is very easy to scale. You can do any site if you have
the mold.
The mold to
Okay.
do it. Yeah.
Thank you.
Any more questions? Okay, we thank you again for your presentation.
Thank you.
And with this presentation, we close this session. Thank you very much.
So that concludes the session number 4. So in closing, I would like to extend my heartfelt thanks to the organizing committee, sponsor, and all the behind-the-scenes contributors who have worked tirelessly to make this conference a success. So this is the first installment of the conference, Advanced Material and Energy Storage. I'm going to join very soon Imperial College London, so the next installment will be in London. So I will all going to invite you for everyone to the conference again in London, so I will welcome in advance. And I know there's a lot of speakers today, so we are in a hurry. You could not talk to each other. Maybe after this conference, we can meet outside for a group photo, or we can go to grab some drinks outside and all, if you have time. I would like to take a moment to express my sincere appreciation to a truly exceptional individual, my supervisor, Professor Alejandro. Thank you, Professor, for your commitment to excellence and for being the driving force of the behind the success of this conference. Your dedication is deeply appreciated. Without further delay, please join me to welcoming Professor Alejandro to the stage for the closing speech. So, thank you.
Thank you all the speakers, thank you all the sponsors, thank you all the sponsors, especially Biologic. The CONEX program, I think, is a good program in the university that start with Professor Sanchez. He was a experienced CONEX. Later on, there is a program just for young people, like Vidhan Pandit. And also, I want to say thank you, Vidhan, just for your time. Yes, we just spent here 3 years. It was incredible. I think you demonstrate in the lab that you have large skills. And then, in fact, you got a position in Imperial College, just very competitive for that. So anyway, thank you all the speakers. And see you next time. Okay, thank you.